This complete Kubernetes course is designed to take you from a cluster novice to a cloud-native architect. You'll learn to deploy a complete microservices application end-to-end, ensuring you master everything from core architecture to advanced networking. You'll gain deep technical expertise in critical components like the Gateway API, role-based access control, and stateful databases, all while implementing industry standard monitoring with Prometheus and Grafana. You'll gain the practical confidence to build, secure, and scale production-grade environments in any cloud ecosystem.
Kubernetes, Kubernetes, Kubernetes. We all want to learn Kubernetes, but what is the right way to learn Kubernetes? I myself have created a lot of content on KubeSimplify for learning Kubernetes. My past workshop got 1.7 million views, but I am really excited to put all my effort in and create a Kubernetes course for you covering the latest Kubernetes features and the latest Kubernetes version 1.33. My name is Sam Pathak and I am the founder of KubeSimplify, and I'm very excited to bring you the Kubernetes course. So we are here to learn about Kubernetes. But wait. Before we dive into the world of Kubernetes, I think it is important to understand a bit of the computing history and then a bit of where we are in the ecosystem of Kubernetes, like how it came, a bit of history of Kubernetes as well. So let's talk about the history first. Long time back, or even today, the main goal is to deploy the application. This is our main goal. In order to do anything or any of the tooling that we are using, these are the helper tooling that we are using to deploy faster, debug faster, deploy it at scale and all that stuff. But in the end, what we want, and as an enterprise needs to ship software and to ship applications to their end users. That was the case decades ago. That is the case today. The tooling has evolved. Let's try to understand how the tooling has evolved. So long time back, an enterprise used to order hardware in order to build their on-premise data centers. So now they are placing an order to the provider of their choice, maybe IBM or whatever that is. They are ordering the hardware. There is a whole process that is being incorporated in that, and now they have the hardware stack ready. Now there are a bunch of network engineers who are working to make that hardware sit perfectly in their data center or lab, wherever that is. And then, so this is the server or creating of rack or whatever that is. And then they install the required operating system on top of it. And then they also have a team of sysadmin who installs the libraries, dependencies, and all the tooling required to deploy the application. Now, the thing is, the application can be a Java app or a Python app or whatever language the app is, or C app. So there has to be specific tooling that has to be incorporated in order to deploy these set of application. For example, if it's a Java application, then you have to install JDK and the libraries and dependencies for that particular application, and then your application will be running over here. Now, the developers or the team of developers, what they want to do is they want to ship a new version of the application. So they would kind of do, it's a monolith application at this particular point of time. Like everything is written in one language. So all of them are kind of Java developers, and very difficult if any new thing comes up in the market and they want to incorporate that, or their application might improve performance and stuff. But it will be very difficult for them now, because now the whole stack is only the Java stack. It's very difficult to change, and it's very difficult to add anything new with a separate stack. So this is the monolith architecture. Yeah, it's faster. It's easier when the team is small, and it's also kind of easier because there is only one kind of place to make the changes. But if you make one change and if there are different endpoints, then the application needs to be rebuilt. All the components need to be rebuilt, and that might cause an issue. So let's say there is an application for login and you are making a change to the login, but there are other endpoints for that. Like there's a checkout endpoint, there's, testing endpoint. Those might get impacted. And if one thing breaks, everything breaks. If one feature fails, everything has to be reverted back. So those are some of the limitations of the monolithic kind of architecture. We'll go into how the next architectures kind of look like, which is the microservice architecture. So microservice architecture is a modern way of deploying the applications. But before moving to that, let's keep continuing of what is happening now. So now we have this server. Let's say the application now needs something more, or there has to be another version of the application that needs to be deployed. So there is another environment that needs to be created. So in a similar manner, this particular thing will be copied over here, and this will be called staging. In the other environment, there has to be another order placed, and everything needs to be created again for the dev environment. Now, let's say there is a small application or another application that needs to be deployed. You can't deploy it over here. So there needs to be another piece of hardware that is being installed, and all the layers will be over here, and then there will be app number 2. Now, the problem here is there is a lot of wastage of resources. So what is happening is you have this server here, you have this server here, you have this server here. But this server is like, only like maybe 20% is used. And on server B, the application is taking maybe 30%. Application C is kind of taking maybe 40%. But what about the rest? The rest of the servers are getting wasted. The rest of the servers are getting wasted. This is where the industry evolved, and there was around 1960 time frame, there was this whole virtualization era that started. So virtualization means slicing up of the hardware into smaller chunks so that resource utilization can be much better. Now, what that means is, let's say you have a data center over here, and you have a data center over here, like the pieces of your server stack over here. Now, what will happen is, this is your server, this is your server. Now, here you'll be having OS, or one can be without OS as well, because there are two type, like mainly the virtualization is type 1, type 2 kind of thing. So the type 2 one is where you can have the hypervisor here. This will be able to virtualize that. So this will create VMs. And other can be directly on the bare metal. You can have hypervisor. So this is type 1. Type 1 like the VMware, which still is kind of one of the dominant players in the industry. So it lets you create VMs. Now what it does is, it takes your CPU, memory, and all the components, and it separates them out in layers. Like it separates them out in small number of batches. Now you don't need to understand in depth, because there is a lot of in depth that we can go over here. But we are going to through a very small brief history before we get into the next layer. So this is where things were. So we moved from the bare metal, like we still use bare metal, like we haven't moved, but we have improvised or improved the bare metal ecosystem. So the bare metal is there, the bare metal is still there, but it is now virtualized. So bare metal is now virtualized. Now when the bare metal is virtualized, these servers are being used in a more efficient and resource optimized manner. We are being able to use these servers in full capacity. But the thing is, for enterprises, it is fine. For enterprise, it is fine to pay upfront cost of, let's say, 100 server rack when they just have maybe 100 applications or maybe 50 applications. But what about a small enterprise, a small startup? how do they kickstart? They are not, they just have an idea, they have an MVP and just want to deploy and ship their application to their customers to get the feedback, initial feedback. They cannot go into the 6 months of loop of placing an order, getting it, having network engineers dedicate, and then deploying the app. So 1, 2, 3, 4, all these steps, they are unnecessary. Why to have all these steps in place? So this is where the era of cloud computing. Okay. Now you have clouds like AWS, GCP, Azure, and you also have, smaller cloud providers like Exoscale. Shout out to them for helping me create this course for everyone for free. So these are the set of cloud providers. Now, what is a cloud provider? So as cloud provider, what they have done is they have created very big, like massive data centers, DCs, which we call. Here they have racks. Now these racks are servers. These racks are servers. So there is a lot of capacity. So there is a lot of capacity that they have. There are a lot of CPUs and RAM. Now, if a user wants to deploy an application, these cloud providers have built a UI, CLI, all the interfaces through which this user can communicate and can create a VM. This VM, which I showed here, this particular VM on demand, on demand in different parts of the world that can be closer to their location, because there are a lot of data centers now in a lot of regions around the globe. So they can create this on demand and they are able to get it within a few minutes. Now this is massive, because if they want to expand their application, they can immediately get that. If there is a Black Friday sale happening, then they can order a few more already, or put some in reserved mode already, reserved instances, and add them to the pool where they can deploy their application and load balance the traffic across all these nodes, all these virtual machines. This is pretty cool, because now they have easy to use virtual machines on demand that they can easily create via the cloud console, which is called the UI, or via their CLI. So cloud providers abstracted away the complexity of data centers. They created them for you. So your data still goes on to the data center, and which is then deployed over there. But they abstracted away all the complexity, provided you with the APIs that you can directly contact or interact with the CLIs or the UI interface as well. And you are easily able to deploy your application. You can deploy your application, you can order a lot of other services on demand, and you'll be able to even expand. So if you want an app too, you can still have more number of servers that you can order. So this was the cloud era. In the cloud, everything is like, it was meant to be cheap, but we have seen in the past that cloud providers are actually becoming a lot costlier, and some of the organizations are going back to the data centers model where they host whatever they host because of the ingress fee, egress fees, and all this, so on and so forth stuff. And this is where the smaller cloud providers are coming in, like Exoscale, and they are shining because they are economical in nature, and they are very specific to smaller number of services that they provide, and they provide them in a very efficient manner, because they put in all effort on smaller number of services to make sure you can deploy the application in a neater way. So that's how the era has been so far. So you have DC, data center era, which is still there. Okay, bare metal is still something that people do, and a lot of people are switching back from cloud to bare metals as well. So data center, but the next technology is virtualization. Now the next one is virtualization and cloud. So cloud being the best one out there, because one click you get everything. Now it comes to containers and Kubernetes era. Now this is coming from 2013 timeframe. So containers became popular because of the introduction to Docker. Docker is a company, a tool, a CLI, a product that actually hyped up, or I should say streamlined the containerization ecosystem, led to the birth of container orchestrator and stuff like Kubernetes. But let's try to understand some of the problems that containers solve and why they are one of the critical milestones in the industry, in this whole computing industry, the whole industry of deploying the application. Always remember, right now as well, since we are going through a brief history, now also the main aim is to deploy the application. Main aim is to deploy the application. Now the huge monolith, which is a full application, is broken down service wise. Like for example, you have a login, you have a sign up, you have main app, and that also you can have, front page, then you can have a checkout page, you can have a dashboard. So there can be different services. And now, as per the microservices architecture, these will be a separate application within itself, like a separate microservice in itself. What that means is these all can be written in different languages. So this can be, the front end can be written in, in JS, Next.js. The back end or the login and the sign up can be written in Golang. And the AI stuff, the inferencing or the AI stuff can be written in Python. So it gives you a lot of flexibility in terms of the architecture. And since we are moving towards the containerization or the containerization architecture, I'm telling you about the technological shift, it is easier to containerize smaller set of microservices and run them individually as containers, and they can again communicate with each other rather than a huge monolith application. One of the other drawbacks of monolith application that I told you, that it is very difficult to update the application. Now it's just you have to update the sign up or the login page. You can just update this, kill it, and rerun it. It should have the newer version of your sign up and the login flow. Rest all the applications will not have any set of downtime. So every microservice can independently move and independently scale as well. So you can scale one particular application where you think the load will be more during the peak seasons. You can scale that individual piece of application as well. So these are some of the benefits. Yeah, overall, since it takes time, so you can, this will talk to this will talk to this will talk to this will talk to this. So the time taken is more, and the time taken within the monolith application is less. So it is better performant, and there are a lot of scenarios where monolith is still relevant. But yeah, the modern architecture is the microservices kind of architecture. Now, I'm not going into the architecture wars over here, because I just want to show you as in a brief history of how we came to the world of Kubernetes and what Kubernetes is. And then we'll dive on into the app-based approach of learning Kubernetes, learning the crux of Kubernetes, because the end goal, remember, always the end goal is we need to deploy the application, and we need to deploy the application the best way possible. So now you can see that there is a virtual machine. This is the layer that I was previously talking to you about. So you have a bare metal server or a cloud server. And then you have this is a piece of hardware that will have a CPU, RAM, disk, network. Now you have the hypervisor on top of that, which is installed. Now you have the VMs. So hypervisor will be able to create the virtual machines, and this is the slice of the physical CPU, slice of the physical memory and the network which is there, and every VM will be there so that this can be used effectively. But still, what people have realized is even inside the virtual machines, people are not able to use this at full capacity. So because these are very big pieces of hardware, so how can we use it in a more efficient way? Now that led to the rise of containers. Now there are a lot more benefits of containers, like it's lightweight, it's faster to start. It uses Linux namespace to isolate each other or to create those containers. It uses the concept of Linux namespaces. So the shift from the monolith application to the microservices led to the small chunks of hundreds of applications talking to each other. If you have been part of the cloud native ecosystem, you're probably aware about this container and Kubernetes ecosystem. But now let's try to understand about the containers. So a container is a piece of software that packages the code. So you have this application, and your application is having, obviously it's having a piece of code, and with the code it has its dependencies, libraries which are there. So now container is a set that packages up all the code and its dependencies and runs as a process on the host. Remember this, it runs as a process on host. So in the end, all the containers are the processes that runs. It's a Linux process in the end. So and I told you it uses the power of Linux namespaces to run the applications as containers. So whenever you talk about containers, we try to compare that with Kubernetes ecosystem. So virtual machines are the actual slices of the physical hardware that you have multiple virtual machines created on a single machine depending on the hardware spec. In this way, you have different environment setup based on different flavors, different operating systems which are there. This can be Ubuntu, this can be CentOS, this can be Fedora or whatever that is. Containers are the slice of the operating system. So containers are the slice of the operating system to provide you with the look and feel of the operating system, which uses a container runtime. So here you have a physical machine, you have operating system, you still have your network tree process users operating system, whatever is there. And then you have a thing called container runtime. Now, when it all started, Docker kind of came into the picture and it hid up everything. So Docker engine was the one that is here. So Docker engine is the one that is there. So containers uses Linux, the concept of Linux namespaces, C groups, and union file system. So these three things. Linux namespaces. So containers uses Linux namespaces, C groups, and UFS, union file system, to glue and create a container. Using this, the operating system can be sliced and have containers running in an isolated way. Now let's see how that works. So as you can see, the process ID maps to the PID1 inside the container, and MNT maps to the root file system. Container has its own interface. Process inside the container can share resources and talk to each other using IPC. Every container has its identity, which is its host name, and the user root. So the user inside the container is root, but is mapped to a different user on the host. This is how containers are formed using the Linux namespaces. C groups are for the CPU, RAM, and block IO. When we talk about containers, you can run multiple containers from a single image. That actually works using the layered file system approach, which is copy on write, meaning that for each container, there is a writable layer specific to that container. Example, let's say you run C1, C2, C3, and all are from Nginx image, and make some changes to the HTML file from C2. So only the C2 is changed and other remains the same. Let's say you write a code in Python and pack it with its libraries and dependencies, and it's called a image. And this image is pushed to a registry, and when you run this, it is called a container. So that's what a container. This course is not about containers at all. This course is about Kubernetes. So the prerequisite for this particular course is actually containers. I'm just giving a small primer, small history and stuff of the containers, but this is in no way a course on containers. But I just wanted to tell you that, give you the history kind of thing. So coming to Docker, it first originated from .cloud, and LXC at that time was already there. They created LXC, they created something called DC, LXC plus AUFS. They moved to Docker. Slowly over time, they removed the dependency on LXC and then moved to libcontainer plus AUFS. Docker was launched in 2013, and they provide a nice developer experience of building and running the containers with storing the images onto the registry. Since then, it has evolved, and when you talk about orchestrating, the orchestrator engine is called Kubernetes. So now we are at Kubernetes. So Kubernetes is also known as K8s because there are like 8 alphabets within KNS. And it is an open source system for automating deployment, scaling, and management of containerized application. But it is much more than that because of the extensible projects which are there. Not only it can manage the containerized application, it can manage a lot of things. It's a CNCF graduated project. It's the first CNCF project. It was born out of the architectures of Borg and Omega. And I highly recommend checking out the Kubernetes documentary. I'll put the link in the description, where they tell you all the story of Borg and Omega, and how they planned to open source and bring out Kubernetes from the architectures of Borg and Omega. It was launched in 2014. It is already a 10-year-old plus technology, and it is designed for scale. But let's try to understand why actually Kubernetes is needed. Now, there are a lot of containers, which is there. Like, there are a lot of applications, and every microservice is a container which is there. So a few containers is fine, but what about scale? So there are a lot of things that goes into when we talk about running the microservices or running the container. So when you are running, let's say you have maybe 20 applications, every application is having 10 to 20 containers. So this comes to be about 200 containers bare minimum. So you are running 200 containers, and let's say you don't have any Kubernetes in place. So how you run it? So you have the system, or you have maybe multiple systems. So you run these containers manually. Now, how do you monitor them? So you need to have custom scripts in order to monitor these. So you need to monitor this. If it goes down, will it self-heal? What about that self-healing? You need to write a custom script for it. What about the connectivity? So if you have one container here, you want to have one container here, how will they communicate with each other? If you want to have redundancy, how will you manage that? One copy, then how will you run multiple copies of that container? What about the auto scaling? If you want to have one copy of this container or this particular VM, this can be VM1, this can be VM2, and another copy of this particular container or this particular node or virtual machine, I should say, then how will you manage the scheduling? So you have to do the manual scheduling, you have to do the manual auto scaling, you have to do the manual healing, you have to monitor it manually, you have to check for the uptime, you have to check for the scale. So everything is there, and these are the problems and the challenges when you do it manually. Yes, it is doable manually when you write lots and lots and lots of scripts. But why to write that? Because this is where you have Kubernetes. So it is where Kubernetes comes in, and this is what Kubernetes provides. So Kubernetes provide you everything in detail, where you have automatic scheduling. You can have, it has a mix of controllers that lets you run all the applications, and also Kubernetes is very extensible. So you let's say your name is, like, my name is Sayyam, and I want to create a object of Sayyam, but I can write a custom controller that can watch for this particular project with this particular kind, and it can actually create it and do some functionality. So there are controllers. For example, when you install Kubernetes, we'll go into the depths of it, but when you install Kubernetes and you have a Kubernetes cluster in place, then what happens is you can extend it. So you can install tools like Crossplane, and you can manage AWS resources from that. You can actually create a AWS YAML file over here, a S3 YAML file, and you can create that on the cluster. It will automatically create resources in AWS, manage resources from AWS. So saying that Kubernetes manage only containerized application is not entirely true. Like, it is true statement, but it is not a complete statement. So it is a true statement, but not a complete statement. So it complete is basically it can manage much more than the containerized application. It can manage databases, it can manage objects from other cloud providers. So it can manage a lot more than just the regular container. It can manage other Kubernetes clusters. So Kubernetes within Kubernetes is a very big thing these days in 2025. So that's what Kubernetes is. So till now, this was the brief history from data center to virtualization to cloud to containers, then Kubernetes. And actually, we have another technology called WebAssembly, which is also one of the very cool waves in this whole life cycle. And there's a WebAssembly course. I'm not going into that, but there's a WebAssembly course on KubeSimplify that you can watch. So that is the stack that we covered. And we covered monolith to microservices. And I also gave you the primer for Docker and container. Like it runs as Linux namespaces. So that was the brief history. Now let's come to what we'll be learning throughout this course in Kubernetes terms. So we'll be going through an application. So first I'll let you know what the application is. And then in order to deploy that application, we learn all the concepts. So we learn about Kubernetes deployment, services, ingress. We'll deploy the application using cert manager gateway API. So we'll learn about gateway API as well. We learn about load balancer. We learn about statefulset. We learn about Kubernetes volumes. So all the basic Kubernetes constructs we'll learn. We'll also learn about Kubernetes autoscaling. We'll also do the observability, a little bit of observability from the application. So I'll show you the application first, and then for the first time ever on my channel, I'll be showcasing creation of clusters. So we'll do KubeADM, self-managed, and then Exoscale managed. So we'll do two types of Kubernetes cluster. One is self-managed, one is managed Kubernetes cluster. And I'll show you other options as well, like kind, Docker desktop, and all that stuff. Once we create that, we'll go through the end-to-end architecture, including CRI, CNI, and CSI. Yes, you heard me right. So what are we waiting for? Let's move towards the application that we'll be deploying. And because remember, from the first point, I'm trying to say that the thing that we want to deploy is the application. The main goal is deploying the application. And in order to do that in the most efficient way in 2025 using Kubernetes, we learn all the concepts to deploy the application. Let's move on. The main goal of this particular course is to deploy the application, but let's try to understand the application. So the application is Game Hub. What that means is in this application, there are multiple services. So there is a game service, there is the auth service, there is the database, and then there is a front end. In front end, you have different things. You have a flow of sign up, you have a flow of login, and then you have the game, which is the actual game, and you authenticate it with the authentication service, and all the game logic happens in the game service. And all these components, like how they appear, they are in the front end service. So we have different mechanisms and different things in place when we talk about this particular application. This is how the game looks like. So you can see the Game Hub application. Right now, it's currently hosted on test.kubesimplify.com with HTTPS whole connection that is done using the gateway API K gateway. So this is the sign up page, and you can enter demo user 12, demo user 12 as the password. Sign up is successful. Okay. Now it comes to the login screen, demo user 12, demo user 12. It comes to the login. Like this is how the logged in user looks like. So this is logged in as demo user 12. You can see the dashboard. The dashboard stuff is actually public. Let's play maybe some of the games. So this also is front end. So you can play a snake game. So this is the snake app and we can play it. Let's start. Let's eat some food. And then let's die. Go back to the dashboard. So demo user 12, snake highest score was 3. Let's play tic-tac-toe and we will try to win. And we won. So if we go back to the dashboard, we can see our tic-tac-toe wins as 1. And then let's play rock, paper, scissors. Another interesting game. Rock, paper, scissors. Let's select paper. It's a tie. Scissor, you lose. Rock, you lose. Paper, you lose. Scissor, tie. Rock, you lose. Rock, win. Finally, I won. I'm back to this rock, paper, scissors. Losses are more than the wins. Anyways, this is how it looks like. And this is how the dashboard looks like when we go back. And in general, when we log out, the dashboard page is public. So the dashboard page is public, but when we try to play Snake or play any other application, it asks us for the login again. So that's a application with a multi-tier application. And let's see some of the code for this as well, like how it works. So in sign up, there is a component called front end and auth service. In sign up, there is slash sign up that calls to the auth service register app.py receives it, and it receives the username and password. It hashes the password with bcrypt, and then stores it into PostgreSQL. Let's see that in action as well. So if you see, this is the sign up page. And this is where it comes in. It renders the classes, like it renders the username and the value. And on submit, it goes to handle sign up. And as soon as it goes to handle sign up, it calls the full URL of API auth register, and it waits for that. And along with that, it passes the username and password. Now, this is present in the auth service app.py. You can see app.root/register. It gets the username, gets the password, checks if it's, the basic checks of 3 characters and 6 characters long. Then it hashes it, connects to the DB, executes the query, insert into users with the username and the password hash, and then return. As soon as it returns, signup.js puts an alert of sign up successful, please log in. So that was the sign up flow that we saw. And the login also happens the same way. You would log in, auth login. It looks up for the user by the username, verifies the password, creates a JWT token with the username and the expiry. Expiry is currently 24 hours, means the session will be valid for 24 hours. And the front end, when everything is success, so the front end will receive a JWT token, which will be stored in the local storage. And if you see it here, there is a login.js. So in the login.js, you can see that it is calling the API auth login, and it is passing the username and the password again. As soon as it goes to app.py of the auth service, it goes to the login page, gets the username and the password, and encodes the password and tries to fetch the user, get the hashed password, try to compare that, and then create a JWT token with username and the expiry and the secret key. Secret key is just present over here, like your secret key. I mean, you can define that. And then it returns the token back. As soon as it receives, it does the local storage of token and get that token data. So that's the login flow. And authentication, so JWT is the key to secure communication between front end and back end. All APIs are using this. And in every API, you will find this authorization bearer JWT token passing it. And the backend use it with JWT.decode token secret key. So these things are happening. All the APIs are kind of using that. This is the game flow. So let's try to understand one game that we actually saw, which is the snake game. So this is the snake which is trying to eat. So the game is played in React using the state. When the food is eaten, as soon as the food is eaten, the score increments, and there is a post call to API game snake score, and it is called with the score. JWT token is sent in the header. That's why I said all the APIs are communicating with JWT. So you can see that all the APIs are using the bearer JWT token. Now it calls the backend service, which is the game service, extracts the username from the JWT, fetches the user ID, updates or insert the higher score. Like here, we only update the score if it's a higher score than the previous one in the Postgres database. And then we have the dashboard. Dashboard is public. It fetches all the scores from across all the tables inside the database and updates that. So let's see the snake game. So this is the snake game, and you can see the directions. You can see the collisions. If the food is eaten, that is important. So if the food is eaten and if the new score is greater than the previous score, it also gets the token. So it takes the token from the local storage, and here it calls the score. So along with the new score. So it is in the game service. It goes to the game service app.py, and here you have game stats, which is used by the dashboard, but you have a snake score because this one is pretty different. So you have snake score, and it updates the snake score. Like again, request token, it gets the token, verifies the token using the verify token command over here, JWT verification. It decodes and does all sorts of stuff. And then it also gets the score. Now it connects to the DB, connects the user ID from the username, and finds the user and then select the score. If the score is higher, if the previous score is higher already in the database, it doesn't do anything. If the new score is higher, then it kinds of update. So it does the update query of update snake set score, where the new score is whatever is passed on. So that's how the application works. Why I chose this particular application, it's fun, it's easy, it's game, and it has different bunch of things. It has a sign up flow, it has a login flow, it has a uh, authenticated UI, it has an unauthenticated UI, it has a database connection that it is having. So it's a kind of a multi-tier microservices architecture application that we are going to deploy. And it is already deployed actually on Kubernetes cluster. This is already a deployed application on Kubernetes cluster, which is there. So that's how it kind of does it. And we can see that for each application, like for auth service, we have a Docker file. So Docker file is the file that obviously is used to build up this particular image. I haven't concentrated on the best practice of the Docker file here yet, but still I have managed to use a slim image, work directory, copying the requirement.txt that is having all the libraries that it is using, and running all the requirements.txt, copying the app, and then using the Gunicon server, which is recommended for production. Same is for front end. So if you see, there is a front end Docker file as well. It's a multi-stage build, a much better build than the previous one, because so that we don't copy unnecessary binaries after the npm install. So it just takes the app build, user steer, Nginx HTML, and the Nginx conf as well. And then it uses the Nginx daemon auth. And then for the game service as well, we have a simple Python 3.9 slim image, work directory, copying the requirement.txt, bring the pip install, copying the app.py, exposing the port, and using the Gunicon server. So these are the three main components. Then we have init.sql that creates the list of databases. It is actually being done using a config map, which the concept will go later on, how it is using the init.sql. That was for local. And we have all the YAML manifest defined in the manifest section, which we will study when we are actually doing specific sections. Like, for example, when we'll be doing the deployments, we'll go through each of the deployment, like game deploy and how it is being deployed. But one thing that can be checked is all the Docker images and Docker builds are done using this command. So using Docker buildx build, since I am on Mac R1, but my cluster is running AMD 64. So I'm choosing platform Linux buildx, Linux AMD 64, tagging the image to my repository, and then pushing it. That's pretty much it that I'm doing. Now you don't have to worry about the other manifest, because this was just to showcase from where the image came, because we'll be using the same images in the deployment manifest that I'll be showcasing when I'll be walking through the deployments, services, and all the other sections, and we'll side by side deploy. So we'll learn the concept and then we'll deploy. And in the end, hopefully we'll be successfully able to deploy it on a new subdomain and on a fresh Kubernetes cluster. So that's the whole point of this particular course. So this is the application, and this is what we are going to deploy end to end. In order to create the self-managed Kubernetes cluster, we'll be using Exoscale. Here we have to go to compute instances and add instance. For the name, we can give Kubernetes 133A, we just use plain Ubuntu instance. We can pick any zone. We can pick a standard medium instance, and we can update the RSA pub. So I already have added my SSH key pair to this account. You can also add that. And for security group, I'll just add a few more security groups so that it has all the networking enabled. That's pretty much it. So we can add this particular Kubernetes 133A Ubuntu instance. And what we'll do is we'll create another one because we need to join a node as well. Like I need to show you how to join a particular node. We'll use exact same settings. Everything is working as it is. And we'll add that as well. So Kubernetes 133A, Kubernetes 133B, two instances are getting ready. So our instances are up and running. And now let's log into Kubernetes 133A. This is the public IP address. So SSH-I .ssh id rsa ubuntu @ and yes. Okay, we are logged in. Sudo su clear the screen. So we are logged in here, and what I'll do is I have a script. So vi demo.sh. Let's go through the script one by one because we need to install the Kubernetes cluster using kubeadm. So first of all, we begin by installing the regular Kubernetes binaries, which is the kubectl, kubeadm, and kubelet. So we set the apt keyring and add the official Kubernetes 1.33 repository, as you can see over here. Then we install the kubelet, kubeadm, and kubectl version 1.33, and we mark them apt mark hold. This ensures the version consistency. Now we disable the swap configurations. So the step number 2 is swap off the kernel modules. So we comment out swap from the /etc/fs tab and turn it off live with swap off -a. And then we load the overlay and the brnet filter, and then persist the kernel parameters for packet forwarding and network bridging using sysctl. So those are the persist kernel modules. The next step is installing and configuring containerd. So this particular section checks if the containerd is already present. If not, then it adds the Docker repository and generates the config.toml file and also updates the systemc look equal to true. And then systemctl restart containerd and enable containerd. And then it is time to pre-pull the images. So you can see kubeadm config image pull, and CRS socket is mentioned at run containerd.sock with the version Kubernetes 1.33. And then we give kubeadm init with the pod network CIDR range and upload certs at the control plane endpoint. In here, control plane endpoint will give the IP address of this particular instance, which is 159.100.248.188. And then CRS socket, then set up the kubeconfig for the user by creating this directory, copying the admin.conf file, which we'll study in detail what this file is, and then applying a CNI, which is the container network interface. So this is the setup that has to be done on the control plane node. And it's okay if you don't understand what a control plane node is. We'll just learn everything about that. Right now, it's important to just learn how the Kubernetes setup is done using kubeadm. So chmod +x demo.sh/demo.sh. So it will start installing all the things step by step. So installing kubeadm, kubectl, and kubelet. Now these are the swap off kernel modules, overlay, brnet filter, and then installation and configuration of containerd. So since it's a fresh Ubuntu instance, there is no containerd over here, so it is installing containerd here as well. Pulling all the images, registry.io, Kube API server, controller manager, Kube-Proxy, CoreDNS, scheduler, pause container, etcd container. So we'll study about all of these components in detail when we study the complete Kubernetes architecture. For now, these are the components that are required to be installed on this particular cluster. And after that, it is doing the kubeadm init, and it is starting kubelet, making sure it is healthy, configuring all the stuff, certificates, and it has already given that you should install and create this directory. I think those commands are also there, and it then installed the flannel as the network. So actually, kubectl get nodes should be there, and we have a control plane ready on Kubernetes 133A. So there is this command called kubeadm join with a token. So we definitely want to join, and we definitely want to join on the Kubernetes 133B. So let's log into that instance, which is the 23, which is the 159.100.247.26. So now we do SSH, and the command is SSH, and then we add the IP address of the B1. Yes. So we are logged into the B instance. Sudo su clear. What we'll do here is we don't have to install everything. So we'll copy only the relevant portions from the script that we had earlier. So we are demo.sh. So what we don't have to do is we do have to install all of these. We do have to install container D, and then we can skip the kubeadm init. We don't have to initialize the cluster, because initialization of the cluster only happens on the control plane nodes. You don't have to initialize any of the other clusters. Yes, if you need to do the multi-control plane setup, then there will be commands like this, like you can join any number of control planes as well using this command. But what we want is a simple two-node cluster with one control plane and one node. So we'll not use that. We'll just use the worker node. So this will be acting as a worker node. And we don't have to do the kubeadm init for that. So this much is enough for this particular instance. So chmod plus x demo /demo. Once the configuration is done, what we'll do is we'll copy this command kubeadm join till here and paste it to the worker node. So this is the command kubeadm join, and it should have joined the cluster. So kubectl gets nodes. Now this is what I'm then running on the control plane node, and soon we should see that from not ready it should become ready. So kubectl get pods -a. We should see that all of the pods are running. So by default, Kubernetes installs certain stuff like it has etcd, it has API server, controller manager, Kube-Proxy, Kubernetes scheduler, and then we installed a CNI flannel over here. So it has flannel pods as well. That is a very basic setup of Kubernetes cluster that looks like. So this is something which is called a self-managed Kubernetes cluster that we have created on Exoscale Ubuntu instances. We'll also create very shortly a SKS cluster, which is the managed Kubernetes offering by Exoscale. And mostly people use managed Kubernetes because you don't want to take the headache of running self-managed and maintaining that. If you want to do local testing, then also you have something which is called Docker Desktop. So Docker Desktop. So you can download the Docker Desktop, and you should be able to get Kubernetes here as well. So it comes with a Kubernetes cluster. And you can also do and install something which is called Kind. So Kind is another project in Kubernetes, which is Kubernetes in Docker. So local cluster for testing Kubernetes. It's a SIG project. It's a kind of a tool for running local Kubernetes cluster using Docker container nodes, and you can use Kind as well. But for all of the cores that we'll be using either the self-managed Kubernetes cluster whenever I have to log into the node and show you certain capabilities, and our application that we'll deploy will be deploying on the SKS Exoscale Kubernetes cluster, which will be production ready. So in order to create a managed Kubernetes cluster, the cloud provider that we'll be using is Exoscale. So Exoscale has happily partnered with Kube Simplify to bring you this particular course. So this is what we'll be using to deploy our complete end-to-end application. So this is how the portal looks like, portal.exoscale.com. You can see over here, it has a lot of services which are there, but we are most interested in SKS, which is the Kubernetes service for Exoscale, and they have named it as SKS. I already have a Kubernetes cluster which is there, but I want to show you how you can create a Kubernetes cluster from scratch in Exoscale Cloud. So you can use it using the UI. You can select these particular zones. You can give it a name, and you can do a starter or a pro one, and you can pick the Kubernetes version. And it's great that they have the latest and the greatest Kubernetes version support, which is 1.33. You can also put an auto upgrade on. You can choose between different CNIs, Calico or Cilium, and you can add the add-ons as well. Obviously, Cloud Controller is required if you want to use load balancer kind of thing. Metrics server is required if you want to use certain metrics. And the CSI is required if you want to use the storage classes and attach volumes to your pods. So you can do it via UI, but to make things a little bit interesting, what we'll do is we'll do it using the CLI. So there is the Exoscale CLI. They have a Terraform support, so everything is there, but we'll keep it simplistic. So you can use Exoscale CLI. In order to download the interface, you can directly do the curl command, or you can use Docker, or I'm on Mac, so I already have Exoscale installed over here. So when I do exo, these are the commands that you can actually run. So let's first do exoconfig. So I already have configured one account, but if you want to configure a new one, you can do that. It asks for API key. How to create that API key is you go to IAM, you go to keys, you go to add a key, and this is a course key, and let's make it owner, create. So the key becomes this, you copy that, I paste it here, and then the secret key. Name is course. So the default zone, you can pick the default zone, and you have now exoconfig configured as well. So exoconfig, and you can see configuration, which is over here. Now we can use that, or we can use the previous one, which is fine. So I'm using the previous one because I have already shown you my key and secret. So I'll just delete that so that you do not have access to it. Now let's create this step by step. So first things first is we need a security group. So in Exoscale, you have something which is called security groups. Obviously, these are the security groups to manage the traffic going in and out of Exoscale or your resources. So Exoscale compute security group, create Kube-Simplify security group. So that's what we are trying to create over here. And if I just refresh that, I'll be able to see a new security group over here. It has a name, it has an ID. Next step is to add the required security groups for Calico. Since we'll be using Calico, so we need to enable certain ports or node port services. We need to enable the kubelet access. We also need to enable the Calico VLAN traffic. So let's do that one by one. So Exoscale compute security group rule add Kube-Simplify. I want to add a security group for TCP, and I'm giving the description and network 0.0.0.0/0. These are the port numbers that I want to enable for the node port services, and it says the rule is added. The next one is for kubelet access 102.50, and description makes it more easier. And another one is the UDP for VXLAN 4789. So let's clear the screen. If we go back and we refresh it, we should be able to see a few rules appearing over here. And you can see 3 rules appearing over here. Now it's time to create SKS cluster. So Exo compute, so it's part of the compute service. SKS create, the name is Kube-Simplify. I'm naming the zone DEFRA1. Service level I'm putting as pro, and I'm creating a node pool name Kube-Simplify node pool. I'm giving it a size, so it should be a 3-node cluster, and I'm attaching the security group I just created. So that's what I have created. And if you go in SKS, you'll be seeing that in DEFRA1, it is in creating state, and in instance pool, there will be soon an instance pool getting started to create over here as well. And you can see the node pool, Kube-Simplify node pool is getting created, and we already have our SKS cluster, which is in running state. In order to get the Kube-Config file, either you can take it from the UI, you can go to the details, and you can see get Kube-Config, you can see set the validity, user and master, and you can generate that. It will generate a Kube-Config file with the cluster certificate and the user data. Or you can use the CLI too. You can use exo, compute, SKS, Kube-Config, Kube-Simplify, Kube-Admin, and zone and group Kube-Simplify.Kube-Config. So if I do export Kube-Config equal to this kubectl get nodes, and we can see the nodes have started to come up, and some of them have already become ready, and all the nodes are in ready state now. This is the clean, plain Kubernetes cluster we have created an SKS, which is managed by Exoscale. These are the default pods that are in initializing or creating. So basically, you have a Calico controller and Calico pods on all the nodes. You have CoreDNS deployment, which is there. You have Kube-Proxy as a DaemonSet, which is there. You have connectivity agents. You have metric server. So these are the default pods that are created by Exoscale for the SKS. And you can see just in a matter of a few minutes, we are able to spin up a production grade Kubernetes cluster on Exoscale. So that's the power I wanted to show you, and a huge thanks to Exoscale again. Do check out Exoscale, and the links are in the description of the video. So again, thanks to Exoscale for partnering with Kube-Simplify on this particular video. And we'll continue with the course and deploy our application on this cluster that we just created. So let's keep going. Now, once you create the Kubernetes cluster, one of the things obviously you need to interact with the Kubernetes cluster, and you need to create the Kubernetes objects. You need to create the files, the deployments, the pods, whatever stuff is required for your application to run. So in our application, there is a lot of things that we need to deploy onto the Kubernetes cluster. So YAML is YAML and markup language. What it means and why do we care and why it is important to learn is because all the manifest, all the files which are written is in the YAML specification, YAML format, and in the whole DevOps ecosystem, whether it's Docker, whether it's Kubernetes, whether it's any of the DevOps ecosystem, the communication is mainly through the YAML files. So it is important to kind of understand what it is, so you can easily write those YAML files. By the way, no one likes to write the YAML files. Anyways, YAML files are human readable. So basically, these are the human readable. That's why they are so popular. That's why they are so widely used. So they are actually human readable in the terms of syntax. It's a data serialization language. There are other serialization languages as well, like XML, JSON, but these are not very human friendly or very much readable. They are used just fine. Like the DevOps ecosystem is not very developer heavy ecosystem, so which is why the human readable format was widely adopted and accepted. So how do you write YAML? So let's get right into it. So there are 3-4 things mainly which are there. One is the key value pairs, one is list, one is objects, and one is the pipe symbol or multi-line strings. So let's say, take this example. So you have name Sayyam. So this is key, this is value. So my name is Sayyam. So basically my properties, it is my properties. And this indentation. So indentation is very important when you are writing YAML file. Profession, founder of Kube-Simplify. What are my skills? Now I can have multiple skills. So which is why this is a list. So my skills is a list. How do you write So you have given one space over here and then one hyphen symbol, and then you write Kubernetes, Docker, GitOps. So that's how you write the list. If you have to check, if you have to check the YAML specification, there is a site called YAML lint. So YAML lint, you can paste this and you can check. So it's a valid YAML. Let's move on and see a nested YAML, like a bit more complex. So this is a nested YAML because here name is Sayyam. So name is Sayyam, but address, the key is address, but the value is nested key value. So the value is nested key value because my address will be having more details, like it will be having a street, city, zip code. And let's move on even further. Let's say there are multiple addresses. So I live basically at 2 locations. Then you can have that as list of objects. So this is a list of objects because address can be a list. There are multiple lists. Let's try to understand it from a real example. So this we'll just cover after this particular section, like what API version means, what kind means, what this spec means. But this is a pod specification. Pod is a Kubernetes object. So pod is a Kubernetes object that runs your application. This is the one that actually runs your application. I mean, inside that there is container, inside that there is CRI that actually runs the container and stuff. But yeah, you can say that pod encapsulates. So pod encapsulates the containers which are your running application, running instances of your application. So kind is pod over here. So these both are key value. So right now we are focusing on the YAML syntax only. Key value, and then you have metadata, which is the object. So metadata is the object, and this object also has a key and a value. Now spec is an object. Containers are list of objects because one pod can have multiple containers. So that is why container is list of objects where you have again name, Nginx, image, Nginx latest, ports, again a list. Port is again a list because port can have a container port, it can have a name, all that stuff. So port is something which is there. So pod and its properties is what a YAML file representation is. Now, another thing can be like if sometimes you write a Kubernetes object called ConfigMap to provide the configuration files or specific scenarios. In YAML, you can specify this pipe symbol. So after this pipe symbol, the indentation follows as it is. My config, and then it is storing 2 multi-line values. So start.sh, the startup shell script, and properties file. And we are using the pipe symbol to preserve the line breaks, and the format is exactly as written. So this is useful when you are storing scripts, when you have config files or any block of text inside the config map. So another one in the YAML specification is that you can also have placeholder. So these double braces, the double braces are the placeholder things. So this is the placeholder that can be defined. It can be used for Helm or customized. So usually it is used in that scenario where you have Helm and customize and you are dynamically putting in the values. That is one thing that you can do. Another thing is the variable. So you can also use values, dollar password and things like that. But here, for example, if you export password on your system and then this particular thing is in pod.yaml file and you do the kubectl apply -f, then you will be able to substitute that particular password. So this on a very high level is what YAML specification is. So I hope it gives you a confidence to write a number of YAML files and specifications. Moving on to what you do when you actually create a Kubernetes cluster. So you have created a Kubernetes cluster. So this is your Kubernetes cluster. How do you interact with it? So to interact with it, there is a utility called kubectl. So kubectl is something that you download on your system. So this is your system. This is your computer system. And here you download the kubectl utility. So you download this utility. You then can use this to interact with the Kubernetes cluster. For example, I already have this Kubernetes cluster. So kubectl get nodes. You can see a 2-node cluster. Kubectl get pods, but it has to interact with kubectl. For example, if it has to go, like if it has to interact with the node, so this particular thing is the node, the Kubernetes node, and if it has to interact with the API server of the node, then the first step that API server does is the authentication. Authorization is the second step. So authentication, authorization, and admission. So how it happens? Against what it authorizes? It authorizes against a Kube-Config file. So kubectl config view is the one. This is the Kubernetes configuration file. Let's try to understand in a bit more deep dive way what a Kube-Config file is. A user access the cluster using kubectl and gets authenticated using the Kube-Config file. In the Kube-Config file, you have the API version v1. You have clusters. So clusters here is a list. You can have a list of multiple clusters. And again, context, you can have multiple contexts. So again, it is list of objects, as we just saw when we were learning about YAML. What it is saying is the cluster server, this is the API server IP address. So in the end, all the communication, everything that we are sending, it is going in as JSON, even if we are sending a YAML or if we are doing a command and it is a REST API call to this particular API server address. We are just calling this address and we'll try to do in a more, command line way as well. But right now, this is the server address, certificate authority data. It has a name called Kubernetes. Then comes the context. So context means which user is associated to which cluster. So user Kubernetes admin is associated towards a cluster called Kubernetes, and the context name is this. And what about the user? So users is also a list of users. So these are the credentials. So there is a Kubernetes admin as a user, client certificate data and client key data. So by default, there is a user that automatically gets created. But let me show you how you can actually create a user and do it end to end, like, create a particular user. But before that, also, let's try to understand this API version, this, what all this is actually. So in Kubernetes, again, there are a lot of deployments, there are a lot of pods. We already discussed about this particular specification. Like in Kubernetes, there is the thing called YAML. This is the YAML specification for object called pod. So how do you create a pod? You say API version is v1. So what is this? In Kubernetes, there's two things, two concepts. One is GVK, one is GVR. GVK is group version kind. So group is basically this. So usually, if you go to a store, if you go to a medical store, or if you go to a departmental store, there are items grouped, like there are chocolates, and then there are variety of chocolates. There are biscuits, and then there is a variety of biscuits. Chocolate and biscuit are not there. Similar to that, if there is networking, then the networking, the kind networking and the kind different kinds will be there inside the group networking. Then there's a group called apps. There are different set of groups. Then there is a group called the core group. The core group is basically double quotes, which is why in pod, because pod falls in the core group, that is why there is no slash. Like we don't have anything over here. Like we don't have this over there. You can just omit it because it is empty. It is core group. So core group, pod is part of the core group. So group, you understood here. Deployment, for example, this particular piece is deployment, and in the deployment, this particular thing is the group. Now comes the version. So versions can be different. You can have alpha, you can have beta, alpha 1, and then you can have the GA, V1. So here you have V1, you can have V2, depending on whatever the version is. So right now, here the version is V1. This is the version. So this is called the API version, which API version we are actually using, because based on that, there can be certain fields in the specification that might have changed. So every Kubernetes release, there might be alpha, beta, graduated, these set of features. Based on that, the API version will be different. Based on that, certain features will be different. Now comes the kind. So here the kind is pod, the kind is deployment. So inside the biscuits, there is Biscoff. Inside the tea, there is Red Label. Inside the tea, there is the Taj. So there inside the tea, there is English breakfast tea. So those are the kind of keys that are available in the departmental store. So deployment is one of the kind available in apps. So when you are defining the specification, you put GVK, K, which is the kind. So you use GVK when you are dealing with the structure or the schema of the object. Now comes GVR. Here also the group version remains the same, but the resource is the plural of kind. So for example, if the kind is pod, the resource is pods. If the kind is deployment, resource is deployments. So whenever you are calling the API endpoints, and this is which is being used internally, because when you call the API endpoints, you are directly interacting using the resource over here. So it is used for calling the API endpoints to interact with the objects. Now, what we'll do is let's create a user. Now let's create a user. So we have this kube-config file, kubectl config view. This I already have shown you. Here you have users, but what we are trying to create now is a new user, because what will happen is in enterprises, you won't be distributing the same admin kube-config file to everyone. You will be creating new users, assigning new roles and role bindings, like what actions this user can take on this particular cluster, and then you will be distributing that kube-config files. So let's try to create and replicate the entire scenario of creating a new user. So first we'll create and generate a new certificate for the user. This is the general Linux command, OpenSSL generate. This command creates a 2048-bit RSA private key for the user SIEM. Next is generating a CSR. So CSR is to be created now, certificate signing request. Again, OpenSSL request new, and key, we are passing the key and generating the CSR here. CN is the username and O defines the group that can be later used in RBAC. But next step is to embed into a CSR object, because we need to create a CSR object. For that, we need to base64 encode it. So this is what we'll encode. I'll just copy this VI CSR. I already have a sample CSR, so I'll just remove this and put this. And this you should be now getting a gist of what it is. API version is the version from the GVR. Kind is the resource. Here it is certificate signing request. Metadata is also one of the object in the YAML specification. We learned that while we are learning YAML. Spec is the object where we are passing the request as the base64 encoding CSR, and the signer name is Kubernetes.io Kube API server client. Usages is client auth. So basically this is a Kubernetes object certificate signing request that we are passing to Kubernetes. So kubectl apply -f CSR we have created. Now we need to approve this. And for that, we can use again kubectl. We need to approve this using kubectl certificate approve SIEM. So we have approved this request. Now we need to get the signed certificate. For that, get CSR -o JSON path, get the certificate and store it as SIEM CRT. Now we need to create a role and the role binding for this user, like what actions this particular user can take. For that, we are creating a role and the role binding. So again, role and role binding are Kubernetes objects. So this is the resource. So kind is role. So it is the kind, GVK. So kind is the resource, API version is RBAC, authorization K8s-V1, metadata, namespace, in which namespace you want it, and in what is the name. Rules are very interesting, because now here we'll apply that what all things it has access to. What we are trying to say is it has access to get, watch, and list the pods. Apart from that, it has no other access. Once we create this, we also need to create binding to bind SIEM user with this role. So you can see here in the subject. So that object is called role binding. And how to bind it is in the subjects we mentioned kind user should be bind with the role reference of pod reader. kubectl apply -f role. So the role and the role binding is also created. Now we need to configure kubectl to use this new user. So for that, we use this command kubectl config set credentials, and we give the client certificate and the client key. And now we create a new context. So kubectl config set context and give the context name, cluster name, and the user name. Now if we do kubectl config get context, we'll be able to see two contexts. Now, if we do kubectl config use context, we have now switched to SIEM context. So if we do kubectl get pods, there are no pods, which is fine, but at least the request is passing. But if I do kubectl get deploy, well, it's forbidden. And we wanted that because the rule that we gave is only the list watch get of pods in the default namespace. Even if we do kubectl get pods -a, it won't give because it only can list the default namespace pods. Now, another thing that we can do is, I'll show you the GVK. So the GVK, I told you, it's for the resources, and the resource is the plural, and it is used to call the API endpoints. So let's now try to interact with the Kubernetes API. How you can do that is, we'll create something which is called a service account. So in Kubernetes, there is a concept of service account, which is a machine identity. It's basically built-in identities in Kubernetes, managed by Kubernetes itself, and are used when we need to talk to the Kubernetes API. So when we need to talk with Kubernetes API, we create these users. So first, let's create deployment JSON. So what I'm doing here is kubectl create deployment nginx image nginx, and I'm not creating it, but I'm doing a dry run of that and outputting it as JSON. So in order, if you want to create a JSON from imperative way, you can do that. If you want a YAML instead of -o JSON, you can do -o YAML. It will create a YAML manifest. If you want to see that, I'll just display it on the screen. I just type YAML. It will create a YAML file for that. Okay, we have the JSON. Let's simulate the API interaction with a service account. So first we are creating, oh, it's not there because I haven't switched back to the context. So kubectl config use context Kubernetes admin, create service account in the namespace SAM. Now we create a role binding. So it is saying kubectl create cluster role binding. So we created role and role binding. There are two more, cluster role and cluster role binding. Instead of creating them using YAML files, I am using imperative way. So imperative way is kubectl create cluster role binding, name of the cluster role binding, and the cluster role, which is cluster admin. So we haven't created a cluster role because cluster admin role is automatically created by Kubernetes when you have the Kubernetes cluster. And the service account name that we want to attach is the default SAM that we just created. So it is a admin user. Now, in order to interact, we need a token. In order to interact with the API server, we need a token. Now, this token is something that we'll be using. So let's export that token token and put this. Now let's get the API server address. For that, we are using kubectl config view minify. You can just use the kubectl config view and get this and export it as the API server address. But now let's do the interaction. So you can see currently there are no deployments, but the API is successful. So how I did it, curl get API server address. And now I do APIs group version namespaces, the namespace, and deployments. So this is the GVR deployments. And if you have to do pods, it's basically API server, API, v1 namespaces, and pods. But anyways, now we'll do the deployment. Now let's create the deployment. And if we have to create, obviously the request is post request, not a get request. Post request to again APIs, apps, v1, namespaces, default deployments. But here we pass the content type application JSON, and in the D we say deployment.json. It creates. Now if I do the deployments and if I get, we'll be seeing in the item list is not empty anymore. So this walkthrough shows you how Kubernetes handles authentication, authorization, and direct API interaction using both user certificates and service accounts. Now we need to deploy our application. That is clear. The main goal is to deploy the application. But before deploying the application, it is important to understand some constructs of Kubernetes itself, what happens when you actually run a pod and how the whole life cycle works. So first things first, whenever you interact with Kubernetes, you use something which is called kubectl. Kubectl is a command line utility that's installed on your local machine. So on your local system, you'll install kubectl. So like I already have kubectl, so this is kubectl, and there are a lot of commands that you can run with kubectl. And if I want to get the nodes of a particular cluster, in this particular case, I have it. What happens is kubectl gets nodes. The request first is authenticated, then authorized, and then it is giving us some information. Now, how that happens or how anything happens in Kubernetes and how does it goes and talk to the Kubernetes cluster and get back the info. So let's try to understand the architecture and components of Kubernetes. So this is what many people refer to as a Kubernetes architecture. So everything in Kubernetes is running inside virtual machines or bare metal infrastructure. So you have either a VM or you are having a bare metal instance. So you can have a VM or you can have bare metal. On that layer, you will be having Kubernetes installed, or you will be using a managed Kubernetes service like Exoscale. Then you will download, or if it is generated using KubeADM, if a cluster is created using KubeADM, you will be getting a kubeconfig file automatically. It generates that and places it into a particular directory. And if you are using a managed Kubernetes service, it will give you a kubeconfig file. It will give you a kubeconfig file. And then in order for kubectl to run, you need to have a kubeconfig file. Now, by default, it reads the home.kube directory and use the config file, but you can also export kubeconfig variable. If that is exported, then also it will know which Kubernetes cluster, etc. it needs to interact with, what is the user and all that stuff, because kubeconfig file has all the information. And we'll obviously go through the kubeconfig file in detail and create a new user as well. So now let's say you already have a kubeconfig file and you are trying to run a workload. This particular command means I want to run a pod, kubectl run. This is the pod name and this is the nginx. So let's try to understand the life cycle of it, like how the entire process works, how every component within Kubernetes interacts with each other. So this is a virtual machine or a bare metal instance, and this is the control plane node, means this is acting as a control plane node, and control plane node has certain number of components, like it has an API server, scheduler, controller manager, etcd, cloud controller manager, and then you have the worker node that is having kubelet, Kube-Proxy, and your pods that is actually running your containers. It has container D, and there is also CNI, which is part of the architecture. So first, everything, all the communication, everything that happens, either you use kubectl or you use curl commands, or however you want to interact with the Kubernetes cluster, you can use that. You just need kubeconfig file that will be having the cluster information where it has to go and interact with. The request first goes to the API server. API server kind of is where every request comes in, and it performs three things, which is called the AAA: authentication, authorization, and admission. So first, the user is authenticated with the headers passed. So let's say you are entering a building. So and you need to enter a building, you have ID card, right? So that is your authentication mechanism. Now authorization. Now you are entered the main building using your card, but now there are specific buildings for each company. Like you have Microsoft, you have Google, different companies which are there. Now, which building are you an authorized user to enter that particular building? In Kubernetes, the authorization is mainly used using RBAC, role-based access control. Like, is this particular user authorized to create a pod in default namespace? So, is this particular user authorized to create the pod in the default namespace? And then you have webhooks to validate or mutate, and then it saves to etcd. So when you have webhooks or you have admission controller in image policy webhook or different type of webhooks, or you can even have Caverno. So it can validate certain information that only process the request if it has certain request resources defined in the pod spec, or if the request comes in, then mutate certain amount of labels, some labels to it. So that comes under the admission. So first, the request comes in, goes to the API server, the authentication, authorization, and admission phase passes these three phases, and the request is then stored into etcd. The next component that comes into play is the scheduler. As soon as the request comes in, the scheduler checks for a lot of things. So on a particular pod, there can be certain fields that we kind of provide, like there can be taints, there can be toleration. We'll go through that. There can be affinity, there can be a node selector already present, there can be a node name already present. So all these things are there, on the basis of which scheduler tries to check whether there is a node selector, there's a node preference, whether there's a node affinity, that this particular workload should go to a GPU node, or this particular should go to a node with specific labels, something like that. It checks, and also whether this particular node is able to accommodate the request. Like maybe I have a 1 gig or 500 MB of resource request that I have done while creating the pod, whether one of the nodes is able to meet that request. Once it finds the node, it updates the API server and updates the field of node name. The request is saved to etcd. Now, what is etcd? Etcd is just a simple key value store for distributed systems. It is acts as a database for the state management of the Kubernetes cluster. API server writes to it. And in HA mode, there are three etcd, where one is leader. It follows the raft algorithm and the leader election protocols, which is like 2n plus 1. And the state of the cluster is very important. So time there should be a etcd backup that you can take and store to the S3 bucket and then restore from that, And there are several other mechanisms as well, but it's the most simplest one. Like you have a cron job and you do the etcd snapshot and then you save it to a S3 bucket. Okay. Now this is the worker node. Now worker node is basically the node where your workload will actually run. And here what happens is you have the main component, the main request comes to kubelet. Now kubelet talks to three things. So you have to take care of these three things. You have to understand these three things in detail. And I will actually explain all these three things in detail. So you have a CRI, you have a CNI, you have a CSI. So kubelet, what happens is kubelet talks to CRI that, hey, there is a pod that I need to run with Nginx image. Now CRI will do its magic and get the pod in the running state. CNI is a special networking plugin that is installed on the Kubernetes cluster while we create the cluster, which I have already shown when we created a self-managed Kubernetes cluster. That networking by default is not a part of Kubernetes, and you have to attach a particular plugin to it. For example, Flannel, Calico, Cilium, and so on and so forth. It attaches the network to that, gives it a IP address and the other fancy things. And then comes the CSI whenever there is something related to storage that has to be done. So for that, you have your CSI drivers. Now, two important components over here. Like we'll just immediately after this, we'll do the deep dive of all of this. So then next component on the worker node is Kube-Proxy. Kube-Proxy maintains the network rules on the nodes. These network rules allows communication to your pod from network sessions inside or outside of the cluster. Basically, it is managing your IP tables, NF tables, or IPVS, whichever mode the Kube-Proxy is running in. So basically, in short, whenever a pod is created, the IP tables is handled by Kube-Proxy. Now, what happened to our request? So basically, kubectl run nginx -image nginx API server. Scheduler said it will be running on this particular node, and then it is saved in etcd. Request goes to kubelet. Kubelet says, I want to run the nginx pod. CRI runs the pod. CNI attaches the network interface, ETH0, ETH pairs, and all that stuff, networking magic over here that happens using one of the networking plugins, for example, Flannel, Calico, or Cilium. And then the pod is running with one or multiple containers. Since here it is only one container in Nginx, so it will be this particular pod that is running. As soon as the pod is running, so the Kube-Proxy will also update the IP tables or NF tables or IPVS based on whatever the configuration it is started with. And your pod is now in running state, which will also be updated in etcd that your state of the pod is in running condition now. Now there are two more components in the control plane node. One is the CCM and one is CM. So controller manager makes sure that the actual state and the desired state of your cluster is matched. For example, if you say that I want to run deployment in Nginx with 3 replicas. So it will be the responsibility of the controller manager to make sure that there are 3 replicas of Nginx pod always running. And there are a lot of the controllers over here. There's a DaemonSet controller that makes sure that one copy of the DaemonSet is running on all the nodes. Even if there is a new node that comes up, DaemonSet controller will deploy additional pod of the object DaemonSet on that particular node. If it's a statefulSet, then statefulSet controller is there. There's job controller, deployment, replica set. A lot of controllers are there. So controller manager is kind of the loop that is checked. So it's a watcher. So it keeps watching for the objects which we create and make sure the desired state is always matching the actual state. And one additional component that is specific to a cloud provider is CCM, because when you create something like load balancer, so it has to communicate with the cloud provider and then return you the load balancer IP. So for that, there are additional things that can be done using the cloud controller manager, that is cloud specific thing. So this is in short the Kubernetes architecture or how a pod works. So I hope that particular portion is clear. Now let's try to understand CRI, CNI, CSI, Kube-Proxy, CoreDNS in detail, because they are also kind of critical to Kubernetes itself. Let's talk about CRI. CRI is the container runtime interface. And I told you, right, that from the kubelet, the request goes to the Docker shim. That was the case before, but now it goes to container D and then it goes to run C, and run C is the one that actually runs the container. So let me explain you how stuff works. So you have your kubelet. The request goes to container D. This is the CRI implementation. So container D is one of the implementations of CRI. And then the request goes to container D shim. And then it goes to run C, which is the low level container runtime. So this is the low level container runtime. This is the thing that actually do the Linux namespaces and starts the container and then exits. So this is a short-lived process. And then container D shim updates back the status to container D. So that's how it works. But what is this CRI initiative, how it came? So a long time back when Docker was started, what happened was Kubernetes was having Docker inside the Kubernetes code base, but that could not work for a very long time, because as there is a container runtime, there were a lot of other ideas that were floating around, which were trying to make it more lightweight and with other set of features, with more security, less security, more lightweights and things like that. So there was Rocket and people were developing other things. Now this tied up to every Kubernetes release. Any feature from the container runtime would be tied to the release of Kubernetes itself. So which was becoming difficult, and also the code base of Kubernetes was becoming heavy, which is where in I think in Kubernetes 1.2 core, Docker was deprecated, although Mirantis still have that Docker D shim, which is being maintained by them. But in the end, what happens is there is now container D, which is kind of the industry standard that is being used. But there are a lot of other as well, like gvisor, Firecracker, Cryo, and this comes under container runtime. But what even container runtime also comes under another initiative called the Open Container Initiative. And actually, this initiative was started by a lot of companies, and Docker itself was one of the big contributors and creators of the Open Container Initiative. So Open Container Initiative was started, In that, there were two things. One was the container runtime and one was the container registry. So they specified the OCI spec, which is their specification. So they gave the specification for the runtime, how the container runtime should be, like how it should start, how it should stop, how we should delete the container and stuff like that. And same for the container registry, how the image spec would look like and all that stuff, and how it would be pushed or pulled to the registry. So that is the open container initiative. In that there is runtime, in that there is CRI, container runtime interface, and then there is the implementation of these interfaces called container gvisor, firecracker, and so on and so forth. So you can see here CRI was developed, kind of coined in 2016 December. CRI is basically responsible for pod container lifecycle, image management, status, and container interaction, exec, logs, attach, all that stuff. So that's how the CRI would work. When the request comes to kubelet, it goes to container D, then it goes to the container, like via the CRI API, it goes to the container D, and then it goes to container D shim, and then once he starts the container and creates the namespaces. So with container D, there are two tools, or there are different set of tools that you can interact with. Like there is a CTR tool, there is nerdctl, there is CRI-CTL. These are just the command line utilities. So like, for example, I told you kubectl is used for authenticating with Kubernetes. CRI-CTL is used to interact with the CRI container D. CTR uses the direct container D API to interact with container D. So that's how you can use some of these tooling for troubleshooting and debugging purposes. So you have container D, you have a container D daemon, and then you have the container D shim. Now shim is very interesting part, because this particular part is something that it can be replaced with a run wazi shim in order to run the WebAssembly workloads as well. So this shim made it possible so that even further customizations can be done, and workloads like WebAssembly can also be run in the same way. So that's what about CRI is. Another small recap: container runtime, kubelet, CRI interface, container D shim, run C starts the container, and you can see over here you have the in the container you have PID, which is the PID namespace, process ID, you have root file system, and this is the MNT space. You have network, which is there, which prepares the each zero network. You have IPC for the process inside container to share memory, inter-process communication. You have UTC, which lets you have its own names, host name in the container. In the container, it's the root user, but on the host, it's a different user. And then you have C groups for the isolation part. You have C groups and layering mechanism, which is there. So Linux namespaces plus C groups for the CPU and memory allocations. Everything is done via the CRI. So once you have the CRI, the request goes to CNI. So now the request goes to CNI, which is the container network interface. Now this is very interesting, and you need to understand how it goes to CNI and what CNI is and how it works in depth. So let's try to understand that in depth. So container network interface. Container network interface, a cloud native computing foundation project, consists of a specification and libraries for writing plugins to configure network interfaces in the Linux containers, along with the number of supported plugins. CNI concerns itself only with the network connectivity of the container and removing the allocated resources when the container is deleted. Because of this focus, CNI has a wide range of support, and specification is simple to implement. So what it does? Overall, these are the things that CNI does. Assign IP address to the pod. So pod gets his IP address from CNI. Setting up the vEth pairs between the host. So what happens is, CNI is responsible for setting up the virtual Ethernet pairs between the pod and the host. I'll show you that in the diagrammatical form so that it's more clear on your head. Connecting pod to the cluster network, often using the bridge network, ensuring routing and connectivity between the pods. So that's how it actually works. So if you say create a deployment with 3 replicas, pods are scheduled, pods are being run. What CNI does is assigns the pod IPs. So you have the pod IPs. Every pod gets its own ETH0 Ethernet, and they are connected with the bridge network inside. And then CoreDNS watches, and also you create the service, and then CoreDNS watches for the service and updates the DNS. Kube-Proxy programs the IP tables. We'll actually go to CoreDNS and Kube-Proxy in detail too, but I just wanted to give you a high level what happens. Now let's see that in deep dive. So this is a node. This is a node which is a VL. Now, whenever you created a pod, the pod that we created, remember kubectl run nginx -- image nginx. So we created this. It came to the node, kubelet created, called the CRI. CRI did everything and made the pod in running state. Now the pod is in running state, but it is yet to get the IP address. What happens? Let's see. So the CNI is responsible for creating the network namespace. So the network namespace, which is the netNS for the pod, is created by the CNI. So on the machine, on this particular machine, the node, it creates a new network namespace. It also creates a virtual Ethernet pair. How it does is, this is the pod. Okay, this is the pod which is there. It creates ETH0. This ETH0 is there, and then it also assigns the IP address from a range of CIDR. CIDR is the range that you provide, and it assigns the IP address via the CNI IPAM. So it assigns the IP address. So one end inside the pod namespace. So this is the pod namespace, which is Ethernet. This is inside the pod network namespace. One end is in the root namespace, virtual Ethernet pair, and this is the connectivity. This is the connectivity. So, and this is dependent on the CNI. Obviously, it can be named vEth or Kali or whatever that is. So one end is in the host namespace. So I'll show you that. I log into the node. We can see the vEthernet pair. I log into the pod exec into the pod, and we'll be able to see the ETH0 pair. This is connected, and now connects the host side vEth to the cluster using a bridge, CNI, or the overlay. How it happens is, let's see this. So you can see, after you create a pod. So I created a pod and I came to the host. I did IP link show. It is showing me the loopback address, the Ethernet over here, flannel over here, the CNI, which is the bridge, and then it is showing this vEth pair. Now this vEth pair is connected to, linked to network namespace, this one. I do IP list, IP net NS list. I do IP net NS list, and I see that there is this particular network namespace, which is exactly same as this. Now I do IP net NS exec, give the IP net NS and IP link. This gives us a loopback and ETH0 IF9. So this ETH0 is inside the network namespace of the pod. So this is the network namespace of the pod. Inside that, there is a interface which I did using IP link, which is ETH0. So this ETH0 is this one, and this vEth on the host is this one. And you can see the connectivity 9 over here, 9 over here. That is one way. Another way is link netNS this, and this is the network namespace. So like this, you can see how it actually gets created. Also, if I exec into the pod, now if I exec into the pod, and if I do IPA, I'll also be able to see the same thing, because this is directly coming from the namespace. When I exec, it's all, everything, every container is a Linux process, means everything is isolated using the Linux namespaces as I have been stating before. Let's see how inter-node pod communication happens, like how one pod is able to communicate with other pod. So there are two pods over here. One is Nginx. So I created an Nginx pod and a busybox pod. So this is the multi-container pod. Yes, a pod can have multiple containers, and every pod having multiple containers interact on localhost. So this particular pod and this particular pod can reach out to each other using localhost. So they share the same network namespace. They share the same network namespace. And there is this one more container which is very interesting, which I'll just come to. So CNI, what CNI did is it created a ETH0 pair, vEth pair on the root network namespace, and it also created the same for the another node. And then these virtual Ethernet pairs are connected to the CNI bridge. So this is the CNI bridge. This is the CNI bridge. Now this CNI bridge is responsible for communicating. So traffic from A to B, what will happen? Let's see. Traffic packet, which means the packet goes to ETH0, VETH acts as a tunnel and traffic goes to root namespace. So this acts as a tunnel, traffic goes to root namespace. Now it comes to the bridge. Bridge resolves the destination address using the ARC table. So it knows it has the entries in the ARC table. It uses that and goes to the VETH2 namespace, and this is how it reaches the pod 2. That's how the request goes. Now node to node. So to see node to node is again simple. After ETH0, it goes. So you have VETH, this pair is there. Then you have the bridge. Then you have the ETH0 of the node itself, and then ETH0 of the node itself. It is connected to a network. Now here it gets resolved to the node IPs, and then the same process follows. So it comes to ETH0 of another node, then bridge, then ARC table, then goes to the right particular pod. So I told you that there was one pause container over here. Let's try to understand that. Pause container is basically just a sleep container, and the container creates a network namespace, and pause container holds the network namespace. So it is used to hold the network namespace. So whenever we do ls, ns, and the process ID, we'll see 3 namespaces: net, UTC, IPC. They all are held by pause container. So that's the only purpose of pause container. So I hope you got a gist of what happens. We'll now do a demo as well of how it works, how CNI works, like all of the things that I've shown over here. We'll try to do that in action. So I already have a Kubernetes cluster, kubectl get nodes. This is a self-managed Kubernetes cluster on Exoscale. The reason for that is because I need access to the nodes, and I want to show you certain stuff which happens by logging into the nodes and also needing access to some of the core components. So this is Kubernetes 133A, and this is Kubernetes 133B. So you have 133A and 133B. That's part of the cluster. The first step is IP link show, that I want to show you that there's a loopback address, there is ETH0. ETH0 is the interface, the network interface on the virtual machine itself. There is a CNI one which is there, and then there is Flannel. So these are some of the interfaces that gets created, some of the that you can see in the IP link show. What is interesting is I also told you that inside a particular pod. So now you know what a YAML manifest is. So I can at least show you a multi-container pod. So vi multi.yaml, and this is the API version, kind, metadata. The name of the pod is shared namespace. In the spec section, I have specified 2 containers. One is P1 and one is P2. P1 is a busybox container, which is running a command sleep, and one is the Nginx container that will be running the default Nginx daemon command. Now, the thing here is, interestingly, what I told you when I was telling you the networking concept, that when you have a pod can have 1 or more containers. kubectl apply -f multi. Now, what will happen is kubectl get pods. There will be a pod that is getting created with 2 containers, 0 out of 2. This is fine. When I told you the concept that a single pod has only 1 network namespace. So let's see how that works, and the rest everything is processed on the Linux host. So kubectl get pods. If I do a command of -ovide, it gives me a little bit more information. So this particular pod is running on 133B. You can see the IP address, and also the CNI creates network namespace, and the rest of the namespace is created by runc. So let's try to see that in action. Now if I do IP link show, there is one interesting thing that gets added, which is a VETH pair. So that's what I told you, like there will be a Ethernet inside the pod, and then there will be a VETH, and then that will be connected via the tunnel. So VETH is created on the host. So right now, this is, you can see I am on the host, and you can see it is linked to a network namespace. This VETH is linked to a network namespace. This is the network namespace. We can also check that using IP net ns list. So this is the network namespace. So there is a new network namespace that got created, and this is the same as this one. If we go deep dive into that, so IP net ns exec this IP link, we'll be able to see now we are inside the network namespace. Inside the network namespace, there will be a loopback address and there will be a ETH0. This is very important because here it means that inside the container, inside the pod, basically, inside the pod, the network interface is ETH0, and on the host means on the node, on the virtual machine that is connected to the Kubernetes cluster, it's vETH. And you can see the connection over there, IF20. So this is 20 over there. And you can also see that when you are on the host, it already specifies that it is linked to a particular namespace. When you exec into the particular namespace, you'll be able to see that it is connected via the ETH0 from the pod. We can actually exec into the pod. So let's exec it, kubectl exec -id -sh. So this is the command to go inside the pod. Kubectl exec -it means interactive mode, shared namespace, --, then what command I want to execute. Right now, I want to go into a shell. Since I haven't specified any container out of P1 or P2, it defaults me to P1 container. I can go to the P2 container as well. Now I told you that yes, there is a single IP for the pod, but there are two containers. The two containers share the same network namespace. How can I say that? I'll show you that as well. So ls ns grep nginx. So there is this particular namespace. You can see mntpid c group, but let's even further expand it. So ls ns -p. This is one. And now we'll be able to see all the other namespaces, especially the net UTC IPC. And this, interestingly, the network namespace whole is held by the pause container. And now let's see, instead of grep nginx sleep, because that's what our busybox pod was doing. So you can see mntpid and c group of the container. So every container, whenever there is a new container that gets created, I told you when I was discussing the CRI concept. So container creates a set of namespaces. So every container is having a set of namespaces. But since it is contained inside a pod, what will happen is that the pause container will hold the same network namespace. So network namespace will be 1. So let's see that. And now if I do ls ns -p, you can see 4009959 is the PID, 4009959 is the PID for the net, UTC, UTS, and IPC. This shows that there is a single network namespace for the containers, and that's why they are able to communicate with each other over localhost. So if I do localhost port 80, I am able to get welcome to Nginx, because Nginx is running on port 80 of this particular localhost of the pod. That's how the networking kind of works in Kubernetes. Now that we know the concept of CNI and we have seen the demo, we have now seen CRI, we have seen CSI. The next step is CSI. So let's go to CSI. CSI is the container storage interface. CSI is the container storage interface. It went GA in 1.13, Kubernetes 1.13, it went GA. And as of Kubernetes 1.33, almost all the entry cloud providers and the storage drivers are deprecated. So what it basically does, it allows the pods to provision persistent storage. So we'll definitely do Kubernetes volumes where we will study about PV, persistent volume claim, MTDR, and all those stuff. But yeah, you can say if you want storage within your Kubernetes cluster, if you want stateful sets, if you want to persist a state, then you need some sort of storage, and for that CSI is kind of used. It has two things. One is the controller plugin. In the controller plugin, there are three things: provisioner, attacher, snapshotter. And then there is a node plugin that talks to the backend storage and the kubelet to actually mount that into the node and stuff. So attach, detach volumes to the nodes, mounting and unmounting of the volumes on the node, snapshotting, clone, expand volumes, and everything is managed by CSI. So this is the overall standard and the spec that defines how storage plugins work inside Kubernetes. Before CSI, storage vendors build drivers inside Kubernetes. Now, the problem of building inside Kubernetes is that all the new features with respect to a particular driver or a provider was tied to a Kubernetes release. So the features were getting delayed. With CSI, the storage drivers live outside of Kubernetes, and Kubernetes just stopped them over a well-defined gRPC API. So it has two things, the controller plugin and the node plugin. So the controller plugin has three main key things, which is the creating, deleting of the volumes, attaching, detaching them to the nodes, handling of the snapshots. So you have these containers as the sidecar containers, CSI provisioner, CSI attacher, and CSI snapshotter. Snapshotter only works when you have enabled the snapshot, manages the snapshot creation and the deletion. The provisioner watches for the persistent volume claims and then call the create volume. And when we delete, then it calls the delete volume. Attacher is something that actually does create the volume, talks to the driver, and CSI driver then communicates with the backend via the APIs. Then the node plugin is working as a DaemonSet, talks to the kubelet, mounts, unmounts the volume, formats the file system if needed, and reports the disk status. Let's see that in form of like how it works end to end. So a user creates a persistent volume claim. A persistent volume claim is backed by a storage class. A storage class, whenever it is created, it has a well-defined driver. Now, the driver is the one that talks to the cloud, which creates the volume, which creates the actual volume. So, what happens is the CSI provisioner watches the PVC. As soon as it's created, it calls the create volume function. Then it calls the driver. Driver calls the cloud. It creates the actual volume and PV is created on the Kubernetes. Like it says, the volume is ready to use. Volume is ready, volume is created. But it's not yet on the node, not yet attached to the node. When you create a pod, so now user creates a pod. And when the pod is created, CSI attacher, which is again a sidecar container, calls the controller publish volume. Again, it goes to the driver, and now it plugs in the storage to the machine where the pods is to run. So the pod is scheduled on one particular node. This tries to attach that on the same node where the pod is to run, because that's how the next step would work. Next is node plugin. Node plugin talks to the kubelet and it calls the node stage volume, means prepare or mount the block device to the staging path inside the pod. So now on the cloud, it is created, it is on the node where the pod is running, and now node plugin actually mounts that into the pod for specific pod volume path and stuff like that. So that's how the whole CSI kind of stuff works. We'll do it end to end when we walk through the storage stuff. Now, from the Kubernetes architecture point of view, we have understood like how the request goes, kubelet, and then goes to CRI, then CNI, and then CSI, and there are all of these projects that are taking care. There are two more key things here. One is Kube-Proxy, which is we tell part of the worker node, and one is CoreDNS. So let's try to understand Kube-Proxy in a bit more detail. So whenever you create a pod, in order to access, pods are ephemeral in nature. Pods are ephemeral in nature, means whenever there is a pod that dies, it will get a new IP. So you cannot directly communicate with the pod. Whenever someone external or some internal services also, internal pods also wants to communicate with a particular pod, with a particular application, you communicate with a Kubernetes object called services. We'll definitely study services in depth, but right now it's important to understand the role of Kube-Proxy when it comes into the play. So you create a pod, a user creates a pod, a user creates a service, and then there is something that gets created is endpoint slice. Endpoint slice will be having the mapping of like this service has these endpoints that it has to go to. The endpoints are the pod IP addresses. So Kube-Proxy takes that information from the API server and it updates the IP table rules. I mean, it really depends on the Kube-Proxy configuration. So if you have the proxy mode as IP tables, proxy mode as IPVS, or proxy mode as NF tables. So based on the Kube-Proxy configuration file, it generates the IP table rules. So IP tables rules are basically the firewall rules inside the Linux. It's a Linux concept which is there, and it is divided into tables. So that's why it is called as IP tables, because there are 4 types of tables which are there. And then these rules are forwarded. These rules forward traffic coming from the service, whatever the IP is, to the pod IP via DMAT. So we see that in action as well, like how it happens. But right now what happens is user creates a pod, user creates a service, then Kube-Proxy creates rules based on the configuration like IP tables or IPVS or IMF tables, and these are the 4 tables. So these tables, what they do is filter accept or deny requests coming from the packets. NAT, implement network address transmission, modify packet source and destination address. Very important. Mangle, change the IP header of the packet. Raw, mark packets that should not be handled by connection tracking system. So overall, what are the differences? Like IP tables is packet filtering NAT framework using chains. So there will be a chaining system which we'll see in action as well. It is a modern replacement, NF tables, for the IP tables with better performance. So NF tables are the modern replacement for IP tables with better performance, simpler syntax. IPVS is actually layer 4 load balancer. So we say, for example, there are 3 pods, 1, 2, 3, and then you have a service on top of that. So you call that service. Ideation is that it should automatically route the traffic either to this or to this or to the third one. Now we say that there is load balancing, but there is only one load balancer that is supported, which is the round robin, because that's IP tables, that Linux process, it was not meant for load balancing, but it has multiple algorithms, the IPVS, it has weighted source hashing and stuff like that. And also it is highly performant and it is built into the kernel as part of the IPVS module. So NF tables is the modern equivalent of IP tables, and I think like with Kubernetes 1.33, it's already like something you can use very easily. IPVS is something kernel based, that's a much more advanced mode and is definitely used in production as well. And eBPF tech is also there. So here CLI is the IP tables, here the CLI is NFT, it is configured directly, no general purpose CLI. This is the default or older mode, the IP tables, and this is supported and is actually matured, the NF tables, and this is the advanced mode for bigger performances. So that's how it works. When you see a particular chain, so this is one particular chain where you have a target chain. So this is your target chain. So what it means is, if there is any incoming TCP packet going to the IP address of the service, so this is the service IP address on a particular port, then send it to this particular chain. Now this chain, when we expand this chain, knows which pod it has to send the traffic. So you can see I now go into this particular chain, and what I see is it has the target and it has the pod address. So this is the pod address where it has to send the traffic to. So you have to send the traffic to this. If we again further see this particular chain, we'll be able to see that the traffic is actually denatted to the destination. That's how Kube-Proxy works. Let's try to see that in action. So first, let's see the pods. You can see the Kube-Proxy pods which are there. Now let's see the IP tables and the line numbers and stuff. So the command is sudo IP tables -t nat. So this is the table nat. L is the list rules, kube services, and then the line numbers. So these are the list of stuff which is already present. You can see there's a default Kubernetes service and whatnot. Now let's create a service. Let's create a service. So we already have one pod, right? Kubectl get pods that we created, which is this. And if we want to see the labels for that, -- show labels. It doesn't have any label. So let's label it kubectl pod label with app shared. Now I already have a service API version v1 kind service, and it is selecting on the basis of the selector. So it is saying select all the pods with app shared. So it should be able to select this particular pod, add it to the service, add it to the endpoint. As soon as the service is added, Kube-Proxy will create those IP table rules on all the, because it's running at the DaemonSet, so it will create on all the nodes. So kubectl apply -f svc, kubectl get svc, kubectl get endpoint slice. You can see the shared service got the IP address. And if I do kubectl get pods, you can see -o wide. So you'll be able to see 19 is what that is added as the destination. So this is on a very high level that it gives. Let's see from the chaining perspective what happens. So we have the chain number 1, kube services. Let's see if there was a new service added. I can see a shared service. So this is a chain that is added. So it will go to this particular chain. Now we can also grep by the IP of the service. For example, this is the service IP. And you can see I directly get the chain. But anyways, since the number of IP table rules are very less, so it's easier. If not, then you can directly grab by the service name, service IP address. Now see the rules inside the specific chains. So let's do that. And again, the command is almost same, but we are now going, instead of L as kube services, we are defining a specific chain. So let's copy the chain from here. Now we are inside that chain. So how the steps are working, we have gone through kube services, then the kube SVC chain. So this was the SVC chain. Now we'll go into the, we are into the SVC chain and we see a pod chain. So we'll now go inside the pod chain. So let's now go inside that. And as soon as we go inside the pod chain, we'll be able to see that here is what, which is there, that default shared services, traffic is the mode TCP, traffic is getting denatted to the destination 10. 244.219 port 80 kubectl get for -o wide. That should be the IP address where it is going, 10.244.219. That's what Kube-Proxy is, and that's what Kube-Proxy does, the magic of IP tables. Let's move to the last section, which is CoreDNS. Very short one, but still very critical for service discovery. So it is basically a service discovery mechanism. CoreDNS is a DNS server, as mentioned in the name itself. It is written in Go. It can be used in a multi-node environment because of its flexibility. It is a flexible and extensible DNS server used by Kubernetes Cluster to resolve the service names. So let's say one service wants to communicate with another service by the name. How do you do that? So whenever a pod tries to go to myservice.default.svt.cluster.local. So what happens is the request first goes to the CoreDNS pod. So there is a CoreDNS pod which is there inside the cluster. You can see there is in the next pod, in the next service that gets created. CoreDNS is listening on a particular service and port 53. The request goes here. It checks the configuration file, which is this particular configuration file, which is that etc core DNS core file. And it checks for the plugins and then resolves the name. And then responds with the cluster IP of the my service. And when it does that, then you have the IP table rules and stuff like that. The two things are main. It has one, the core file. This is what the core file looks like, and the plugin. So you can see it is 53. We have Kubernetes that talks to the kids, API to resolve the names. You have forwards the unresolved name to the external DNS. Cache speeds up the memory. You have Prometheus to expose the metrics. So all that stuff is present over there. So when we say my service, it searches in the pod namespace. And we say my service default, it searches in the default namespace. And if we can also give the fully qualified domain name as myservice.default.svc.cluster.local, we can actually see that kubectl get pods -n kube system, kubectl get deploy -n kube system. So we'll be able to see that CoreDNS is a deployment which is present on the node. This is the config map, kube system. In the kube system namespace, there is a CoreDNS config map. You can see all the plugins and stuff which is present over there. Kubectl get svc-a. We'll be able to see the KubeDNS service on port 53 that it is listening to. Now let's create a pod, a very simple pod via nginx.yaml. So pod, nginx, container, and then with the service. kubectl apply -f nginx. kubectl get pods. It's container creating. kubectl get svc. We have an nginx service. Now we can actually do kubectl run a busybox container and go inside the shell and do the ns lookup for that. And we can do the exit and see kubectl get svc. The IP address is 10.108.31.55, and you can see the IP address that has been resolved perfectly. So that's how one pod, if like you can directly call from the service name. Now this one directly called inside the pod's namespace, but we can do the fully qualified domain space like domain name as nginx service default svc cluster.local, and it gives you the address of 10.108.31.55. So that's what CoreDNS does. So that's the whole overall architecture of Kubernetes. Now you can say that you fully understand the Kubernetes architecture, which is the API server, scheduler, controller manager, cloud controller manager, and then here you have the kubelet, Kube-Proxy, and then how CoreDNS works, how all the three key things which are written in very short over here, CRI, CNI, CSI works in depth. So now you know the whole Kubernetes architecture. We have already gone through the concept of how to create a user, get it signed by Kubernetes, creating the certificates, the cert, and then creating a new Kube-Config file and see how the first level of authentication happens for a user. Let's try to dive a bit more into the 3 A's of Kubernetes: authentication, authorization, and admission. So whenever a request comes in, the first phase is always the authentication, and this happens as a credential check. So authentication, there are a lot of plugins for authentication. It can be the client cert tokens like the kubectl, kubelet, how they communicate, static token files, the bootstrap tokens, which are the long-lived static tokens, OpenID Connect for the cloud IAM kind of integrations, and the webhook for external auth service, anonymous auth where the auth is disabled, and service account tokens as well, where how you communicate with the Kubernetes API server from within the pods. So these are some of the authentication plugins. So there is a regular user which is managed by the external user management system. So in Kubernetes, you cannot create external users. That if you create, that has to be managed by external user management system. For Kubernetes, that is managed by Kubernetes, there is something which is called a service account. So in Kubernetes, the type of user that it creates for the applications or pods to communicate within the cluster is the service account. So as a service account, you can generate a token, which is then stored as a secret, which is then used for authentication. Once the authentication check is passed, it is moved to authorization stage, and there is some level of information that is passed on, like user info, username, UID, group, field, all these things are added. So the next page is the authorization page. It checks if the user is allowed to perform the requested operation. And here the most common thing that is used is RBAC, role-based access control. The last step is the admission. So policy check by the admission controller. Let's try to look it from another angle. So a user, say I want to create a pod, request goes to Kubernetes API server. First question that Kubernetes API server asks is, in the authentication phase, who are you and how should I authenticate you? So they provide with either a service account, a client certificate, bearer token, OIDC, webhook auth. So any of these plugins, and then it authenticates and say, okay, you are good to go. Go to the next step. But the next question before they go, Kubernetes API server asks, are you allowed to do this operation? And this is checked using RBAC. And the next stage is Kubernetes sees if there is any policy to be checked against. There can be two types of policy, validation or mutation. So validating policies or mutating policies. Validate means the request, like, enforcing some type of policy like limit ranges, ensuring there is resource and limit are set. Only then you accept the request. And mutating means if we want to add things like sidecars or labels and stuff like that. So that's the whole point of the 3 A's of Kubernetes: authentication, authorization, admission. Let's try to see that in action as well, how it works. So let's try to create a cluster role to create a deployment and a daemon set. So we'll be creating a cluster role to create a deployment and a daemon set. Only these two. So let's see how we can create it. And let's try to do that inside a particular namespace, or we can just do it otherwise as well. But before that, I want to just explain you two more things, which is that there is a concept of role binding, cluster role binding in RBAC. Now, role and role binding are namespace scoped, and cluster role and cluster role binding are cluster scoped. That's the only difference. You can create a role binding, cluster role binding, or a cluster role and a role binding as well. So in this particular case, first let's try to create a namespace. kubectl create namespace app, and kubectl create service accounts. That's the command to create service account, demo service account -n app. So kubectl get service account -n app. You can see that there was by default, there is a service account that gets created for every namespace that you create. And this is the one that you have created. Prior to 1.24, there would have been some secrets over here, but post 1.24, there are no by default secrets, and you have to create those secrets. In order to create those secrets, you need to run the command kubectl create token demo sa-n app. So that's how you usually create a token. Anyways, moving on. Now it's the time to create the cluster role. And the command is simple: kubectl create cluster role my rules. That's the name of my cluster role. Verb is something what you can do. So you can create on what resource, deployment dot apps, dry run client. So vi my rules. So we'll be able to see API groups, apps, resources. We actually need to do that on daemon sets as well. So we'll add that here, and verb is only create. So kubectl apply -f my rules, and the cluster role is created. Now the role is created. The cluster role is created, a service account is created. We have to bind them together. So for that, what we do is we can use a command kubectl create cluster role binding, name of the cluster role binding, name of my cluster role, my rules, and the service account. So service account will be app and the namespace. Now it has binded that particular service account. Now let's see. In order to check, what we can do is we can use a command called kubectl auth. Can I create a deployment as system service account name space name of the service account and the namespace. And it says yes, because it can create deployment, it can create a daemon set, but let's see if it can perform any other operation. Can it delete a deployment? No. Can it get the pod? No. Let's try by creating the resources actually. So kubectl run a pod. It is not able to run the pod. It is forbidden because we cannot create a pod. So the pod has failed. Now let's try to create a deployment. Kubectl create deployment with Nginx image replicas 2 in the namespace app as the service account, and it is able to create the deployment. So our cluster role binding is working. Now let's try to do another scenario, which is this one. Give a service account demo2 SA. So that should be the name of the service account. In the namespace dev1 permission to create deployments only in that namespace, and then use its token to perform the API calls. This is exactly the same thing that we did before as well. So we can do kubectl create namespace and then the service account, then create a role, this time it's a role and the role binding, which is why we have to specify the namespace, So let's run all these commands and they are created. Now let's do the auth can for this. And yes, it should be able to create the deployment. Now I told you can get a token. So kubectl create token, and if I do a echo $token, it should have the token for that particular service account. And the next step is actually to get the API server address. We actually saw that when we were using the kubectl kubeconfig portion as well. We saw how to get it. Kubectl config view minify JSON path. And this is the curl request. So it's 403 forbidden, because here what we are trying to do is we are trying to create a secret. Secret creation is not valid operation. It can only create a deployment. It can only create this particular deployment. So let's try to create a deployment. And kubectl get deploy -n. You can see the deployment got created from the service account. That's what we needed. So curl request API server APIs app v1 namespace, the resource deployments, bearer token, and then we pass the whole deployment JSON specification. So there are some other files as well, like if you want to see how a service account looks like as a YAML file. So this is how a service account looks like, a YAML file. If you want to see a role in a YAML specification, this is how a role looks like. So this is a role. API version is RBAC, authorization gates, IOV1, kind is role. This is on a namespace. So this is applied on the namespace level. API group apps deployment. So this role is that it can create, whosoever has this role can create, delete, get, list, patch, update, watch the deployment resource. So kubectl create -fsa, kubectl create -f role, and cat RB. This is the role binding. So for the service account deployment manager, that was the service account that got created in the namespace default. Refer it to the role, add a role reference of deployment creator. This is the deployment creator that got created, and the API group. So kubectl apply -f RB, and it is created. So we also have some test. Can I create deployments? Can I create secrets? No. So which is perfectly fine. as per our role. And then you have another set of role only for the secrets. So this is the role binding, but let's see the role. This is for the secrets. So kubectl apply -f secrets or role 2 and kubectl apply -f or rb1. And the role binding is having the same service account. Now, if I do kubectl auth, can I create secrets? It's a yes, because I have added that particular role as well. But now if I do for services, it should come out as no. So yeah, that was the concept of Kubernetes role binding, how to do that. One last thing is we have also learned about admission. So in Kubernetes, there is a concept of validating admission policy. So I'll just show you how a validating admission policy looks like. So this is how it looks like. Validating admission policy. In this particular policy, it means that it has to match constraints, resource rules, API groups, version, create and update of deployments. It has to match the expression. So wherever a user is trying to create or update a deployment, what validation? And this is a CL expression. What validation it has to perform? It has to check that the replicas are less than or equal to 5. And the binding should be validation action is denied. So, and it is only applied onto the namespaces where the environment test label is present. So, what we can do is we can first apply this. So, let's add this in a YAML. So, vi admission.yaml. kubectl apply -f admission. You can see validating admission policy is created, validating admission policy binding is created. We have to now label it, label our default namespace with environment test, because that's where the policy will be. And now if I try to create a deployment with 6 replicas, it says it is false. The validating admission policy denies it. So that is where the validation step comes in. So the user had the access to the cluster, the authentication passed, the authorization passed, it was able to create the deployment, but admission failed. So it has to go through all 3 to go to the next step: authentication, authorization, admission. So this was all the 3 steps for Kubernetes 3 A's. We are all set to learn about pods now. So in Kubernetes, the smallest unit which is deployable, that is running one or more containers, is pods. So pods are most widely referred to as the smallest deployable unit in Kubernetes, but that's not all what it does. There are a lot of constructs when it comes to pod. Let's try to understand everything in depth. So this is the YAML specification. By now, you know what YAML is, you know what GVR is. So API version v1, it is part of the core group, kind is pod. In the metadata section, we have put some labels, and labels are used to add or group them into service and, do additional logics on top of that. Then in the spec section, which is the most critical one, we define containers. Now, when we learned YAML, we learned that containers are list of objects. So there can be multiple containers. So the first one here is Nginx with the name Nginx, and the port on which it is running is the container port 80. Restart policy is always. So if it kind of fails, it always restarts it. Like kubelet always restart it. So the request comes in, the kubelet talks to the CRI, it pulls the Nginx image and starts the Nginx container. It goes to CNI. CNI attaches the network interface and the pod IP, and the pod runs. So when we do kubectl get pods, the name we get is Nginx. The container name can be different, and this will be the container's name, which is actually kernel. You can interact with the pod, like you can obviously create the pod, you can describe the pod. These are some of the commands. You can see logs of the pod, you can delete the pod, you can exec into the pod if the pod is having a shell. Not every pod has a shell, some of them has, some of them not, depending on which type of base image you are using. And then you can do -o to get the other information as well. So what we'll do is we'll try to understand, we'll try to do a demo, we'll try to understand, we'll try to do a demo. So kubectl get pods. So this gives me pods in the default namespace. We can create a namespace, kubectl create namespace demo. Namespace is basically a logical entity that is created to do basic level of multi-tenancy. So what I mean by that here is that I can have a namespace called demo, I can have a namespace called Sayam, and I can run specific workload in specific namespaces. I can assign specific number of resources in specific number of namespaces. That's the kind of basic use case over there. But yeah, you have a namespace. And if I do kubectl get pods -n demo, if I have to view the pods in a particular namespace, then this is the command to specify -n. If we don't specify -n, then it gives me in the default namespace. So let's run a pod. You can run a pod either in the imperative way or in the declarative way. Imperative way is kubectl run nginx -image is nginx. Or let's do a demo, nginx demo. So the pod is created, kubectl get pods. And you can see the pod is running. Kubectl describe pod nginx demo. So this describes the pod. Describes basically gives you a lot of information and it's good for troubleshooting. Like it gives you the events. The pod is scheduled. Kubelet is pulling the image using the CRI. Image is pulled. Kubelet is trying to start the container. It is container created. And you can also see there is a lot of other information over there, which we also didn't specify, but it actually added, like the node name, and a certain QoS class, download API, and so on and so forth. Okay, so we have run our first pod, which is very good. So I have a few YAML manifests as well. So if we want to do it using YAML, so let's do that. So here API version v1 kind pod, and we have an example pod in the container. Now the pod name is example pod, but the container name is example container. And image is Ubuntu, and the command I'm using is hello, and args is also a list, which is welcome to kubesimplify. So kubectl apply or create. So create is when you are creating for the first time. When you do it for the second time, you apply with only the changes that are there rather than create. Apply -f first. Kubectl get pods. Now if I do kubectl logs, hello, welcome to kubesimplify. Now one interesting thing, kubectl get pods. This will go in crash loop back off. The reason for that is these containers run to completion. The pod run to completion of the containers. Now here we said in Ubuntu, just run this, and after that kubesimplify, welcome to kubesimplify. Now that's it. The pod has completed its work. That's why it just exited and it went. But Kubernetes nature is it kind of restarts the pod because it exited and it restarted. So that is why it is gone into crash loop back off. So you can see kubectl describe pod. And again, it backed off, it successfully pulled, it started again. So it keeps on doing that. And you can see it will say completed, and then it will again restart. It will say completed, and it will say again restart. So we can include a restart policy of never. That's how, things can work out. Like if I do first, and if I do a restart pod restart policy never, kubectl delete -f first, kubectl apply -f first, kubectl get pods. And now let's complete it. It won't restart because our restart policy is done. So the status of the pod will be completed. We'll actually come to the life cycle of the pod. So this is the pod. Let's go to the pod life cycle. So whenever we first created, the pod goes to pending state. Means it is trying to find the node. The scheduler is trying to find the node, or it is waiting for a PV to be attached, which is persistent volume and persistent volume claim, which we will learn when we are going to the section of Kubernetes volumes. Check. Then it went to container creating, we saw that. Then it went to running, we saw that. It can also go to error state. If there is an error, it can go to crash loop back of state. It can go to succeeded, or in case of jobs, and completed as well. We already saw that. There is a init phase as well. When we do the init containers, so it can also go to the init phase. So you will see init 1 out of 0, or 2 out of 1, 0 out of 2, or 1 out of 2, or 0 out of 1, stuff like that. We'll do that when we just below, when we do the init containers. There is another field in the pod that you can specify called spec-os.name, where you can specify Windows or Linux containers, like indicate the OS on which you want the pod to run. In Kubernetes 1.33, the value spec.os.name does not affect how the kube scheduler picks a node for the pod to run on. So if I try to run this particular example, the pod might be scheduled, but the kubelet will reject it. So it will say pod not supported. We can try that. Vi os.yaml and kubectl apply -f os.yaml. Now kubectl get pods. We can see pod is not supported. It was scheduled. kubectl describe pod. We can see that it was scheduled, but again, kubelet rejected that pod because we don't have any Windows operating system support over here. Okay, most widely, now I'll tell you one of the interesting facts. Usually in production, you do not create the pods. You create them as part of the higher level constructs that automatically creates the pod, and in that you do the pod templates. So you usually create deployment, StatefulSet, DaemonSet, jobs, and in those Kubernetes objects, you specify pods as templates. So for example, if we create this job, in the spec section, we defined a template. Now, template will have its own spec section, and that spec section will be same as the spec section over here, like hello, busybox container, and all that stuff. Now, let's try to see what we saw when we described the pod conditions. So, pod conditions have all these. First is pod ready to start containers. This is enabled by default as of Kubernetes 1.33. This means that if it's true, means the pod is scheduled, init containers have completed. The pod sandbox is set up, means the CNI, CRI, the pod whole Linux namespaces have been set up, and the pod is ready to launch the containers, but hasn't necessarily started them yet. Now, initialized means all init containers have completed. Ready means the pod is ready to accept the traffic if you have the readiness or the liveness probes. If you have the startup and the readiness probes. Containers ready, it's ready to accept the traffic. Pod is scheduled true. So all these are different kind of conditions. I already told you about the container restart policy. So you have always automatically restart the container. Never does not automatically restart the container when the container is terminated. On failure, only restarts the container if it exits with an error. Now we are going a bit deep over here, but this restart policy that we have seen over here, right? Cat first. We saw that restart policy over here is never. We can actually delay that. So we can reduce the container restart delay. It is the newest feature in alpha in Kubernetes 1.33 that you have to enable. So you enable that using reduce default crash loop back off delay. So changes the restart timing cluster wide. So it changed the restart timing cluster wide. initial delay seconds is 1 instead of 10, and back off multiplier is 2x, and the max delay is 60 instead of 300. Useful for faster recovery and rapid back off for the critical workloads. There is another feature, but since this changes is cluster wide and you might need some of the nodes, some of the containers, do some different restart policies. That can also be done. So you have configurable crash loop back off. How you can do that is you can configure kubelet crash loop back off max. This was alpha as of 1.32. So it is a node level configuration to override the max restart delay. So override this max restart delay. So crash loop back off, max restart container period is 100 seconds. So you can set that in kubelet configuration. So it still starts at 10 seconds delay unless overridden using this. It doubles each time at 10, 20, 30 up to the configurable max, which is 100. If set to max is less than 10, the initial will be equaling to the max. Now, the point of this is we both use this in conjunction, then it will be more interesting. So if both are enabled, the reduce default crash loop back off sets cluster wide faster retry, and the kubelet crash loop back off max allows per node overrides, which takes the precedence. So if this is there and this takes the precedence, which is why on different nodes, the restart times can be different. So for critical workloads on next particular node can be different. It can follow the same one, but on the other follow the same one, which is this. But on the other nodes, you can specify this. Let's move towards container probes. So whenever you are creating a container, there can be 3 probes that can be created. So for example, you are creating a container, but is your container ready to accept the connections, like ready to handle the request? For example, if there is a login container or a sign up container and your database is not ready, then your requests will fail. We don't want user to do that experience. So we want a container with readiness probe that can check is the database connection ready. And if it's not ready, then it marks the pod as not ready and removes them from the endpoint slice so that the request never goes to that particular container. Liveness container. So this is how you define liveness container. And you have 3 things, like you can specify HTTP GET if the response is okay or not. TCP socket, you can do a port check, or you can use even exec custom command line to check if the pod is ready or not. And kubelet will restart the container when liveness fails. It will be good to prevent deadlock, keep your whole liveness probe, your whole container healthy. If it's not healthy, then it will restart after doing a particular check. Now, startup probe is interesting because it runs at the first, like as the name suggests, it's the starting probe that runs, and it is basically for the SOA applications. It disables readiness and liveness. So first, how the flow will look like. So startup probe will run first, and then so it means that it will run periodically every 10 seconds and for 30 times. Failure threshold is 30, and this will be disabled till then. Once this succeeds, readiness and liveness will start after their initial delay seconds periods, and they will run after the interval of 5 seconds or 10 seconds, whatever the period seconds has been specified. So probes are important because Kubernetes will send traffic even if the pod is not ready to handle it. And if any deadlock situations is there, then still the K8s will keep on sending the traffic, which is where we need liveness probe so that Kubernetes do not check or it restarts the container when the liveness probe fails. But it has to be used with carefulness. Like if all liveness probe fails, your whole container ecosystem might crash for that particular workload. So it has to be used with some auto scaling mechanisms and stuff like that. So startup is the first probe. Wait for the app to fully start, pod kills. Liveness is your app still running, starts after startup plus the initial delay. And app is your app ready to accept the traffic, removed from the service endpoint if the app is not ready. Let's see one example of startup probe. So we have a probe.yaml file. So you can see you have a pod. These are the containers. This is the first. So it will check port 80. If I actually do port 8080, it won't work because container port for Nginx is 80. So we'll first do this kubectl apply -f probe. Kubectl get pods. So probe saying it is running, but it is 0 out of 1. It is not ready. Kubectl describe pod. You can see connection is refused. Startup probe is failing over here. Let's fix that. So kubectl delete -f probe vi, change this back to 80. Kubectl apply, kubectl get pods. Now this will be ready. So kubectl describe pod. It has started. We'll be able to see the probes over here. You can see success, success, success. So let's see. Started. Kubectl get pods. Yes, it's already running 28 seconds ago. It will fail again if I check for the liveness, which is 8080 or whatever that is 880. So kubectl delete -f probe, kubectl apply, kubectl get pods. You can see it is running, right? It is running perfectly fine. But if we have a probe that can check if the application is healthy or not with our specific check, obviously, soon it will do the liveness check. And once the liveness check is failing, it will mark the pod as unhealthy and it will restart. So let's see when the first restarts occur. And you can see 2 seconds ago, it restarted. So this was the concept of Kubernetes probes. Now let's move to what we said initially, that a pod can have one or more containers. Yes, this is absolutely true. A pod can have one or more containers. But why is that even needed, or what patterns it is, or how it works? Let's see that. So and when you have multi-container pod, I showed you in the networking as well, networking part of the section, that it can talk over local host. It has a shared volume because it has the same shared CNS stack and it follows the same life cycle of a single pod. The most common patterns are init containers and sidecar pattern. They both are linked together because sidecar is part of the init container, which I'll explain you just now. Think of init containers as specialized setup specialist for the pods, and they run before the main container. So let's actually understand first the init container. So runs before the main container, runs in a sequential order because there can be multiple init containers too. And app container do not start until all the init containers have finished successfully. It runs to completion. Use cases, let's talk about that because that is very important. So you can use tools without bloating the app. For example, if you need curl, SED or Git for the setup, you can just include them in the init container. It can be used for the setup logic. So you can have some preconditions, some volume checks. You can do if your secrets are loaded, if your databases are there, if your config maps are there, if your files are prepared, if you are waiting for a particular service to be ready. Those can be the precondition checks before you want your main container to be started. So this is the setup logic. Init container can also access secrets and config maps that we do not want our app containers to kind of access. So that can be done, and it can write to a shared volume, and then app container can read it later on. For example, again, I told you startup delays, cloning the repository, waiting for GitHub service, and do not bloating the image which is there. So that's what init container is used for. So now let's try to run some of this and see it in action. So we have cat init.yaml. This particular pod is API version v1 kind pod spec. In the spec, we are using volume directory. This is basically your shared file system. So you can think of it as two directories, two people trying to access the same folder from your laptop. So you specify containers as this and init containers as this. Init container will run to completion and go away. So what it is trying to do is it is using a busybox image, trying to run a command, getting kubesimplify.com as and saving it as at user share data index.html in the user shared data. So that's where it is trying to, this is what we have mounted. This is the mount path, user shared data, the mtdir. And Nginx will serve this user share Nginx HTML and use that mounted volume. So whatever is there here, it will mount that to the user share Nginx HTML. So let's run that. kubectl apply -f init kubectl get pods. This is the new phase that I was talking about. Init 0 out of 1 means it is initializing the container first. Kubectl get pods, it is running. So now let's do kubectl logs. If we do kubectl logs, it will show the logs of the Nginx container, but we can actually exec kubectl exec -it Nginx -it bootcamp pod -sh, and we can do a cat of user share Nginx HTML index.html. And we can see this is actually the HTML file for kubesimplify. So that's what it is serving. Exit the container. So this was the init container. You can have multiple init containers. Everyone will run in a sequence. Now, one of the key use cases for multi-container pods is also the sidecar pattern. Now, what happens is I'll show you different sidecar patterns. So these are the multi-container pods and various use cases. And also the sidecar pattern was not the sidecar pattern which we are used to. Like the main use cases of multi-container pods were the sidecar patterns. For example, you have the main container and you have the sidecar container which shares the same namespace. For example, very interesting example or very widely used is the service mesh. So you have a proxy server on every particular pod, it attaches a sidecar that does whatever communication that is happening. So you have a main pod, you have a proxy server, and that talks to maybe database service or whatever that is. You have a main pod, which is a web server. You might have a log forwarder that is sharing the same file system. That can be one of the use cases. You can have a main container. You can have a metrics collector as a sidecar container that is again pushing the logs, collecting the logs over localhost using the main container and then pushing it to the centralized monitoring system, kind of the adapter pattern. You can have, like in the service mesh, you can have auth, MTLS, health check, tracing metrics via the sidecar containers. So for example, user talks to the sidecar container and the sidecar container then does, MTLS, authentication, whatever that is, all the health checks of the pod, and pod finishes the job, pushes back to sidecar container. And if the pod A, the pod A has to communicate with pod B, it again, the sidecar communicates with the sidecar container and then it moves to the main container. So this is how it's kind of useful in the multi-container scenario. But multi-container pods are good, but the sidecar pattern was not native to Kubernetes. So in Kubernetes 1.33, finally the sidecar is now the first class citizen. How that happens? How that happens is there is a restart policy always that is included in the init container. So now you can put a restart policy of always in the init containers. Why it usually happened or what happened is basically when you can run init containers, okay, that runs in a sequence 1, 2, 3, howsoever it is defined. But let's say you have a sidecar container and you have a main container, and you do not have the regular first class citizen. but you don't know the order in which they'll start. Maybe the main container starts first and then the sidecar container start. The helper functionality will mismatch over there. Or let's say you have a job. In the job, there is a main container and then there is a sidecar container. But what happens when the job exits and the sidecar container is still running and it has not finished its execution and your job never ends? So in these particular scenarios, the sidecar native pattern is pretty useful. So this is a multi-container pod with sidecar. And how to enable that is when you specify restart policy always, it becomes a sidecar container. Now, this particular container will run till the life cycle of the pod. It shares the life cycle of the pod. It can also add some probes, like init container cannot have the probes and stuff, but sidecar container can have the probes and stuff. So now what it will do is we are using empty dir over here. I already explained you, like empty dir is basically two folks trying to share the same folder on the local machine. That's what empty dir is. So what it is doing is it is mounting the empty dir to slash user shared data, and it is every 5 seconds it is doing a cat of proc mem info and sharing that to index.html. And then there is Nginx container that is serving from that particular file. So what we can do is we can apply this kubectl apply -f sidecar. Kubectl get pods. We have 6 seconds ago, the multi-container pod, 2 out of 2 is running. So kubectl logs. And again, these are just the logs of the next container, but we need to see if the HTML is correct. So kubectl exec -it multi-container pod -sh cat index.html, and you can see, and this will keep growing. So cat is showing the correct output over here. Let's exit this, clear the screen. So this is how pods work in Kubernetes. This is the pod. This is the pod lifecycle. This is the sample manifest. You can use the imperative way. You can use the declarative way. You can describe, logs, delete, exec into the pod. We have seen that. You use generally pod templates when we do the deployments, replica sets and stuff. We'll again come back to the templates, conditions, some of the new features, Kubernetes 1.33. You've done container probes and multi-container pods with different patterns, init containers and sidecar containers as the first level citizens of Kubernetes 1.33. That was it about Kubernetes pods. Now we know about the Kubernetes architecture, the basic constructs, we know all about pods. But it is very important to understand one more construct before we actually move towards deploying the first part of our application, or we move towards something which is called deployments. So the concept that I'll be discussing now is called Kubernetes scheduling. Although we have touched a bit on it, like whenever there is a pod that is created, the next step is scheduler picking up the node, like scheduler trying to find a node where it can place the particular pod and then update the API server. But how that works and what all things goes behind is, I think, pretty important to understand from Kubernetes point of view. So let's say there are 3 nodes and one of the node is WebAssembly node, one of the node is GPU node, one of the node is CPU node. The thing is, you would want your GPU workloads to go to GPU node. If you do not specify anything, then Kubernetes will use its default scheduling mechanisms and algorithms and filters and scoring mechanism and select the best fit node. Now you can be lucky that it goes to node GPU, or you can be unlucky and it ends up on node CPU and it doesn't even run. What's the point of that? So for that, there is the concept of Kubernetes scheduling. But even before that, there are just 2 things I want to focus on. One is labels and selectors. So label is just a regular concept, like you add label onto the books, like this book belongs to Sayam, and then this book is a science book, a physics book, a chemistry book, or you add label to the items that you have in the kitchen, like this is tea, this is coffee, this has this much ingredients, this has this much protein, this has this much sugar. So all these are labels. And then you select, like today I want to drink tea. So I will select the box where tea is written. And if I want to select coffee, or I want to drink coffee today, then I will select the box where coffee is written. So basically labels are adding meaning to the object, and that is why we should label everything in Kubernetes objects as well. And labels are the key value pairs which we define in the metadata section. So labels are the key value pair. It's defined in the metadata section. You can see the metadata section over here. In that we have labels. Here we have live, demo, run, nginx. Key, live, value, demo, key, run, value, nginx. And now we'll be selecting on the basis of labels. So objects like deployments, this is the one that we actually want to learn, because we want to deploy our application, and for that deployment is critical. But yeah, so let's say we have deployment. In that we have something which is called selector. So selector, here we are saying select match labels app nginx. So match all the pods with app nginx. That's how it selects. Same goes for service. So like this, the selection happens, and the selectors can be a node selector as well. So we can say for a workload that select while scheduling, that do the selection on the basis of a label, like go to node WASM if it's a WebAssembly workload, go to node GPU if it's a GPU workload, go to node CPU if it's a CPU workload, and stuff like that. In selectors also, there is one equity-based selectors like component Redis, and others are set-based labels. Like in the match expressions, you can specify a set-based label, like key is tiered, operator is in, like in, not in, and exist, and the value is maybe cache or a multiple from the list, and it can be or over here. And then choose something which is not in the values, and then we can define the list over here. So kubectl get pods -- show labels. So for any of the Kubernetes objects that you want to show the labels, -- show labels is the command. And this is just running nginx image, getting the pod, showing the labels. Adding a label is easy. Kubectl label the object name, like the object type, which is pod, deployment, service, node, and then nginx, and then label. The next concept that I want to show is the namespaces. So that was about labels and selectors. Next up is the namespaces. So what happens is there can be multiple teams in an organization who are using a Kubernetes cluster. So namespaces provides you a logical way of grouping the resources together and isolating different teams. So dev can have a namespace 1, test can have a namespace 2, and they can logically differentiate the workloads they are deploying from each other. There are a lot of things that can be applied onto a namespace. For example, resource quota. So in Kubernetes, yes, you can define resources for your pod as well. For example, if I am deploying a workload, I can specify that minimum CPU and memory required for my pod, and the maximum, like the limit, it should not cross this limit. This helps in defining in better utilization of the resources. But there is something which is called resource quota. Let's say I put too much resources on my workloads, and I do not want other people to get deprived of. So what I can do is, maybe for test environments, I can add a resource quota on that particular namespace, so that not everything is getting consumed by the pods only in the test, in the namespace too, by the test team. And you can define the limit ranges as well. You can define the network policy if you want to restrict the network from one pod to another pod, from one namespace to another namespace. You can define network policy. By default, it's a NAT kind of thing that I showed you in the networking section, that how every pod is able to communicate with every other pod within Kubernetes. That's the default behavior of Kubernetes. Now let's say you have two nodes, node 1 and node 2. You can have a pod, multiple replicas of the pod, and some of the pods can be on node 1, some of the pods can be on the node 2, and they can be grouped together in a logical entity of namespace. Now, by default, there are some namespaces in Kubernetes. So let's try to see that. kubectl get ns. So by default, there will be default and kube node lease, kube public, and kube system. So what are these? kubectl get lease hyphen n kube node lease. You can see there are 3 lease objects. So the kube node lease is used by the nodes to send the heartbeats, like saying, hi, I am alive kind of thing to the control plane. Every node it gets lease objects, as you can see over here. And Kubernetes use these leases to detect the node failures without overloading the etcd. So it's like every few seconds the node is checking and it is saying that I'm alive, I'm alive, I'm alive. The default is the default namespace. If you don't say where to put your pods and stuff, if you don't specify any namespace, it is going to the default namespace. Then you have kube system. So all of your critical pods run in the kube system namespace. So kube system. So the CNI, the CoreDNS, the CSI controllers, the specific agents, metric server in this particular case, Kube-Proxy, all of the critical components which are required to run the Kubernetes ecosystem are running in the kube system namespace. And then kube public is basically a readable group by everyone. For unauthorized user also, it's mainly used to provide config maps like cluster info, so that kubectl connects to a new cluster. It has that information like where it can talk to. So that is a small gist of namespaces. Although namespaces has these constructs of resource quota, limit ranges, and network policy, but it is still not a very efficient solution for Kubernetes multi-tenancy or enabling different teams to use the same Kubernetes cluster with the isolation level. There are other projects like vCluster that can be used in this particular scenario. Anyways, let's do a couple of more demos over here. So I have something on the limit ranges side. So let's do that. So there is this limit range that is being applied on example namespace. So limit range is a Kubernetes object. First, let's create the example namespace. In the spec section, I'm saying limit, add the limits of type pod and give max CPU2 per pod. Max memory is 2 gigs per pod. Minimum is this. For type container, you have this. Default request. Default CPU for any will be this if I haven't specified any. And max and min. So it is something that you can define as part of your limit range. And this is namespace level resource. Let's see resource quota. Resource quota is another object. Here I am saying hard limits. That total amount of CPU that can be requested in this particular namespace is 500 M. Total amount of memory that can be requested is 200 gigs. Limit to the CPU, total amount of CPU limit across all the pods is 1. Total amount of memory limit across all the pods is 4 gigs. And total amount of pods that can be created is 10. So that's the only thing that can be done. So kubectl apply -f resource quota.yaml. I have applied that as well. Let's try to see a oversized pod. So pod oversized.yaml. So you can see here I'm trying to access resource with 600 MI. So it should kind of reject it. kubectl apply -f pod oversize. And yes, it does. So requested CPU and limited is 500. So limit is 500. I'm trying to request is 600. It becomes forbidden. It's not created. So that's how you can add restrictions onto your namespaces and make better choices when you are grouping the resources by namespaces for different teams. Coming back to the Kubernetes scheduler concept. So what we are trying to do is scheduler is trying to find the most feasible node to run its particular workload. So it is trying to find the most feasible node to run the workload. So first, the nodes that meet the scheduling requirements are called the feasible nodes. So it finds the feasible nodes and then scores them and use the scoring mechanism, tells about the highest rated one to the API server. That's what it does. How it does, this is the kind of flow that looks like. So pods line up here, it queues up. Then it uses two main things, filter and scoring. Filtering and scoring. This is based on the new scheduler framework, which has a lot of plugins. So if you go to the GitHub repository of Kubernetes package scheduler framework plugins, you'll be able to see all the plugins over here that can be for filtering and scoring. For example, least allocated prefers node with least resources, node affinity scores based on soft node affinity, pod topology spread scores nodes to evenly spread the pods. And then once it does the filtering and scoring, once it tries to find the pod and then it tries to score the pod, and then after that, once the highest score pod is there, then it binds them to the pod. Now, how you can influence the scheduling decisions? You can either write your plugins, you can either write your own scheduler, or you can use some of these concepts of node name, node selector, anti-affinity topology constraints. Before moving to that, there is another thing which is called scheduling gates. So in Kubernetes, you can also specify a scheduling gate. So pod scheduling gates are the feature that allows you to delay the scheduling of the pod even when it's ready to run. For example, there can be a custom controller that can finish preparing something, or external system that approves the pod, or some other condition is met. So if the gate is present, the pod will be gated. If the gate is not present, then the pod will be scheduled. Let's see that in action. So pod scheduling readiness. So I have this pod. Right now, the scheduling gate is disabled. This pod will run. So kubectl apply -f pod red pod scheduling readiness. Kubectl get pods -n demo pod. Kubectl get pods. You can see the demo pod is running. So kubectl delete -f pod scheduling readiness, vi pod scheduling readiness, and I uncomment these. So here I am saying scheduling gate name Sayyam. So the controller can do some stuff, and once it's kind of done, either the controller or you can manually patch it. Kubectl apply -f pod scheduling, and now you can see the status. Kubectl get pods, and it says scheduling gated. So that's what I wanted to show over here. Okay, moving on, there are 4 different things that can be done. One is node name. How node name works is I can specify a node name directly. So let's say I have this YAML. So there is this pod. In that, I can directly specify a node name. Like if I have kubectl get nodes, I have 3 nodes in this particular scenario, and I want this pod to directly go to this particular node. So I can just provide the node name so that it directly goes to this particular node. If I'm very sure about where I want to run a particular workload, I can directly use this particular feature. It bypasses the scheduler and directly assigns the node name, because scheduler also updates the node name field. So it directly bypasses the scheduler over here. Kubectl apply -f node name. Kubectl get pods. Node name. The first pod is running. Kubectl get pod first -o wide, and we can see ESRWY. That's what we defined in the node name, and that's where it got scheduled. So that's one way. The second one is node selector. This is what we have discussed, like it's based on the label selector kind of thing. So let's see that in action. Cat node selector. So I'm trying to say over here is I'm on a pod with the name Nginx SSD, and I want it to be scheduled on a node that is having a label with key workload and value was. So let's create this kubectl apply -f node selector, kubectl get pods, and I can see that there is a pod in pending state. Let's try to describe this. Kubectl describe pod, and it says there is no node available over here. The reason for that is there is no label right now on the node which says workload wasm. So now I can do is kubectl get nodes. I can pick any node, kubectl label node, and I can provide workload equal to was. Node is labeled, kubectl get pod, it has started. So kubectl get pods, it is in running state. So it got scheduled to the node that I just labeled with workload was. This is another way of scheduling using the label and selector. Let's move towards affinity, anti-affinity, taints, and toleration. So even node affinity is the concept where your pods can be scheduled based on the labels of the node. So it is similar to node selector, but it has some enhanced versions with more options like required during scheduling, ignored during execution. What that means, such a big term, but it simply means that the first half, it is required at the time of scheduling. The pod won't be scheduled unless this matches. So how you define it? In the pod, you define affinity, then you add node affinity, then you add required during scheduling, ignore during execution, and node selector terms match expressions. In the key, I'm saying this should be the key and it should have a value of zone A or zone B. Means it only gets scheduled on the node that has the label this in zone A or zone B. After scheduling, if the label changes, it keep running. That is what it means by ignored during execution. So ignored after the pod is scheduled. If the node label changes, the pod will stay. So that is what it is called preferred during scheduling, ignored during. And what do you mean by preferred? And there is one more. And there is one more, preferred during scheduling, ignored during execution. Means here I am saying required. So it won't even schedule the pod if this condition is not. Now I am saying preferred means it will try to match for this condition and try to find a node that is having this particular label onto that particular node. But if not, then it still finds a node and then just run it. So let's see that in action. Cat node affinity. So here we can see there is a pod, my container nginx with the container, and in the affinity section I have two things. One is node affinity, required during scheduling, ignored during execution. If I do not have this particular region value as chdk2, it won't get scheduled. Now I have this, so kubectl get nodes -- show -labels. I can see that chdk2 is actually mentioned over here for Kubernetes region. So yeah, this is the one. Topology.kubernetes.io, topology.kubernetes.io/region chdk2. So this is there. So required during scheduling should met. Preferred during scheduling is disk type SSD. So right now we do not have any of the nodes that is having disk type as SSD. So it will just try to find it. If not, then it will just find a node and will run it on any of them. So kubectl apply. Or what we can do is first to show that it won't work, the required during scheduling is working. What we can do is we can change the node affinity and we can put CHH because there's no label like this, no value like this. So kubectl apply -f node affinity, kubectl get pods, it should stay now in pending. So you can see my pod is in pending state. Kubectl describe my pod. So again, 0 out of 3 nodes available. So let's switch it back, remove one edge, kubectl delete -f node affinity, kubectl apply -f node affinity, kubectl get pods, my pod, and it's in running state now. So that's how you can use the affinity, node affinity and stuff, which is enhanced version of node selector. Now there is another concept over here is taints and toleration. So while node affinity is the property of the pod that attracts them to a set of nodes, taints and toleration are taints are the opposite. They allow the node to repel a set of pods. Let's take an example. So in this particular pods, I have a taint red dress. Now any user other than red dress, when it tries to come, this node will reject it. This node will reject orange. This node will reject the user with black dress. It will only accept if the user is having a toleration of red dress. So what happens is your node is having a taint foo bar and it is having an effect of no schedule. So there are three types of effect. One is no schedule, means that the pod won't get scheduled if it doesn't have a toleration and if the effect is no schedule. If it is prefer no schedule, then it will try not to schedule if there is no toleration in the pod. But if it's not there, then it will still execute. For example, if I have a preferred no schedule for this particular pod, it will fail for this node, but again, it will prefer not to schedule here and find another node. But if it is not found, then it will still, accommodate that. But if I have a strict no schedule, which is in this particular case, a pod without a toleration won't go here. A pod with the toleration will go here. So think of it like this. In a pod, in a node, there is a taint. Now, if you want a pod to be scheduled on the node having the taint, then you need to have a toleration in the pod. The pod having toleration that matches the taint on the node will get scheduled on the node, else it won't. As simple as that. And the last one is pretty interesting. If on an existing node, you add a taint of no execute, then all the pods that are not having the toleration will be evicted. So this is also used for taint-based evictions. So again, used for dedicated nodes, specialized hardware, and taint-based evictions. Let's see that in action. So first, let's add a taint. kubectl get nodes. kubectl taint node, maybe third one. And I'm giving app demo and giving no schedule. So node is tainted now. And let me cordon these nodes. So kubectl cordon. So cordon is a mechanism to mark a node as unschedulable so that there is no other pods that can be scheduled on this particular node. kubectl cordon, node name is the command. So kubectl get nodes. Now the only nodes that is ready for scheduling is third one, which has the taint. So if I run kubectl run second -- image nginx, kubectl get pods. It should stay in pending state. That's what it does. Because there is only one pod. Now try to understand this, because there is only one pod that needs to go on a node. It has gone to this node, but this particular pod doesn't have any toleration and the node is having this taint. So the only pod that can be scheduled on this node is toleration pod, because it has a toleration. So kubectl apply -f toleration kubectl get pods. Now the pod with tolerations will start running on the node 3. Now if I remove the taint, add a minus to it, it is untainted. And if I do the get pods, now the last one should also start running, because now I have removed the taint. And let's uncordon the nodes as well. kubectl get nodes. Now all three nodes are in ready state. Now the last one from this particular series is topology constraints. So topology spread, how the pods are spread across the clusters. So basically, let's say there are 3 zones and you have 3 replicas of your deployment, and you want every replica to go to a separate zone and or maybe equally distributed. So you want to create a fault tolerant system for your application by equally distributing the pods to the nodes. Here you can use something which is called topologies. There are some affinity as well, like inter-pod affinity, pod affinity, and kind of stuff that can also be used. But this is the most easiest way of doing using topology spread. There are 4 things. One is max skew, degree to which the pod can be evenly distributed. So max skew defines the maximum number in the pods between the most loaded and the least loaded, like the zones, racks, or nodes. It controls how evenly your pods are distributed across a specified topology key. In simple terms, for example, if max Q is 1, it's an integer value. So if it's 1, that means the most loaded zone or node can have at most 1 more pod than the least loaded one. Topology key is the key for the node labels, and when unsatisfiable, do you still want to schedule anyway or do not schedule? That's something strict or little less strict, and label selector is find the matching pod. Let's see that in action. That topology. So you can see over here in the spec section, topology spread constraint max Q1, and the key is kubernetes.io host name. So on the basis of host name, right, and try to find the pods with the label of app demo app. And if it doesn't match, like if the skew policy is getting violated, then do not schedule. So kubectl apply -f topology. kubectl get pods -n demo, and you can see all 4 are running. So what we'll do is kubectl scale deployment -n demo -n replicas 5, and we'll try to see its container creating. Now if it's replica 6, is container creating, replica 7, none. Let's call on a node, kubectl get nodes, kubectl cordon, and let's scale this to 10. Now what will happen is we'll see couple of pods in pending. Now let's do kubectl get pods -o wide. The thing is, we have the X pool having 2. We have the Y pool having 1, 2, 3, and we have the T is also having 3. So the difference between the max and the min can be 1. So 3 minus 2, 1, 3 minus 2, 1, which is fine. If it schedules one more to a particular node, then the difference will be too much, because now I have cordoned one node and there's only 2 left. So this is how it evenly tries to spread the pods using the max queue. Few more things before we wrap up the scheduling. One is the priority class. So you can define a priority class, which is a 32-bit integer, and that simply means higher the number, higher is the priority. It is used for critical apps. So in Kubernetes, we already have priority classes, get priority class -a. You can see we already have system critical priority classes that are already present. And if you want to create a priority class, you can simply do a priority class object and provide a value. Higher means higher value, and make it as global default as false. So you can add it to a namespace, and then if you want to use that in a pod, then you need to add in the spec section of the pod as priority class name. As soon as you add the priority class name, what will happen is when there is an overload, or when there is when a node is under pressure, then these will be the higher priority pods that will be given the precedence over the other pods, because they are considered as system critical pods or mission critical pods. So this is what priority is. Another one is pod overhead. So sometimes the So some runtimes like gvisor uses more resources for the pod operations, and we can specify something which is pod overhead in the runtime class itself. And this is how you specify the pod overhead. And when the scheduler sees it, it will add the pod resources, the pod resource request, whatever stuff is provided for CPU memory, plus the pod overhead over here to make the scheduling decision. So I think we have covered almost everything in the Kubernetes scheduling ecosystem, how Kubernetes scheduling works, what are the labels and the selectors. We'll also do that in services and see how the pods are getting added and the endpoint slices are getting updated. We learned about labels and selectors on the basis of which node selector also works. We learned about namespaces, which are the logical entities. Very simple to create namespace, kubectl create namespace, Siam, kubectl run nginx -- image nginx n hyphen n Siam. So you can specify all these things, kubectl get pods -n Siam. And then we saw that how you can specify the namespace level resources on a namespace and some of the default namespaces, then how a scheduler works, which was the main essence. Queuing, filtering and scoring. The filtering and scoring is pretty important over here, and then how it binds. And how you can alter the behavior of scheduling by using node name, node selector, affinity, anti-affinity, states toleration, and topology constraints. And also how you can restrict the scheduling using the scheduling gate. And then some of the priority class and pod overhead that you can use as well. So now with this, we have completed our at least the basic constructs before we now move on to deploying the application, the first part of our application. Now that we understand about the Kubernetes architecture, we understand about the pods, we understand about the scheduling, finally, we can now deploy our workloads. So we'll be deploying our workloads using something which is called deployments. So deployments is also a Kubernetes object. And before that, there are two things that I want to discuss. One is replication controller. So replication controller is a legacy controller. It uses selector to manage the pods. By now, you know what a selector is. It selects on the basis of labels, and it can be key values. So this one is only used for the equity based. And then came the replica set, which was the enhanced version of replication controller, and it supports set based operators. And this acts as the building blocks for deployment, because you also won't create replica set. In the end, you will be creating a higher level construct called deployment. And when you create a deployment, replica set automatically gets created. So this is how a replication controller looks like. You have metadata, you have replicas 3. So means there will be 3 replicas which will be running. And then it will select all the pods with the matching labels of app, my app. And the templates for those would be metadata label, app, my app, and spec section of containers will have name this and image this. For the replica set, as you can see here in the match expression section, this is where it adds more value, because it can now use set based expressions and selectors. So it's a higher level construct, better than replication controller. So both replication controller and replication set maintain the pod replicas. Replication controller is older and supports only equity based. Replication set, the replica set, is newer and supports set based selectors and is part of the deployment ecosystem. Also, there is something which is called non-homogeneous pod. So I can actually show you that. So let's say we have a pod replica set. So this is a pod. So what it means is just create a pod with the label app nginx and just have an nginx image running. Now there is a replica set. The replica set says that create a pod with app nginx label, and I want 3 replicas of it. So basically replica set will have 3 replicas and it will generate app label x, app nginx as labels for the pod. Let's try to see it in action and then it will be more clear. So kubectl apply -f replica set. kubectl get pods. And you can see 3 pods are getting created, which is fine. And if I do --show -labels, it will have that label, app nginx, perfectly fine. And it automatically adds the hashes to it. And kubectl get rs means that there are 3 pods which are there. Now, if I create this kubectl apply -f pod rs, kubectl get pods, it didn't get created because the replica set takes the pod with labels app nginx. Now they are already part of the replica set and 3 has to be maintained. So replication controller says that there are already 3 pods with this label. So I cannot accommodate another pod. But let's do it other way around. kubectl delete -f nginx rs, kubectl get pods. Okay, there's nothing in the namespace. Now I apply kubectl apply -f pod and kubectl get pods. We'll see here nginx pod which is running. Now, if I create kubectl apply -f nginx rs, this will be very interesting because it creates 2 new pods, but it will add the 3rd pod automatically to the replication set. So it will count that as 1 pod. See that kubectl get rs. The desired is 3, current ready is 3 because there was 1 pod which was already running as app nginx label. So this concept in Kubernetes is called as non-homogeneous pod, like it can be part of the ecosystem as well using selectors. Now let's come to deployments. So deployments are basically used to deploy our applications because in Kubernetes, that's what we want. We want to deploy the application, and if something goes wrong, it should automatically heal. And we also need mechanisms to do easy updates to the application because every time you write an application, there will be a new version of that application that you want to test. You might want to test that and update that gradually without any downtime. And then you might want to record history, declarative versioning, and also if something goes wrong, then an easy rollback mechanism. Everything is doable in deployments. And let's see how it works. So imperative way is kubectl create deploy nginx --image nginx replicas 4. So it creates a deployment kubectl get deploy. It says 3 out of 4 is ready. kubectl get rs. It also creates automatic rs. And you can see 24 seconds ago, the replication set is also created. Now, if we scale down, so we can scale up, we can scale down. How we can do that? Kubectl scale deployment nginx replicas 3. So it has scaled down. If I do kubectl get pods, now there will be 3 replicas instead of 4 because we scaled down. When I scale down, what happened and how it picks up which pod to delete. So there is a pod priority kind of thing. Like there is a priority order for pod deletion. Pending pods that aren't ready yet are deleted before any running ones. If there is an annotation of controller Kubernetes IO pod deletion cost, then lower values are deleted first, higher values are protected from deletion. Pods of the nodes with more pods from the same controller is deleted and then it helps in balancing the number of pods per node. And then older pods are deleted before the newer ones based on the creation timestamp. And then if everything is kind of similar stuff, then it's a random selection. So we have seen how to create a deployment, but let's see some of the other mechanisms as well. So let's create a deployment course with image nginx replicas 3. So the deployment is created and we can actually check out quickly the rollout status. You can see that the deployment is successfully rolled out. So here you can see kubectl rollout status deployment and the name of the deployment. Let's say you are changing a particular image. Maybe you have added certain set of features and this is the new image that you want to set up. So either you can do kubectl edit of the deployment, or you can directly use the imperative way kubectl set image deploy course and change the image. And you can use -- record. -- record is actually deprecated. So instead of that, what you can use it, you can actually annotate the deployment. So you can use this annotation, kubectl annotate deployment course, and change cause update to nginx 1.14 kubectl get pods. What happens here now is, so there was one pod that got created and it went to image pullback off, but the other ones didn't get removed immediately because of the rolling update strategy. So there is something which is called a rolling update strategy. I'll come to that, but before that, you can actually see the rollout history, what has happened. So kubectl rollout history, and you can see update to nginx 1.14, and you can see this. So I updated to 1.14. What we can do is we can actually go back to one revision. So we can say rollout history, maybe revision 1. So revision 1 was having the image nginx, and it shows you what it was there in the revision 1. In case we want to undo the deployment, and if we say revision 2, then we can see this particular thing is image 114a. So there are messages which can help you with each revisions what is happening. Now, if in this particular case, like you can see there is error that happened. Okay, this is the error. And this can be like your pod crashed or your new application is not working. It corrupted the database, or the database connection is not handling well, whatever the reason might be. Now you want to roll back. Your current application with the previous version of the application is still running. So the application is not yet down for the end users who are connecting to the service and trying to access your application. That is still working. But now your course new image is not working and you might want to roll back. For that, again, the command is kubectl rollout undo deployment course to revision 1. We want to revise it to revision 1 itself. And you can see the deployment is rolled back. So kubectl get pods. 3 pods are up and running. So another thing that you can do is you can pause the deployment. So let's say you scaled it to 6 replicas and did a pause. So I don't know how fast it went. It did 6 or not. 1, 2, 3, 4, 5, 6. Yeah, actually it was pretty fast. Before I was able to do the pause, it actually started all the containers. So yeah, but you can pause the deployment. It's not, actually I haven't used it anytime, but yeah, rollout history is important. Adding the annotations is something that you should be knowing, and then how to roll back. So you remember this command, when we updated the image, what happened? There was an image pull back off and there was one extra pod. So there were 3 pods plus there was one more pod that was created. Why that is created? So there is something which is called kubectl get pods, kubectl get deploy course, or nginx, whatever you want to use, nginx -o YAML. So there is something that gets added over here, which is called a strategy called rolling update. By default, the strategy is rolling update. So that is the default strategy. Max search is 25% and max unavailable is 25%. So this is one type of strategy, and you can specify it as the number of pods as well. So what happens here is Kubernetes starts new pod with the updated spec. As the new pods become ready, it deletes the old pod so that it can save the application from downtime. So you can control how many pods are added and removed once. So there are 2 fields that you can set: max search and max unavailable. How many extra pods that can be added temporarily? How many pods can be unavailable during the time of update? So we can say that there is maximum one unavailable pod that can be there, and there can be maximum 1 pod that can be extra. How many extra pods can be added temporarily? So with replicas 3 and max search 1, the maximum number of pods running during the update can be 4, which we actually saw. And for this, the maximum, this means at any point during the update, at least 2 pods will remain available, because max unavailable is 1. So this particular strategy is something that you can tweak around and add. Another strategy is recreate. So the recreate strategy is that Kubernetes deletes everything and only then it starts creating the new pods. So cat recreate. So this is a demo deployment. So kubectl create -f recreate kubectl get deploy. Everything is fine. Now vi recreate. I make it as nginx v1. And what we'll see now, kubectl get pods. Kubectl apply -f recreate. Immediately there will be 3 pods container creating at the same point. So 3 pods will get in container creating state, and all of them can fail because that's what it is. It is not meant for gradual rolling update. So this is the recreate update strategy. Now, often you will hear when we talk about deployments, 2 more things. One is canary deployments and one is blue-green deployments. So what happens is user is accessing services and there are different versions of your application that you want certain amount of users to access that, and gradually you can increase the traffic of the users to your newer version of the application. So for example, right now it's V1, V2, and V2 is something which is new. So only certain amount of users can go to V2. It's basically traffic splitting on the basis of weight, which is very easier to do in a gateway API stuff that we'll be talking about later on, or service mesh concept as well. Now, blue-green will have both versions of your application run. So you'll have V1 pods, 3 replicas, and if you have V2, then you'll have V2 pods, and then you just point the service from V1 to V2, and everything will be changed. Here, you gradually increment the application using canary. So let's see the canary stuff in action. So we have deploy canary. Cat deploy canary is a deployment with 1.17 image, 9 replicas. We have V2 cat deploy canary V2, that is 1.181 replica, but both of them has same labels. So obviously the label will be same, then only it will be added to the service. And then we have canary SVC. So kubectl apply -f canary SVC, kubectl apply -f deploy canary V2 and deploy canary kubectl get pods. You can see there are pods that are getting created, and if I do kubectl get deploy, we'll see 9 out of 9 pods running. But let's see one interesting thing. Kubectl get endpoint slice, and this one -o YAML. We'll see that the addresses are going to Nginx table. That is fine. Nginx table, stable, 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 stable. And then there is one more pod which is there, Nginx canary. So Nginx canary pod is also added to the services. So some amount of traffic will start going. And as we keep increasing the number of replicas of this, we keep decreasing the number of replicas from the other one. We are gradually increasing the traffic towards these particular pods as well. Because in the end, I told you, right, whenever service is created, you have IP tables rule, everything is there. And IP tables follow the basic round robin kind of load balancing. So it will automatically switch to, whatever pods are associated with that particular service. It automatically sends the traffic, and out of 10, one request can go to this particular thing. And as you gradually increase, you will see. So this is something which is called weighted or traffic splitting in service mesh in different terms. And then in blue green is completely different, because here at a single time you will directly switch from V1 to V2. So that's about deployment. So now that we have learned about deployments, it's important that we start deploying our applications and move a small steps towards deploying our application in production. So the first step is we have already seen three microservices that our application is having apart from the database, which will be the CloudNativePG. We have a front end which is there for the application. We have the auth service, we have the game service. So this is what something that I explained in the initial part of this particular course. So by now you should be knowing what app we are going to deploy. For that, what we need is we need to create the images. So we containerize the application and Kubernetes run those containerized applications as pods. And we will be creating deployments because we want higher level abstraction to manage those pods in order to use the Kubernetes features at the maximum. So what we have done here is I have three front end, auth service and game service. So if I do ls front end, there is a Docker file here. If I do ls auth service, we have a Docker file here. And if I do ls game service, we have a Docker file here. So we have a Docker file for all these. The main thing is to build these Docker images and also the nginx.conf. So let me just pull that in. Cat front end nginx.conf. So inside that, I have explained when I was explaining the application as well, I explained, but now what we are going to discuss will even make this more relevant because here I have specified that if it comes to API auth, the proxy path is auth service.crashcourse.hvc.cluster.local. Now, when we were discussing the concept of CoreDNS, this is something that will be part of the service discovery. So this and game service will also be part of the service discovery. And we will be creating a service as well for each of the objects. And we'll just, after this, we'll learn about services. But first part that we have to do is we have to create the images. So let's do that. For command for that will be docker build x build. Platform used Linux AMD 64. That is what the cluster is based on. Tag, use your own registry over here. I have used my Docker Hub over here. Then the name and then the tag. And I'm going to push as well. This is for game service. It should not take much time because I have already built it multiple times. And now for front end. So we change the folder and we also change front end. And the last one is auth service. We change here to auth service. And we should have all the three images pushed to our Docker Hub. We can actually go and check hub.docker.com. Sign in. And we can see front end, game service, and auth service. They all are pushed less than a minute ago. Now we need to deploy that on the cluster that we created. So kubectl get nodes and kubectl get pods -a. It was a fresh Kubernetes cluster. We do not have anything else. It has Calico, it has CoreDNS pods, Kube-Proxy, metric servers. We don't have anything yet on this particular cluster. Now let's start deploying the applications. So if we go to the manifest folder, you'll be able to see auth deploy, front end, game deploy, and then we'll be able to see their services as well. Game service, auth service, front end service. Services will come later on, but first we'll see what's there in the auth deploy. That auth deploy. So what does it have? It's a kind of deployment, as we have seen, one replica. It is matching the labels of app auth service for the containers. It is using SIEM 911 auth service v5. We'll just change it to what we just created. Final. Image pull policy, always container port 8080. Next, it has some environment variables. For the environment variables, we have to pass the database connection strings. So for Postgres host, we are using Postgres rw.crashcourse.html. svc.cluster.local. Now this is important over here because I already know CloudNativePG will create this for me. So when we'll deploy that, this will be deployed. Right now, we are not deploying it. Right now, we are not deploying the services. So right now, the application won't work, but it is fine because at first, right now, what we want is we want to create the deployment because we are building step by step our application. So even if this deployment fails because it is not able to get the database connection, that should be fine because we first are creating a application pod for auth service. Then the Postgres DB name for Postgres credentials, it is taking the secret key and the secret value. So there has to be these secrets created, username and secret created password. And then the resource request and limit for this particular pod. So again, we don't have any of these applications, any of these that are created. So it'll just be like kubectl apply -f. And yeah, before that, we need to change the name towards the image that we just created. So it is auth service. And the tag name is final. So vi auth deploy and final. So kubectl apply -f auth deploy. So that's the first deployment that we created. Now the front end. So cat front end, same deployment, app front end, and just the front end code. Here nothing is there, no environment variables, pretty straightforward deployment over here. So for the front end, what we have is, if we go back, we see front end and the tag as final. So we'll just change that vi front end and change it, the v1 to final. Kubectl apply -f front end. The front end pod is created. Now we create the game service. So we have the game deploy.yaml. So vi game deploy and game service, we'll make it final. That's what it was. If we go here, game-service. Here also, it's a simple deployment. We do have certain values. Again, this particular thing is needing some of the information. So we have the Postgres stuff, which will be there, and the credentials. So kubectl apply -f game deploy.yaml. Now kubectl get pods -n crash course. So none of the pods are working, which is fine for now. It is completely okay. We'll just redeploy them because we know there are a lot of things, a lot of moving pieces that we need to deploy in order for this application to work. But right now they are failing because this is container config error because there are no secrets and stuff, which is there. The env fails. This is not created because the configurations, the nginx.conf is not able to find the service. Again, the service is not something that we have created yet. So some stuff is not yet created, but it is fine. We have at least deployed our application. This is something we wanted to deploy. Now we have the understanding of pods, deployments, the application that we want to deploy for our demo. But there are certain things that needs to be deployed as an additional object. For example, deployment properties. So the properties in Kubernetes are created as part of a Kubernetes object called ConfigMap. Let's say you have a database. Now, what is the username of the database? What is the database URL? You want to dynamically pick it. So how do you pick that? These are the configurations for your application, environment for your applications. That should not be hard-coded and stuff. So when things should not be hard-coded and is needed by your application in form of environment variables or external endpoints and whatnot, they are all stored in config maps. But make sure to note that config map only stores non-confidential key value pairs. So as you can see, environment variables, you can get from config maps, configurations for your applications, you can get from config maps, container command line arguments, you can get from config map, and interacting with the Kubernetes API. So how you create it, like as a user, you would first create a config map. Config map is being used by the application. So you will create app.yaml file. It starts running. Everything is fine. Let's say there's a new change, but when you change, the config maps are changed, but they are not reloaded. So you would need to restart that. For that, there are projects like Reloader that automatically watch the config maps and secret changes, and then they restarts all those deployments, pods, etc., who are consuming your config map. There is a property that you can set immutable true, which means no updates are allowed. In this particular case, you are not allowed to make the changes to the existing config map. We need to recreate that. And in one way, you do not need to restart, which is only for mounted volumes. When you use config maps and mounted volumes, apart from subpath, then you have this config map and secret change detection strategy that can be used, where you won't need to restart a particular object consuming the config map. So let's actually see it in action to understand a bit more what a config map is. So I have created a config map, which is API version v1. So it's part of the core group. You already know now the GVK, GVR thing. The kind is config map. The metadata includes the name of the config map, data. This is the section that is important. In data, I am defining key value pairs. So in data, I am defining the key value pairs. Username is SIEM. Database name is example DB. Let's look at how I consume it inside the pod. So inside the pod, I have API version v1, pod name is MySQL. In the containers, I have a MySQL container. Now, in the env section, I specify MySQL user. Its value comes from. So value from. This is something you have to specify. Value from. In the value from where? From config map. From config map key ref. I'll be giving a config map key reference. Config map key ref. Refer to this particular config map's username key, and MySQL value will be the value of the key username inside the Kubesimplify config map. In this particular case, username is SIEM when we'll create this. So the MySQL user will be having this config map. Then the database name. So instead of username, now I give the database name. So that value should be example D. And then MySQL password. Here I have specified just demo123, which is a very bad, very bad practice. You should not submit the passwords because this YAML files can be stored on Git. We'll come to that. But let's create the config map. So kubectl gets config map. We have only the CA kube root CA cert. So kubectl create -f cm1, kubectl create -f pod1, kubectl get pods, container creating. Container is running, kubectl exec -it, -sh, env, and we should be able to see MySQL database is example DB, and MySQL user is SIEM. So it has properly got those values from the config map. And if we do kubectl get config map, we'll now see a config map. Kubesimplify config map, kubectl get config map -o YAML. We'll be able to see the data as well. Let's try another example. Cat cm2. This particular config map has some more values, properties, like how you define the properties. So here we have a config map, and in data, settings.properties. In that setting.property, the value is a multi-line argument, like multi-line file. So that I told you when I was explaining the YAML manifest thing, that you just attach, like just type the pipe symbol. So debug true Database URL is devdbexample.com and feature is feature enabled false. And then you have config map for production. Debug is false. And the database URL is prod. So this is app config dev. This is app config prod. And let's see prod 2. This is my web app simple deployment, which is there. Now, by now, you already know what deployment is. Replica. In the template, you have a web container. And in the environment, I'm specifying a development value. And here, what I'm trying to do is I'm trying to mount config map as volume. So you can use it as env, which I've already shown you. You can also mount config map as a particular volume. So I'm saying in my spec section of containers, there is a section called volumes, where I need to define the name of the volume and the config map. So the type of volume that I'm using here is config map. We have used mtdir a couple of times by now. This is the second one, like config map. Name of the config map will be the one that we'll be creating, app config dev. So app config dev is the one that we are creating. And here we want to mount the volume mount should be config map, config volume, and the mount path inside the container will be /etc/config. So kubectl apply -fcl2, kubectl apply -f pod2, kubectl get pods is container creating. So in a few seconds, the pod will be up and running. Kubectl get pods. Now what we do is we'll try to exec into the pod, exec -it, pod name --- command. I just want to get a shell into it. And ls/etc/config. So it should have now the properties. System properties has been totally mounted. If I do a cat of it, so cat/etc/config/system properties, settings.properties, settings.properties, it will have everything that was there in the config map. So this is how you can attach the whole set of config maps as properties inside the containers using volume mounts. Now you remember when I was showing you the pod 1 manifest, I mentioned over here that the MySQL password is demo1, which is not cool. This is where the second concept comes in this configuration ecosystem, which is secrets. So secrets is also a Kubernetes object. For example, if you want to store app credentials, or if you want to store tokens, if you want to store certificates, if you want to pull image from a private registry and you want to create a secret token of your Docker account, then how you create that secret. It's a sensitive data, but make sure it's not as secure as you think, because it's just base 64 by default. It is not encrypted at rest. But yes, you can enable the encryption by generating a key, encryption config file, updating the manifest, creating a secret, and then inspecting. We can actually do this particular thing as well. But in order to use them securely, the best methods is to use the projects like external secrets operator, or sealed secrets, or secrets to CSI driver. We already have videos on this channel. So if you want to deep dive more into how to connect an external system to use secrets, so that you can push those manifests to GitHub as well. I'll show you why I say that. But first, let's try to understand and do some demos. Now, I am inside the self-managed Kubernetes cluster because here I need access to the Kubernetes API server manifest file, because I need to update that in order to enable encryption at rest. So this is something that I have never shown before. And this is something that Kubernetes now support, that you can enable Kubernetes encryption at rest for your secrets. So the first thing is creation of encryption configuration. So vi-enc.yaml encryption configuration for secrets providers is AES CBC key 1, and this is something we need to update. So we'll just create that. In order to create the base64 encryption key, let's use head-c32 random, and this is the key. Let's add the key here. Save this. Now we need to edit the etc Kubernetes Kube manifest Kube API server. Here we need to enable or add encryption provider. Now we have given that our file should be at /etc Kubernetes enc.yaml, but I don't think our file is there because our file is right now in /Ubuntu itself. So what we'll do is mkdir /etc/Kubernetes enc, and here we'll now move the file. Move enc to /etc Kubernetes enc. Now we have the file at the correct location, and we need to add two more things to our Kubernetes API server, which is the Kubernetes volume and volume mount. So we come down to the section of volume. Inside the volume, we add a name, a host path. On this particular host, the file lives in etc Kubernetes enc, where we have just created that. And then inside the pod, we have to also add volume mount. So we need to add a volume mount section as well. Let's add that. Now we have volume and the volume mount. Let's save it. It will take some time for the Kubernetes API server to come back. So let's wait for some time. kubectl get nodes, and we can see that after some time the API server is up and running. So we can try and create our secret. So this is the imperative way of creating a secret. kubectl create secret generic, the name of the secret from literal password is equal to Kube-Proxy. Secret is created. Now let's check in etcd. I'll explain you what I mean by this over here. And you can see if in etcd it starts with k8s.enc.ae and whatever this is key1, that's what we defined, right? So means that the secret is stored in with encryption in etcd. So we have enabled encryption at rest for secrets. Now you can see over here, I exported the CA-cert. In order to communicate with etcd, we need to communicate with CA-cert, cert, and the key. So I've exported that. It was in /etc/Kubernetes PKI folder. It's generated by default. And then I run the command etcdtl, which I have installed on this particular system, get /registry/secrets default demo secret and hex dump for that. And this statement over here means it is encrypted at rest. So I hope you enjoyed the demo of encryption at rest. So we have different types of secrets, which I haven't explained. You can see from the docs, you can create opaque secrets. Like these are the most widely used one. Then this one is obsolete, like not obsolete, but it's deprecated. The recent one is you create a service account token and then you create a token. When we did the curl request, you remember when we did the API REST API curl request to the Kubernetes API server, we created a service account like kubectl create service account SAM. And you can see it already exists because we did that demo. So we can create SAM2, kubectl create token SAM2. And you can see this is the token that gets generated. So this is also something that is being used now. Then the Docker file, Docker config file, basic auth, SSH auth, TLS, and Bootstrap. These are some of the secrets that you can create. So let's try to create some secrets. Like imperative way is kubectl create secret generic opaque secret from literal password super secret. Kubectl get secrets. You can see there is a opaque secret. Kubectl get secret -o YAML. When we do it, it specifies a base 64 encoded. Now echo, if I put this and I do base 64-D, it will give me super secret. So which is the reason why we cannot store YAML manifest file in GitHub repository or wherever in public domain, because if anyone has access to data, they can just do base 64-D and they'll be able to get the value of the password. So you can create using the YAML manifest as well. If you create using the YAML manifest, make sure to add this in base 64 encode. So first you have to encode it in base 64, add that to your YAML manifest, and then create the secret. So you can create a basic auth secret like I mentioned. So let me clear the screen. kubectl create secret generic my basic auth. Here, the type I have specified, this can be a generic secret. If I don't specify kubernetes.io basic auth, but I have specified, so I have to give at least one parameter from username or password. So that's what it created. Next, we can also create SSH auth. So SSH egen, we can generate the private key pair, and it should be like ls.ssh id ed, this one. Okay. And if I create the IDRSA secret where we have to specify type Kubernetes SSH auth, we need to give the path or just in the root /root. And yes, so we have to give the path /root/.ssh and the private key. It creates the secret for that as well. kubectl get secrets. You can see basic auth, SSH, opaque, different types of secrets that are created. Now, let's actually combine the first example that we had, cat pod 1, which was not good in terms of giving the password. So let's see, we have a new pod 3 that we can create. Here, MySQL root password. So the secret is fine. The user value is coming from our bootcamp config. I don't know which config map we have. Get config map. So we have the kubesimplify config map. So we need to edit pod 3 and we need to take it from kubesimplify config map and kubesimplify config map. So the password, MySQL root password, is coming from, now instead of config map or key ref, we are giving secret key ref. So here we are giving secret key ref, MySQL root password and password. So I think we should be having that secret as well, or we can just create it. kubectl create secret generic MySQL root pass from the literal password ABC123 and kubectl create secret generic MySQL user pass. So I think the root pass failed for some reason. Let me create that again. Okay, we have both the secrets created. Both the secrets are used here. One is used in the root pass, one is used in the user pass. So, and we have the config map already created. So we should be able to create the pod 3 .yaml. kubectl get pods. It should be in container creating and running very soon because it has already the secrets and config map created. And you can see the pod is up and running. So the last thing that we'll do is I already have a Docker file with me and it's a simple one. So what we are going to do is we'll just build it for the platform and then push it and also use the Docker 2 Docker file that I just had. And it should just push that to the repository. Yeah, it is pushing that. We can see that on the Docker Hub account. Docker Hub. Let's go here. And we can see the course demo is here. Let me make this particular image as private. So making it private, course demo, make private. So this is now private. So let's create a pod for that. Vi pod 4.yaml and use the image that we just built. And for now, since we don't have any image pool secrets, we'll just hash it kubectl apply -f pod 4 kubectl get pods. It should be image pull back off because it cannot pull the image because it's a private image. Now let's create a secret. So the secret is kubectl create secret docker registry. This is not a generic secret. The name is pullsec. Docker username I have given, Docker password I am taking from a secret. I have already exported that as a environment variable on my file, and then the email. So the pullsec secret is created. Kubectl delete -f pod 4 vi pod 4. Now I can uncomment the image pull secret. So I'm telling my pod to use the image pull secrets for pulling the image. Kubectl apply -f pod 4 kubectl get pods container creating. So it's not in image pull back off. It is in running state. So those are some of the use cases for Kubernetes secrets and Kubernetes manifest. For our specific use case, for our specific demo, the only thing that we need is one config map. So if we go to the manifest and see all the files, we'll be able to see a config map. So that's the config map. This particular config map is actually in the namespace crash course and is having the init SQL file, basically for creating the tables and stuff like that. So that's where we learned about config map and secrets, because we wanted to apply the config map that will be used by our CloudNativePG, Cloud Native Postgres, and will be used to create the initial set of table. Now, since the next step is about services, so it's important to understand what services are. Before that, there is a small concept of daemon sets. So we created deployment, but there is another Kubernetes object called DaemonSet. So DaemonSet is basically a Kubernetes object that creates a copy of the pod on all the nodes. That's the only purpose of DaemonSet, or the subset of nodes if that is configured. But mainly, for example, you have logging agents. So you can have logging agents copied on all the nodes, and you don't have to copy that. You don't have to create that manually. This automatically takes care that the copy of the pod is running on all the nodes, on this, on this, on this, and this. And if this is removed, then automatically the pod is deleted. And if a new node is added, automatically a copy of the pod is also added using the DaemonSet controller. It automatically adds a new copy of the pod. So for logging, for whatever agents that is required to run on all the nodes, it is required. In Kubernetes itself, if you see kubectl get DaemonSet, if I do -a, Kubernetes automatically creates like Calico. It has a DaemonSet Kube-Proxy. It needs to configure the IP table stuff for all the nodes. So it has to be running as a DaemonSet. So like this, the DaemonSet has to be there. So let's create a DaemonSet. Now this is a very simple DaemonSet. So it's part of the apps v1. You already know the GVR, GVK thing. Kind DaemonSet, metadata, the name of the DaemonSet is Nginx DaemonSet. The image and the selector is name Nginx. It is similar to deployment, but it just means that DaemonSet object will take care of making it available to all the nodes and or the subset of nodes when we configure that. But in our case, we just wanted to run on all the nodes. Spec, we just say it should be Nginx image. Kubectl apply -f deployments DaemonSet. Kubectl get pods you can see the DaemonSet is creating pods in all the nodes. So we have 3 nodes. There are 3 pods that are getting created. And if I do kubectl get pods hyphen -o I'll be able to see that they all are on different nodes. You can see that they are on the different nodes. So that's the only purpose of DaemonSet. Just wanted to touch on that topic. Now we want to create the services. For services, we need to understand what services are. So let's try to understand the services concept. So now a user wants to access kubesimplify.com or wants to access your application. Obviously, you people go to a particular web page, right? You people go to a particular web page. Then something magical happens or something magical has to happen so that kubesimplify.com, the application code that is running as pod, it serves the exact thing which is there inside this particular pod. How it happens? We cannot directly map kubesimplify.com to a pod IP. First, the pod IP is internal. It's internal IP address. kubectl get pods hyphen -o. I can't map pod IP to 192.168.136.80 because it's just a private IP. So I can't point it to that. So because pod IPs are ephemeral. For example, if I delete this particular pod, kubectl delete pod hyphen force, it will come up again. But the problem is the IP address of the pod will be different. So you can see 4 seconds ago, this one came up and the IP address of this particular pod is pretty different. Because of the nature of the pod, the pod IP address is ephemeral. As soon as the pod goes down and it comes back up, it just takes from the random pool of the pod CIDR range. It is not guaranteed. So we can't use this. So we have to use another level of abstraction in Kubernetes, which is called services. So services is a concept that creates a virtual IP and you can map. So now what a user will do, a user will call kubesimplify.com and the kubesimplify.com is actually mapped to a service. Now services will redirect it to kubesimplify's pod IP address. We have actually seen this in action when I explained the concept of Kube-Proxy. Because whenever you create a pod, you create a service. Whenever you create a service, the Kube-Proxy will update the IP table rules in order to define the chaining. So we have already seen that in action. But there are a lot of services types. So you have cluster IP that is used for internal communication. That's the most basic service. For all the pods that communicate with other pods or for all the services inside, we create a cluster IP service. For example, in our architecture as well, we have the front end, then we have our auth service and our database service. And you can see when I showed you front end nginx-conf, we are directly communicating with the cluster IP service. We are communicating with the cluster IP service over there for our auth and game, which is fine because we don't want this to be exposed to the outside world. And this is only for the internal communication. For that purpose, we just specify the cluster IP service. But again, the whole agenda is how do I get access to outside world? For that, there's a concept of node port, but we do not use node port for that purpose. Node port actually assigns the static port on the node from this particular range, 3000 to 326, 30,000 to 32767. Now, the issue is, or basic use of node port services, that it is just used for internal testing and these kind of scenarios, or for bare metal Kubernetes. Like if you don't have access, if the cloud controller manager is not there and you cannot provision a load balancer kind of service, which is a public IP address, so then this particular thing is used. What you can do here is you can map a IP of the node with a port number from this particular range and you'll be able to access it from the outside world. But the most commonly used is load balancer. But actually it's not commonly used. Yes, you had me right. See, the thing is, we cannot create load balancers for everything, right? Yes, I can create a load balancer for a front-end service. I can just map it here. But then I have to see, like, it incurs cost. And if I have multiple applications on my Kubernetes clusters, how do I do that? How do I create all these load balancer stuffs? And how do I do path-based routing? It's not possible over here. Also, load balancer depends on cloud controller manager. Headless service. So it is, this particular service is type cluster IP. This particular service is type node port. This particular service is type load balancer. Headless service is of type cluster IP. What is a headless service? Let's try to understand that. So in the cluster IP service, there is a IP address, but in headless service, the only difference is the IP address is not there. It's cluster IP none. So in cluster IP service, the DNS resolves to a virtual IP. So DNS resolves to a virtual IP. Whereas in headless service, the DNS resolves to individual pod IPs. Yes, it resolves to individual pod IPs. And the load balancing also, there is no load balancing in the cluster IP service, and there is load balancing in the cluster IP service. The use cases are pretty simple for internal communication, internal routing. Obviously, I told you, you use cluster IP service, but when the clients want to talk directly to the pods, for example, in stateful sets, we'll just come to stateful set in a second. So when we want to create stateful sets, you definitely need something. You definitely need to communicate directly to the pods, which happens via the headless service. So this is what headless service is, and its main use case is stateful sets. So what happens? Let's try to understand stateful set as well. Since we have done deployments, we have done DaemonSet, let's try to understand stateful set as well. So when we create a deployment, let's say we are trying to create a database. So usually Kubernetes was made for stateless applications. So Kubernetes was meant for stateless applications, but soon people wanted to run databases as well. But databases are tricky, right? Because in database, if you have to create architecture of a master slave architecture, like you have a master and then you have two slaves for that, and let's say you want, this is the master database and you want a copy of this on the slave database. You want to have copy of this particular data. So you need to define that this particular thing is master and this particular thing is slave. But the pod IP address is, the pod's name is ephemeral. The pod name is auto-generated when you create a deployment. So how do you define those names? So there is no static name for the pods. And if the app goes to a service and says that it wants to do an insert operation, then it can actually go to any of the pod. Yes, there are ways where you can have three deployments which are talking to the same database. So let's say you have one database and these three are trying to, map to the same database, the persistent volume, I'm saying the same persistent volume, which ideally you do not want to do. If this goes away, then what happens? And then you are writing and then you're reading. So how do you do that? So there is read write once, there is read write many as well, but that is not ideal scenario. The ideal scenario is that every pod should have its own copy of its storage. So there should be a persistent storage. This should have its own persistent storage. This should have its own persistent storage, and this should have its own persistent storage. Now, when the pod goes down, how it comes back and attaches to this particular storage, this is also tricky. Now, because in deployment, what happens? The scaling process is uncertain. There is data inconsistency. And the deletion process is random. If you delete, there can be a random pod of deletion. If you create, there will be immediately a new pod created, but it will be with random name. So everything is random. And this is where the concept of stateful set comes in, where the names are predictable in nature. So pods get a sticky identity. That just means the name are predictable in nature. It has ordered scaling and deletion, and it uses a headless service. There is one extra thing that you can define in stateful set as well, apart from the deployment regular things, which is the volume claim template. So you can define this volume claim template. So what happens is, as soon as you create a stateful set, it creates the predictable naming pods. For example, if you create a stateful set with Postgres, so the pods that will be created are Postgres 0, and this will be created first. It's persistent volume claim, and everything will be created first, and this will be ready. Then this particular pod will be created, then this particular pod will be created. So if you have a data replication mechanism for your database, what you can do is, you already know that your Postgres pod 0 will be acting now as the master, and the Postgres 1 and Postgres 2 will be acting as slave. So now it is easy to do the data replication mechanism for your pods and create a full-fledged database. And these all are connected to their individual PV and PVCs. As soon as any pod goes down, it will automatically, it can pin up on another node, but it will make sure that the same PV is getting attached to this particular new pod. When you delete, the pod Postgres 2 will be deleted, and then 1 will be deleted, and then 0. When you scale up, the Postgres 3 will be the next one in the sequence. So scaling is predictable, deletion is predictable, and everything is easy. So data cloning made easy, as you know the host name for the pods, you know the order, so that you can designate the architecture for your choice. And this is where your headless service will come in. Let's try to see this in action. So I have the StatefulSet API version apps v1. So it's also in the apps v1. StatefulSet. The name is now Postgres, and the service name it has. And in spec, we can define a service name. So service name also is Postgres. Replicas 3, selector, which is fine. Metadata is fine. Spec, it's Postgres, container port. It needs a password. It needs a username, which is fine. For now, I'm just giving random values. Now it is using something which is called volume claim template. Here I am saying that I need a persistent volume and a storage with access mode read write once and 1 gig of resource. And it should be mounted at varlib Postgres data for each of the pods. Now kubectl get sc. For everything to work with the persistent volume, there has to be a storage class. So kubectl get sc. Right now there is nothing, but what we can do is we can go to Exoscale, we can update our SPS cluster, and we can enable the Exoscale CSI. You already know the concept of container storage interface. So I'll update that. It is updated. So soon we'll be able to see a storage class coming up, and the pods with respect to that, the node plugin and the controller plugin will soon start spinning up on this particular Kubernetes cluster. So you can see we have 2 storage classes which is already there. kubectl get pods -a. We'll be able to see the Exoscale CSI controller and the node plugins as a DaemonSet that are coming up on the nodes. And everything is up and running. So let's clear the screen. We'll do kubectl apply -f StatefulSet kubectl get pods. You can see Postgres 0 pending, Postgres 0 pending, kubectl get PV. So PV, soon the PV should start appearing over here, and then it will attach. The CSI will start working on that. Right now it is pending. Now the reason for that is that in our kubectl storage class, we do not have one as a default. Like we have to provide either a storage class name or we need to have something as default. So we can patch. So kubectl patch storage class Exoscale, and we are saying that this should be marked as true. Very simple command of kubectl patch storage class. So now if I do kubectl get sc, we'll be able to see that there is one storage class which is default. Now if I do kubectl get PV, I'm able to see that there is one which is created, kubectl get pods, it is bound, and it is now container creating state. As soon as it gets container creating and everything is working, it will go in the next phase. But we haven't created a service yet. So cat Postgres cat svc. So this will be the headless service. So in Kubernetes, how you create a service using a YAML manifest is kind. So it is in the core group. Kind is service, metadata, label for the service. And here you do not do anything. You give cluster IP none because this is a headless service. And the selector is app Postgres. So kubectl apply -f svc, kubectl get svc. The service is created here. You do not get a cluster IP. Let's say you want to create a service. Meanwhile, everything is working, getting working. Let's try to do this cluster IP thing as well, right? Because the cluster IP service was something that we wanted to do. So let's create a pod, kubectl run nginx -f image nginx, and then let's create a pod, kubectl run nginx 2, and then let's label the pod Nginx 2 with run Nginx. Now let's expose. So this is how you expose a service. kubectl expose pod. This is the imperative way of doing it. kubectl expose pod Nginx. Give the port -- port 80. And I did a dry run client -o YAML. This is the YAML manifest. So it says I want to create a service of the default service type, and the selector will be run Nginx, and these are the ports. So let's do that. kubectl expose pod. Now I have run this command, kubectl get svc. We have a cluster IP service created 5 seconds ago with a cluster IP. So it got a cluster IP. I can also do kubectl get endpoint slice. So I'll be able to see that for my Nginx service, I got 2 endpoints over here. Why I got 2 endpoints? Because I have kubectl get pods -- show -- labels. Because I have Nginx 2 pod having the same run Nginx label and the Nginx pod having the same label. So it has added 2 pods over there. And if we try to see the YAML manifest that was generated, the selector that we used was run Nginx. So it is based on the label selector thing that we studied long back about labels in selector. So that's how services work. So this is the cluster IP type services used for internal communication. And also the CoreDNS would have created a DNS entry for that. So I can actually call this particular service using the service name. And we can actually see that using a busybox container. So if we do kubectl run busybox and -rm and go get a shell into that. So we are into that. And now if I do the ns lookup of Nginx, you can see nginx.default.svc.cluster.local is pointing to 10.107.13.176. 10.107.13.176. So the core DNS part is also working. And that's exactly what we have used in our application as well. So now we are ready to actually see what's there for our application. Now, before we actually create the services for our deployment, we'll just quickly check if the stateful set that we created got successfully created. And yes, we have Postgres 0 that got created, Postgres 1 that got created, Postgres 2. Now, again, everything will work as it is. Like if we scale it, you get Postgres 3 or 2, whatever that number is, the larger will get deleted first. So it gets a sticky identity, and that's how you are able to access that. So this was about stateful set. Very good for databases and stuff. And headless service. So what we have completed is we have done stateful sets, we have done the cluster IP service, we have done the headless service, and there are a few more services that I want to discuss, but they are just for the discussion purpose. The main one is that we have to create for our applications, which is the auth service. So cat auth service, very simple auth service with a spec selector of app auth service, and it is having the port of 8080. kubectl apply -f auth service. Same, we should have a front end service, cat front end service, a service that selects app front end. Very simple, kubectl apply -f front end service. And last is the game service. So kubectl, so cat game service, very simple, selector app game service, port 8081. kubectl apply -f game service.yaml. So kubectl get svc -n crash course. So for our course, we have 3, which is deployed kubectl get pods -n crash course. So all our pods were crashing. I don't know what's the scenario now. At least the front end one should start working. So let's try to delete this. kubectl delete pod -n crash course, get pods. And we can see the previous Nginx error, the Nginx config error that it was getting is resolved now. The reason of that is it was using the game service crash course svc cluster local. Now this is resolvable, right? So if I do ns lookup of game service crash course svc cluster local, and it is directly pointing to the IP address of that. So let me exit the busybox container now. kubectl get svc-n crash course. That's the 151 is the IP of the game service. So like this, the game service and auth service is fine, which is why the front end pod is now running. Now the auth service and game service will start running. Auth pod and the game pod will be start running when we have the Postgres stuff set up, which we'll do next. But before that, since we are learning about Kubernetes, it's important to understand what all the other services Kubernetes has with certain examples, and also one little concept of ingress controller. So let's start with that. So cluster IP for internal communication and headless service for stateful applications. Now we have still we haven't solved the purpose of people trying to access our application from the outside world. How do they do that? So let's discuss that. One of them is node port. While node port, yes, it does give you access on a particular port because it binds the static port on the node to the service, but it is only widely used, as mentioned before, for a bare metal Kubernetes setup or when you want to internally test some of the systems. So we already have an Nginx service. So if we do kubectl get svc, we have an Nginx service that we created before. Let's try to edit that and change the cluster IP to node port, edit svc Nginx. And if we scroll down, we'll see a type. Now the type here has to be changed from cluster IP to node port. That's pretty much it. And when we save it, kubectl get svc, we should be able to see the Nginx type changed to node port. The IP remains the same, but the port is updated to 31795 of the host. So it has mapped that to the host. So that's what it does, what we can do, how to access it. kubectl get nodes. Now the IP tables will create all the chainings and stuff. We can actually do a -o wide and see the IP addresses. So this is the IP address. Let's put this here. And the port as 31795. It should be welcome to Nginx. Now this is publicly accessible because I am accessing it from the UI, from the web browser. It is working, just good. But we don't usually use this because we don't add this as an A record to a particular service. So what we usually do is we use a service type called load balancer. So load balancer is another service type that creates a public IP and maps it, and it is really dependent on the cloud controller manager. So if we do now kubectl get svc, again Nginx is node port, but let's edit it. Kubectl edit svc Nginx, and in the type we do load balancer. Kubectl get svc. We'll be able to see that here instead of none, now we have started to get pending. Now, if there is no, now you can create a load balancer service for any Kubernetes cluster, but if there is no cloud controller manager that is talking, like there is no connectivity agent talking to your cloud provider to provision the public IP address, then this will always remain in pending. But I know like this is Exoscale Kubernetes cluster SKS. So it is connected to SKS, and SKS has the capability that as soon as it sees the service type as load balancer, it will create a public IP and assign over here. So after a few seconds, if you see, if I do external IP of 91.92.117.224, and if we directly hit this IP, you'll be able to see welcome to Nginx. This is the IP that I can map onto my services, and publicly accessible. Yes, it is doable, but still, this is not what people usually do. This is not the recommended way to do it. Although, yes, load balancer type services are used. So load balancer, in the end, how we actually use a load balancer service is via an ingress. So in Kubernetes, there is also a concept of ingress. So this is a Kubernetes native concept. So Kubernetes ingress is a Kubernetes native concept. But just as networking in Kubernetes is dependent on the CNI that we install, ingress will work on the basis of ingress controller. Like you have to install an ingress controller in order for ingress to work. So what happens then, the recommended way is you create a cluster IP service that goes to the pod. Like when you create that, it has the endpoint slices and everything. And in the ingress, you define how you want to map it. And before that, you need to install an ingress controller. There are various ingress controllers from different organizations. It supports path-based routing. For example, if I install an ingress controller and I do the path-based routing, sayampathak.com/Twitter, sayampathak.com/YouTube. This should go to service A, this should go to service B. I can define that in an ingress object, but I cannot define that in the load balancer concept. So basically, ingress is something very advanced version of load balancers, how you can define it and how you can map it to the path-based routing for different services, different routes, and it is very easy. For our application, like for the application that we have to deploy, we'll not even use ingress. We'll use something which is even superior to ingress, which is called gateway API. We'll just come to that, but I just wanted to let you know that there's this concept which is very widely used, and gateway API is barely new, but everyone is transitioning towards gateway API. So let's actually see one example of ingress controller as well, just to show you that it works and how it works. So I have a few files over here. One is the deployment. So by now it's pretty simple to understand the deployment, API version, kind deployment, one replica. It's just for the Nginx pod. But here, interestingly, what I'm using is I'm using a config map. So I'm using a config map over here. So volume mount et/etc nginx.conf. So what I'm using is I have created a config map. I have to create a config map called nginx config, and I have mounted that config map inside the container, and I'm saying that my nginx.conf should be replaced by nginx conf, which is inside this particular config map. And what is this nginx conf? It's pretty simple configuration over here. I'm just saying that when you are listening to port 80, if the location is /, then just put index.html file. If the location is /public, then just return to a 200 with a message access to public granted. That's it. And the service will be cluster IP service. So it's a simple service. When I don't define anything, by default, it's a cluster IP service. So I don't define anything. I just say select everything with app nginx, which is the same as app nginx. Now the next thing is ingress.yaml. But before we dive into that, let's first install ingress controller first. So this is simple ingress nginx controller that I'm trying to install on this particular cluster. So it has created namespace, service account, role binding, all this stuff, and it will create a service, config maps, deployments, jobs, ingress class, kubectl get pods -a. We should be seeing ingress nginx. Yes, it is in container creating. The controller is getting created. So we just need the ingress controller to work. Now let's see the services in this kubectl get svc-n. You can see this is the load balancer type of service. Now here, the load balancer service is very important, and this is how it's most widely used. For ingress, I will have a load balancer service. Now this is the load balancer service that I am having. And inside my ingress, the API version is networking kits, IO, that is the group, v1 is the version, kind is ingress. Ingress class name is nginx because that's what comes when we install nginx ingress controller. For the host, I have used the public ip.nip.io, which is the wildcard kind of domain. Then we define the paths over here. So we define the section called HTTP. In the paths, we define a path. So for /, it's backend service name Nginx, port number, and if it's /public, so it's the name-based routing. It should also go to this service. It can go to any other service as well, but here we have defined this, and we have the same configuration in nginx.conf. Yes, we do have to create the config map out of this. So kubectl create config map nginx config from file nginx.conf. Now let's create the ingress. Kubectl apply -f ingress. Kubectl get ingress. So that's the thing. It should also populate the address soon. And you can see now it's there. So when you want this to be applied to your domain, right now I have used wildcard. What you can do is you can go to sampadak.com, kubesimplify.com or yourname.com and then add an A record to this particular public IP address. And then you can use, demo.sampadak.com should point to this particular service or this particular route. If I do /public, it should go to this particular route. So let's see if our pod is up and running, kubectl get pods. So Nginx deployment pod is also up and running. So we should be able to get welcome to Nginx page. And if we go to public, we should be able to get 200. It asks for a file, which is strange. Anyways, download the file. And if I see that, yes, it says access to public granted. So whatever that is, it was just for a sample to show you how ingress kind of works, and it follows the path-based routing. So what we have covered in services is if we need to communicate with any of the pods, any of the application, we use a higher level construct called serv. If it is being done from inside an internal communication purpose, then we use cluster IP service. If it is used for internal testing and data center kind of thing where you don't have the load balancer service facility available, we use node port. If you want to expose it and use Cloud Controller Manager to provision IPv4 or IPv6, depending on the cloud provider, use load balancer. If you want to use StatefulSet, then use headless service. Or if you want, basically headless service gives you the DNS to individual pod IPs. And then on top of that, since you don't want to use load balancer for everything, on top of that, you have cluster IP, and then you create the ingress object. So let's cover the final pieces of services, the external name. So these are the services. These are used to access the services hosted outside of Kubernetes cluster. Like they have zero IP management, and we can specify the DNS record. So they come and as like CNAME kind of thing. So for example, if an app wants to access a database outside the cluster, we can create a external name service. Or if one namespace wants to communicate with other namespace, communication across namespaces, that can also be done using external name. So you can communicate with SPC in other namespace. Updates are easy because here you only change the external name and not the pods. Let's try to see that in action to understand it much better. So cd external name. So here what do we have? We have a lot of pipes. So one is app.py. So let's see what is that. App.py. So it is simple Postgres connection. So it is trying to connect with the Postgres database with bunch of environment variables. And in the end, it is just saying I am connected. That's pretty much what it is doing. Then we have something which is called database.yaml. So it is a Postgres deployment. So it is not a stateful set. It's a simple deployment for demo purposes. Then we have the requirements.txt, which is just the dependency which is used in app.py. Then we have the Docker file. Docker file is also just from Python, work dir, then adding the app.py, requirement.txt, pip install, and then running the Python app.py. For the YAML, we also have a service. So cat dbsvc, it's a simple service, cluster IP type, selecting app my database, which is same as app my database from the deployment of dbyaml. And then we have the external name service. So this is the external name service. So what we are trying to achieve over here. So let's try to see. We have an app. We have a app, cat app pod. We have a pod, my application in the application namespace. So this is in application namespace. So there will be a app pod in application namespace. Then we have a database. in database namespace, in database namespace. So we have the database DB. Now the app is connecting to the database using external name. It is connecting using external name. How? Let's see that. So we are creating a service and we are creating this service in the application namespace. So the service that we are creating, SVC, is in the application namespace. That's what we are creating. And we are specifying the external name as my database service dot database ns namespace dot svc dot cluster dot local, so that it will do the CoreDNS stuff, like it will go through the Kubernetes DNS service. Inside the app.yaml file, app.py file, you can see the connection string in the database host. So we have database host, which we need to get. So host is important. Let's see what is there in the database host of the pod specification file. In the database host, I am saying trying to connect to the external DB service. So in the connection, this dot connect and the connection string will connect to the host external DB service. It will query the DNS, which is the core DNS of the cluster, resolve to my database service in the database namespace, and then connect using the rest of the credentials. So let's create this. First, we have to obviously build the file. So we'll do docker build and we'll name it. We can use anything like ttl.sh Siam demo, and then we can use the current directory. So it should be building something. So in some time, the ttl.sh Siam demo should be built. So the application is built, ttl.sh Siam demo. We can do app pod and we can change this. And hopefully the pod should work. And in order for that to work, we also need the DB like kubectl apply -f db .yaml, and we need to obviously create the namespaces. So kubectl create namespace this database ns, and we also need to create the application ns. kubectl create ns application ns, kubectl apply -f db, kubectl apply -f db.sdb underscore svc, and kubectl apply -f app pod, kubectl apply -f external service. Let's see now if the pod becomes active. And you can see it's completed. kubectl logs in the namespace. And it says database is connected. So that was the whole point of showing you how the external name communication works. So there is one last thing and one last concept before we move ahead and try to fix our deployment pods, because I think our pods are struggling, right? kubectl get pods -n crash course. So we only have one pod running. We need our auth service and game service to work. We have the deployments in place. We have the services in place. But the thing is, the Postgres server, which is needed, the database for our application, is still missing. So before we move there, is one thing that I want to show you, which is the external DNS. So there is this thing called external DNS. I cover it always as part of services. So external DNS connects to the pod. It's a cloud managed DNS. External DNS is a Kubernetes controller that automatically manages DNS records based on your Kubernetes services or ingress. So you deploy an external DNS pod. It is a pod that you deploy on the cluster. So it is basically a Kubernetes project. So you can see external DNS. It's part of the Kubernetes SIG, and every provider has to provide their own external DNS configuration and stuff. So you have seen all the providers, and we'll be using Exoscale over there. For Exoscale, I have created the external DNS configuration and the pod. So cd external DNS. What will happen, by the way? So what do we want? And we want whenever we create a pod, then we create a service, then we create a load balancer. The external DNS pod will watch that. And what it will do is it will automatically create those A records. So now I don't have to create the A records when I create the load balancer. Automatically, external DNS pod will create those DNS entries with respect to the domain that it is matching. So for example, if I use external DNS alpha kubernetes.io hostname myapp2.sayampathak.com, and if I have sayampathak.com managed by Exoscale or the specific cloud provider, then Exoscale should create a DNS A record for my application pointing to the IP of the service or the ingress, because those are the two sources that it watches for. So in Exoscale, there is a thing called DNS. In DNS, I have one domain left. So I can do a add of sayampathak.com and I say manage this DNS. But in order for me to perfectly make this work, what I need to do is, if I go in, it has specific name servers. So what you need to do for this to work, you need to go to sayampathak.com in GoDaddy or whatever domain name provider, whatever the DNS provider you have. In that DNS, you have to change the name servers. You have to change the name servers to these name servers so that you are giving Exoscale the authority to manage the DNS entries for sayampathak.com. And now with external DNS, I'll be able to configure the Exoscale, my DNS, and auto configuration of those IP addresses. Let's try to see this in action. So now we have, at least we have the sayampathak.com. We can add the entries here, although it won't work because the name servers I have not updated on the GoDaddy and stuff. So the pod is pretty simple. Cat external DNS pod. It's simple deployment, Nginx, container port, simple service. But in that service, I have the external DNS annotation of external DNS alpha, Kubernetes.io and host name, and given that particular host name. It should add an A record for this particular domain, this particular host name inside, and it should be visible inside the Exoscale domain as well, Exoscale dashboard as well. So in order for me to create an external DNS controller, we have to look at the external DNS pod. So let's look at that external DNS. This is the pod or the deployment, I should say, with the cluster role binding. So it creates a service account. Service account needs to listen to services, endpoints, pods, get watch list, extension, networking gates.io ingresses, and get watch list of nodes. So it needs these permission. We create a role binding and stuff. And now we create a deployment. For external DNS, you use registry.ks.io external DNS with the version. But this varies from provider to provider. For example, here I have to specify the provider as Exoscale. The source, it should monitor services and ingress. Domain name filter is sayampathak.com. Policy, I want to sync the creation and the deletion. Then I have to give Exoscale API key, Exoscale API secret, Exoscale API env API, Exoscale API zone, DEFRA1, where my cluster is. So kubectl apply -f external DNS. So the deployment is created, kubectl get pods, external DNS is creating, and it's in running state. Now let's create the pod and see the magic. kubectl apply -f external DNS pod. It creates a deployment and a service. Kubectl get SVC. We should soon get a service. 4 seconds ago, it's still pending, but soon it should get a public IP assigned to this pod. And we should be able to see as soon as it does, our external DNS should create an entry inside the Exoscale. And if we had the name server also changed in our GoDaddy for our domain, then we give full permission to Exoscale to manage that DNS, and that is being managed by Kubernetes itself. So that is where it is very useful. So it has the IP, and now let's see kubectl get pods, logs of external DNS, and you can see created all records are up to date. It created a new record. So let's go back to this and refresh it. And yes, no need to refresh it. It automatically came over there. You can see the A records, my app 2. And it's directly mapped to 91.92.116.112, which is the service. So that's pretty much it that I had to explain from the concept of services. So I hope you got the gist of services. And now let's move on and fix our problem of making our application that we want to deploy. We are very close now. We have understood all the concepts within the Kubernetes construct to deploy our application. Just a little bit is left. Now let's move on and fix that to make all the pods running. And then we'll move on to very fancy thing called gateway API. So we'll not use ingress, although ingress would have been very easy, right, for this particular course. But let's learn a step ahead. Let's learn something new and something latest that everyone is moving towards, which is gateway API. So we'll learn about gateway API and something, the implementation called K-Gateway, and we'll install that and then get everything up and running from external. So kubectl get pods -n crash course. We still have only one pod running. What to do? The reason for that is we have mounted certain stuff inside the pod which we haven't created yet, which is the CloudNativePG. What do I mean by that? Means we don't have a database yet. So these two services are trying to get secrets, the Postgres, because it is connecting to a Postgres, but there is no Postgres instance yet in the crash course namespace. So we need to install that. For that, we are trying and we are going to use something which is production grade called CloudNativePG. So CloudNativePG is a production grade Kubernetes way of running PostgreSQL. And it's an operator that covers the full life cycle of a highly available Postgres database cluster. So it's autopilot mode. It doesn't rely on the stateful sets as we have studied before. Stateful sets are used for databases, but it has its own limitations. So this one comes up with its own way to manage the persistent volume claims. Don't worry, since this has come up here, we'll just, after installing the CloudNativePG, we'll learn about Kubernetes volumes as well. So it is designed for Kubernetes. It is cloud native in nature, security and TLS, high availability, disaster recovery, monitoring, advanced architecture, Postgres operations. Everything is covered in CloudNativePG, which is why we'll be using CloudNativePG. How to install that? We go to the documentation, we go to the V125 release, we go to the installation page, and we copy the installation command. That's pretty much it. Let's try to see when we run this, what happens. It creates a namespace and it creates something which is called custom resource definition. Wait. What are these CRDs? So Kubernetes is an extensible system. By default, Kubernetes has pods, deployments, replica sets, services, ingress, network policy, StatefulSet, all these default Kubernetes objects. But let's say you have to create your own object to extend, make the Kubernetes system extensible called SIEM or maybe kubesimplify or whatever that can be. For that, you create operators. You create something which is called Kubernetes operators. And there are a lot of frameworks that lets you do that. And one of the framework is Operator SDK that lets you build these operators. So now when we do kubectl API resources, we'll be able to see that not only we have the regular ones, but we have now the Postgres ones. Like the RBAC and the one are easy, right? Because they were created, like these are already there by default. But the Postgres one is something which was new. Now I can do kubectl get clusters, which was not there before, because now it is part. Now the clusters are identified by Kubernetes because there is something which is running kubectl get pods-n CNPG system. So there is the control manager which is running, which is watching for these objects, poolers, databases, clusters, etc. So we have CloudNativePG installed. How to create that? So we have Postgres cluster. So we are saying that API version is PostgreSQL.cnpg.io. That's the group version v1. Kind is now cluster. The metadata section, we specify the name. We say we need 3 instances, means there will be some persistent volume, it will do the magic and all that stuff. And while bootstrapping, we want the initial DB with the database of DB name, owner, user, and I want to initialize that with some initial SQL. So we have something called init.sql where we are specifying some of the tables that we want to get created for auth service, for game scores, game stats, etc. So let's create a Postgres cluster. Kubectl apply manifest pg cluster.yaml. Postgres cluster is created, means it is accepted at least. And if I go to crash course and see the secrets, I am able to see now a newly created secret called Postgres app. Now, if you see the cat auth deploy, we have specified environment variables in which we have the user, which is being taken from the secret key reference, which was not earlier there, which is why there was a container config create error. Now it is there. Now it is there. We have the DB name that we have specified in the CloudNativePG. You can see that in the manifest PG, we have the DB name as DB name. And the DB host, we have given a service. This is the DNS. So this will be also created. Kubectl get sbc-n crash course. If you see the Postgres RW is also there. Now this particular Postgres will fail obviously because we haven't created the config map out of the init SQL. So there is no init SQL like kubectl get config map-n crash course. So we need to create that as well. So kubectl create config map init SQL from file in the namespace crash course. Now let's see what's happening in the namespace. Get pods-n crash course. Okay, it was already in init phase. Let's see if it has started to progress in its init phase. So we can see it started the initial check. It has completed. So it should start now the first pod. Also, we should be able to see kubectl get PV. Yes, our persistent volumes have started to create as well. And it should be creating pods. So first pod is running Postgres 1. The second pod will join it. So the second also is completed and the Postgres 2 is now in phase and it should be running shortly. And then the 3 will start. So we'll wait until all 3 are up and running. And also now if we see all our other pods, the auth service, game service, they are also up and running. So the good news is that the majority of our application is running. Now the only thing that we need to create is ingress. But wait. We are not creating the ingress, right? We are doing something fancy. We are going the gateway API route. So let's try to understand 2 different concepts of volumes because it has created some persistent volume, kubectl get PV. Let's understand what this get PV is. Let's try to understand this whole concept of Kubernetes volumes and then also about gateway classes, how they are superior to ingress, and then install kgateway and create the gateway so that we can do the final stages of our application and make it up and running. So Kubernetes volumes. Now, some places during this course, we have already seen the empty dir. I have told ephemeral volumes to be shared. So container, as soon as the container is gone, the container file system is also gone. So it's basically, which is why we call container or a pod to be having ephemeral storage. Like they are for the stateless application. We should not store anything directly to the pods, because if anything goes off, the file system is completely gone. So a user writes to a container. If the container gets restarted, everything is gone. What happens is, what are volumes? So Kubernetes volumes provide a way for containers inside a pod to access and share data via a file system. So basically, you have a laptop. On your laptop, you create a directory, right? That directory on your machine is actually a Kubernetes volume, as simple as that. So there are different kinds of volume that you should use for different purposes, such as we have ConfigMap and Secrets as volume, which we have already seen when we did the config maps and secrets section, that you can mount them inside your pods as volumes. You can use it for temporary space for the pods, like the empty dir. We have also seen this in action, but we'll do one more example. And then we have persisting data across the container restarts, which is the something called persistent volume claim. And also going forward, with the concept of remote storage, NFS servers, which lives totally outside of the cluster. And also there is host path when we need a particular directory on the host. So let's try to understand first the ephemeral storage. Or maybe, yeah, there are a lot of storages. So let's try to understand the ephemeral storage first. So ephemeral storage is referred by empty dir. Whenever a pod is assigned to a node, so see this, whenever a pod is assigned to a node and you have defined this in your pod, an empty dir volume will be created. It is useful for a scratch space or a cache or intercommunication of the pod. So pod is assigned to node, empty dir is created, and it is removed as soon as the pod is removed. And if you don't specify anything in the curly spaces, it creates on the host. If you specify medium as memory, it will use the RAM. So let's see that in action. So you have this empty dir, cat empty dir. You can see there is an empty dir pod. Container is busy box. It is writing a data to empty dir volume hello.txt. So if we do ls of this, we should be able to see this file. What it is trying to do is how you specify volumes. In the spec section, we specify the list of volumes, and then you give a name, and then you say empty dir. Here you can specify either this, or if I do a cat of empty dir2, instead of braces, you can specify memory. If the medium is memory, it is using the RAM. If not, then it is directly using the directory on the node. So you have a virtual machine, it creates a directory on the node, as simple as that. So let's create this particular pod, emptydir.yaml, kubectl apply -f, emptydir.yaml, kubectl get pods, emptydir pod is creating, kubectl get po, it's running, kubectl exec -it sh ls, and you can see in that you already have a file hello.txt. So that's how the empty dir volume is kind of being shared. Now if we go one step ahead, this was the empty dir volume. We also have a host path. Now host path maps a directory from host node into the pod. Here, one interesting thing is it is safe from pod restart. So here, if the pod is removed or it is restarted, it is gone. The empty dir volume is gone. But here, if the pod is restarted, it is still there. The directory is still there on the host. So it maps a directory from the host node into the pod. And this is how you use that. And instead of in the type, there are a lot of things that you can use. You can use directory, means the directory must be existing in the given path. So /data should be there, or directory or create. If nothing exists, it creates it. Same file or create, socket, and other stuff. So that's the only thing which is extra for the host path. So in the volumes, you specify host path, give the path and the type. So let's see what we have in the host path. So we are saying in the volumes /temp/host the pod, see and create. If this directory is there, then use it. If not, then just create it. So directory or create. So it will create this and again add this particular thing to mount this particular thing inside the container to this particular location /data/host path volume, and our container is writing to this volume hello.txt, as simple as that. So let's apply this kubectl apply -f host path, kubectl get pods, host path should be up and running, kubectl exec -it host path --sh, and if I do ls, we can see the hello.txt. Now, even if I delete this pod on the node where this is running, it should be present. That's what is meant by host path. Just to give you an overview, there are more types of volumes. iSCSI, it is a storage over network. You need to have your own server. It's just unmounted when the pod dies, but the volume is preserved. And this one is saved from the restart. This one is saved from the pod restart. This one is saved from the container restart, but not the pod restart. So this is tied to the pod lifecycle. Now let's come to something which is used in production, which is the remote storage. So for example, you can have your external GlusterFS cluster, you can have your external cloud volumes or NFS servers, and then you can install something which is called PVC. Like you can create something which is called PVC, and you can install a CSI driver. I have already explained you what a CSI driver is, all that stuff. So you can create a CSI driver. By default, the cloud providers will provide you an option to get the CSI drivers, or you can use some of the open source projects like Longhorn, Local Path Provisioner, and stuff like that. So whenever a user, in the end, what user creates is creates a PVC. The CSI driver will create a persistent volume based on the storage class, and then the CSI attaches that to the pod as well. Now, PV and PVC are independent of the pod lifecycle, which is the main thing. It actually abstracts the storage. There are two types of modes, like two modes of persistent volume. One is manual, one is dynamic. In manual, there is no storage class, and you create everything manually. You create the PV, you create the PVC, you create the pod. In dynamic, which is what is most widely used, we have a storage class. In storage class, we have a driver. That driver is having a pod, a controller, and all that stuff. As soon as we create a PV, it creates a cloud volume, and as soon as the pod is created, it attaches that. There is one more concept in persistent volume and persistent volume claim before we move to the demo is reclaim policies. There are two main reclaim policies. Recycle is kind of deprecated. So two main ones are retain and delete. In the retain one, the persistent volume and its data is preserved. Like if you want to troubleshoot afterwards or do manual recovery, you can use this mode if the PVC is deleted. Deleted is simple, like if you delete a PVC, the volume also gets deleted, as simple as that. So that was about persistent volume claim. Let's try to do that dynamic provisioning. So let's see what is meant by dynamic provisioning. Here I have a simple service, MySQL service, and I have a stateful set. In the stateful set, I have a service name MySQL because this is the headless service. That's how you do that. Cluster IP none. And in the container, it's MySQL container. I have a MySQL root password that should ideally be coming from a secret, but right now it's just coming as password. Now I have defined volume claim templates. Here I am saying create a MySQL persistent storage PVC access mode read write once. So there is read write once, read only many, read write many, and read write once pod. 4 modes. So if I do kubectl apply -f dynamic provisioning, service and stateful set is created, but let's go to the PV section. We'll see somewhere down the lane PVC or PV started to get create. So yeah, PVC is there and it is pending. But the interesting part is here we have given a storage class as local path. So I need to edit that and just remove the local path because I already have a dynamic storage class. So I don't need to specify that. Storage class name. Yeah, you can specify a storage class name too. So kubectl delete -f dynamic kubectl apply -f dynamic kubectl get PVC, and now you can see it has updated Exoscale SBS, and soon it should create its bound. So the PV got created as well. So that's the power of dynamic provisioning. You can see 16 seconds ago, this was created as well. I have an NFS server example as well, but it's not something that is relevant to our application, to be honest. But yeah, you can have a NFS server that you can create. So you can go through this README. You can have a NFS server installed on Ubuntu instance, and then export some of the variables and stuff, and export FS RAV, and restart the NFS server. And then you can have a PV. So this is how you create a PV if you want to create it manually. So persistent volume, capacity, access mode, read write many, and here you specify NFS. Here you specify the NFS as the persistent volume, give the path and the public IP address of your NFS server. In the PVC, you will specify persistent volume, read write many, and resources over here. And in the pod, you specify same volumes is this persistent volume claim. So you just specify the persistent volume claim. So this whole thing was explained just because of StatefulSet, obviously, and our cloud native Postgres actually created some persistent volume. So you need to understand the concept of persistent volumes because they are pretty important and are used widely in different kind of use cases. The last thing is for our application is the gateway API. So we have seen the power of ingress. So we know like ingress is there, like ingress and ingress object. This is the ingress object, the object that we created, right? It has the host and path matching. So you can specify a host, you can specify different paths. Like if the path prefix match /, then it is rerouted to this. If it is something else, it is redirected to something else. Then what's the problem? It works fine, right? But what about if multiple teams are working on the same ingress? There will be a problem. It only handles HTTP traffic. What about TCP, UDP? What about traffic splitting? What about additional redirects? So these are some of the problems like limited features. The ingress only supports TLS termination and simple content-based routing on HTTP traffic. This is from the docs. Reliance on annotations. So the problem is ingress also has certain things like you can do traffic splitting or you can do at least redirects or termination policies using annotations. So you have the concept of annotation to add more features, but all the implementations have different level of annotations. Like if you use traffic, if you use contour, if you use Nginx, everybody has different set of annotations, which is not industry standard. So there is a problem of portability. So the annotation approach to extensibility leads to limited portability, as every implementation of the ingress means every ingress controller have their own implementation of annotations. Insufficient permission model. Ingress is not well suited for multi-team clusters and load balancing. Also, it's just a single object. Like it's the same for administrators, same for cluster operators. There is no concept like, we just saw persistent volume or persistent volume claim. As developers, you'll create just PVC and PV automatically gets created or is configured by the administrators. Here, there is no concept like that, which is where Gateway API comes in. Gateway API is referred to as an evolution of ingress. As per the official documentation, Gateway API is an official Kubernetes project focused on L4 and L7 routing in Kubernetes. This project represents the next generation of Kubernetes ingress, load balancing, and service mesh APIs. Like it's something you should start using immediately. So it is divided into different personas. What do I mean by that? There is a concept of gateway class. That is when we install an implementation. So like we install ingress controller, we'll be installing an implementation of gateway class, gateway API. And when we install that, so that is dependent on the provider, right? Whether I want a K gateway or Nginx gateway or whatever that is. So it will get me the gateway class. So that is one. Next is the gateway. The cluster operators create these gateways. Next is the route. Now the application developers only have to specify the routes, like these are the route and it should directly route to my service. That's it. That's what the application developers has to specify. So we have segmented this into different chunks, like different responsibilities, which gives it as a mature model. One of the implementations of Gateway API is K-Gateway. It has become my favorite in the past few weeks. It is the most mature, widely deployed, and is also a CNCF object. It's very lightweight, have all the implementation also used for AI, LLMs. It has native MCP agent-to-agent gateway as well. So it is efficient for Kubernetes plus AI workloads. So we are not diving into everything, but we'll at least do get started and install this. In order to install the Gateway API implementation, which is the K gateway in this particular case, we first need to install the Gateway API CRDs. So that's our Kubernetes cluster, and we'll install the Gateway API CRDs. The next step is the CRDs of K gateway. So these are the K gateway CRDs, and just using Helm upgrade, create namespace K gateway system, and doing that. The last thing is installing K gateway itself. So this particular command installs K gateway using Helm. So K gateway is installed now. One more thing that needs to be installed is Cert Manager. Cert Manager is a tool that gives HTTPS. Just think of it as like I need HTTPS, so I need Cert Manager for my system. But we need to add an annotation for Gateway API enablement. So what we'll do is we'll first install Cert Manager and then enable that. kubectl get CRD. We can see we have the Cert Manager custom resources. So now let's do kubectl get ns, kubectl get pods or get deploy -n Cert Manager. And we have the Cert Manager deployment, Cert Manager, and we need to edit that because we need to enable one flag. This is the flag, -- enable gateway API. Now we need to do the rolling restart. Okay, kubectl get ns. We have K gateway as well. kubectl get pods -n. And we can see the K gateway pod is running. So, and we also must be having a service, kubectl get svc -n K gateway system, which is a K gateway simple service. Now we will be seeing some of the Kubernetes objects that we need to deploy for our application to work. Our application is up and running, services are there, Postgres database is also there now, everything is running, but we are still not able to access it from the outside world. How do we access it? Let's see that. So first is something which is called a gateway. Now gateway is API version, gateway networking k8s.io v1, kind is gateway. The name of the gateway is crash course gateway. The annotation here is Cert Manager cluster issuer, means use the cluster issuer's let's encrypt prod to generate the certificate. So obviously we need to create this as well. The gateway class name is kgateway. Let's see that, kubectl get gateway class. So we can see that there is a kgateway class already there. Next up, we have the listeners. So we add over here what are the protocols like TCP, gRPC and stuff. Okay, this is the HTTP listener, allowed on all ports, HTTPS listener, allowed on all ports, and we specify the host name. Host name for TLS as well. In TLS, we specify certificate reference, like certificate that has to be created refers what secret, which is course kube simplify comms TLS. This will be created. And the host name should be k8s2025 kubesimplify.com. So let's create this. Apply -f gateway. Now let's see the cluster issuer. So we have the cluster issuer. Let's encrypt prod. It has the server, private key reference, and the solver. Solver here is HTTP. Gateway reference, the name that we created, crash course gateway, and K gateway system. So kubectl apply-f cluster issuer as well. That is deployed. Now kubectl get gateway -a. We can see it is programmed true, and this is the IP address. And what was our host name? Let's look at that. The host name is K8s2025. So what we need to do is we need to go to RDNS, wherever your particular website is. Mine is on Squarespace. I'll add a record and I'll add K8s2025, a record, and the IP will be the gateway public IP address. Save it. This part is done. Now we actually need to see what is this. So the gateway class was created by the administrators. The gateway class was created by the administrators. I created the gateway, like which route it is, and for the host name, along with TLS configuration. Now the developers create TLS routes or HTTP routes. In our case, it is HTTP route. So what it says, this is similar to Ingress. So HTTP route, parent ref, crash course gateway, it has to refer to this particular gateway, that is the gateway reference. Host name, rules. I want to match the rule with slash, coming on this, going to front end pod, front end service inside the crash course namespace. Front end service inside the crash course namespace. So kubectl apply-f HTTP route. I also have something which is called HTTP redirect. It just means traffic from HTTP should be redirected to HTTPS. So kubectl apply-f HTTP redirect. Now kubectl get certificate -a. This is false. In some time it will be true because it takes some time. Just now I created the HTTP route. So in a couple of minutes, the certificate became true. And if we go to kubectl get HTTP routes -a, we'll see this is active. So we can actually try this out. It's 2025 kubesimplify.com, and we have it up and running. Let's try to sign up. Sign in 911. Sign up is successful. Let's log in. Login is working. Let's play Snake. Back to dashboard. Scores are getting updated. Tic-tac-toe. I win. Rock, paper, scissors. Tie, and I win. So the scores are getting updated. The login flow is working. Sign up flow is working. The dashboard is working. So the application is up and running. So we have finally deployed our application and learned all the concepts to deploy the application. We have learned about the pods, deployments, stateful sets, the volumes, the config maps, the secrets, the RBAC, authentication, authorization, admission. We have learned about the custom resources, the CloudNativePG, about cert manager, gateway API, K gateway, scheduling, and all the control plane components which are there, services, how they work, and everything in deep dive. Now we also have, you remember, right? We expose some metrics. So in Kubernetes, like we can install n number of things on top of that. So there is one more thing. When we want to monitor the Kubernetes cluster, generally people start off with installing Prometheus. And since we have already exported metrics, which I explained to you in the application part, we can actually see that metrics in Grafana dashboard and stuff. So let's check that out as well. So for monitoring, we'll be using something called Prometheus. And in that, we want to install Kube-Prometheus stack. So first is adding of the Helm repositories, Prometheus community, Helm repo update, and then doing install. So let's do that. kubectl create namespace monitoring. Helm install Kube-Prometheus stack in the namespace monitoring. So Kube-Prometheus stack is deployed. We need to get the admin user password for Grafana. So let's get that as well, which is prom operator. Okay. So let's try to log in. I don't know if it's already started. Localhost. Okay, Grafana is up and running. What about other pods? Yes, we have all the pods in the monitoring namespace running. So it comes with Grafana, Prometheus operator, metrics, node exporters, bunch of other things. Admin, operator, logged in. Now probably we need to create a new dashboard and see if our metrics is coming. Yes, for Prometheus, but it's not standard metrics, right? So we need to create something before this appears, which is the service monitor. So Prometheus will let you create service monitor custom resource. It's also operator. It watches that. So service monitor should be created, and we are labeling that release to allow Prometheus to find this. Namespace selector is crash course, and we need the values in app, in auth service, and game service. The endpoints is HTTP metrics. Path is /metrics. So kubectl apply -f service monitor. That is created. We can check the service monitors. Now let's do localhost 9090. So status, target health. We can see the targets are starting to come up. We can see this is coming up. Let's try to see in Grafana, and you can see the Flask metrics over here, like Flask HTTP request created, request total. So I run this query, and you should be able to see coming from auth service. So this is how you can do the monitoring kind of thing onto the cluster and expose the metrics and visualize that onto Prometheus. Store that in Prometheus and visualize that using Grafana. The Kubernetes course is now complete. So finally, the Kubernetes course has concluded. We have deployed the applications, learned all the concepts. But wait. The thing is that a technology like Kubernetes is ever evolving. There are new features, there are new developments that keeps on happening. So we cannot pack just everything inside one course. So though we have covered a lot of in-depth material for this particular Kubernetes course, but I strongly suggest after this course you do go and do HA monitoring. You apply Thanos and Prometheus HA over there because we just touched a bit on the monitoring aspect. Then you do the auto scaling because we haven't covered auto scaling in detail. We haven't touched on auto scaling. So it's like HPA, horizontal pod autoscaler, vertical pod autoscaling, in place vertical pod autoscaler, cluster autoscaler, all these things you should know. There are bits and pieces on my YouTube channel in terms of the blogs and in terms of the YouTube videos that I have already created on these topics. So you can go through that in the course. After this, I would say there are a lot of things additional that you can also do, but this sets as a solid foundation for your certifications or jobs or whatever that is for your complete Kubernetes understanding. Thank you so much for watching this Kubernetes course if you was still here. Now, the only thing I request is to subscribe to the YouTube channel Kube Simplify and share your favorite moment from the course. If you do happen to complete the entire project, then also share the screenshot of the completed project and tag us. We would love to reshare and repost your posts as well. Share it in your WhatsApp, Telegram, LinkedIn, whatever groups are active, And in the end, I would want to say a huge thanks to Exoscale for sponsoring my time so that I can bring this video to you completely free of cost. So I hope you enjoyed the Kubernetes course, and do comment if you like the course.